Ten mikrofon, to jest który język? Halo, halo, raz, dwa, trzy. Powiedz mi, który to jest język, do którego mówię. Mówię. To jest na angielski, tak? Ten, do którego... No to sobie nie, podpisujemy N, tak? Że do tego mówimy po angielsku.
Good morning, ladies and gentlemen. My name is Łukasz Cioch, and together with the ERC team, we'll take you on a 3-day journey to Mars, to the Moon, and back to the Earth. This is how we have designed this conference, and it is starting now. Welcome. 3 days of inspirations, meetings with experts from around the world, conversations about contemporary space exploration, but also competitions, science, maintenance, navigation, probing on our meticulously recreated Mars yard right outside the Kielce University of Technology. Every morning we'll be focusing on some of the more accessible aspects of contemporary space conversation. So introductory lectures, keynotes, presentations, demonstrations, education projects, especially for our younger audience, space enthusiasts, educators, but also teachers and, of course, children. Every afternoon will be about inspirations, Late in the afternoon, today, tomorrow, and on Sunday, we'll dive deeper into some of the more advanced areas of space exploration. And as the very last point on the agenda of each day, I'll talk to Łukasz Wilczyński to review the progress made after each and every day. Ladies and gentlemen, let's jump right in. We are starting with Home Mars Rover, a workshop prepared by Almocantarat.
Łaziki to niewielkie pojazdy, które wykorzystywane są do badania powierzchni innych ciał niebieskich. Do tej pory łaziki dotarły na Marsa i Księżyc, a pewnego dnia mogą trafić jeszcze dalej. NASA planuje wylądować z astronautami na Księżycu do 2024 roku. Astronauci będą mogli używać łazików do poruszania się po powierzchni Księżyca, przewożenia zapasów i badania terenu.
Cześć, jestem Gala z klubu astronomicznego Almocantarat. Dziś pokażę Wam, jak zbudować Wasz własny łazik napędzany gumkami recepturkami, który będzie mógł się przemieszczać. Do wykonania będą potrzebne dwa tekturowe kwadraty o wymiarach 13 na 13 cm. Posłużą nam do stworzenia kół. Wykorzystamy również jeden trochę większy tekturowy kwadrat o wymiarach 15 na 15, z którego stworzymy korpus. Użyjemy również nożyczek, ołówka, słomki, taśmy klejącej, linijki, dwóch gumek recepturek oraz dwóch cukierków z dziurką w środku. Nie przejmuj się, jeśli nie masz wszystkich tych materiałów. Bądź kreatywny i zastępuj je tym, co masz. To wszystko jest częścią procesu projektowania. Teraz przyjrzyj się uważnie prototypowi łazika. Prototypy są powszechnie wykorzystywane w inżynierii. Jest to baza, na podstawie której można budować, testować i oceniać. Udoskonalanie projektu na podstawie testów również jest częścią procesu projektowania inżynierskiego. Złóż karton na 3 części wzdłuż pofałdowania, tak aby boki były skierowane w górę. Każda część będzie miała około 5 cm szerokości. Na dwóch 13 cm kwadratowych kartonach narysuj przekątne. W miejscu przecięcia linii zrób ołówkiem mały otwór. Ważne! Unikaj przypadkowych ukłuć ołówkiem. Trzymaj ręce z dala od miejsca, w którym ołówek będzie przechodził przez karton. Użyj ołówka, aby ostrożnie zrobić otwór w pobliżu górnej części każdych z dwóch zewnętrznych fragmentów nadwozia. Upewnij się, że otwory znajdują się naprzeciwko siebie i są wystarczająco duże, aby ołówek mógł się swobodnie obracać. To jest miejsce, w którym znajdzie się oś. Wsuń ołówek przez otwory. Ostrożnie nałóż kartonowe kółka na każdy koniec ołówka i przymocuj je taśmą. Przyklej słomkę w poprzek dolnej części łazika po przeciwnej stronie niż ołówek. Wsuń cukierka na każdy koniec słomki. Zagnij i zaklej taśmą końce słomki, aby cukierki nie wypadały. Utwórz łańcuch z dwóch gumek. Zapętl jeden koniec łańcucha wokół ołówka. Zrób małe nacięcia w przedniej części korpusu łazika. Wsuń wolny koniec łańcucha w szczelinę. I gotowe. Aby łazik zaczął jeździć, obróć tylne koła, aby owinąć gumkę wokół osi i puść go. Obserwuj, co robi łazik. Zmierz odległość, jaką pokonał. Zastanów się, jak działał Twój łazik i co można by poprawić. Zastanówmy się wspólnie. Czy koła obracały się swobodnie? Czy łazik poruszał się w linii prostej? I jak daleko się posunął? W ramach dodatkowego wyzwania określimy siłę sprężystości gumki recepturki, używając wzoru na zachowanie energii. mv² przez 2 równa się kx² przez 2, gdzie k to sprężystość, x to długość naciągniętej gumki, m to masa, a v to prędkość. Musimy zmierzyć masę naszego łazika, jego prędkość oraz długość, na jaką została rozciągnięta gumka, żeby obliczyć siłę sprężystości. W celu policzenia prędkości wykorzystamy wzór V równa się S przez T, w którym S to droga, T to czas, a V to prędkość.
Aby policzyć siłę sprężystości, musimy przekształcić wzór na zachowanie energii. Na początku pozbywamy się mianownika, mnożąc przez 2. Aby otrzymać k, dodatkowo dzielimy przez x². Otrzymaliśmy wzór na siłę sprężystości. Teraz należy podstawić do wzoru znane nam wartości oraz obliczyć brakujące. Wiemy, że masa wynosi 150 g, jednak do wzoru należy podstawić ją w jednostkach SI. Przeliczamy wartość masy z gramy na kilogramy. Później to samo robimy z długością naciągniętej gumki, przeliczając jej wartość z centymetrów na metry. Jedyną wartością, jakiej nie znamy, pozostaje prędkość. Możemy ją łatwo policzyć ze wzoru V równa się S przez T. Z wcześniej wykonanego eksperymentu wiemy, że łazik pokonał drogę 17,5 cm w 1,55 sekundy. Zamieniamy jednostki z drogi z centymetrów na metry, podstawiamy obydwie wartości do wzoru, aby otrzymać prędkość. Podstawiamy wszystkie wartości do wzoru i liczymy siłę sprężystości.
Dobrej zabawy w budowaniu łazika i eksperymentowaniu. Do zobaczenia wkrótce.
Ladies and gentlemen, that was Home Mars Rover workshop prepared by Al Mukantarat. A perfect tongue twister of a name, you will admit. Next up, you've all seen those marvelous photos coming to us over the years, all the way from Mars, and that's the very topic of our conversation, except from a geological perspective. Through the eye of a geologist, what we can read from Martian photos. Here to talk to you about it, please welcome Ms. Natalia Zalewska, Space Research Center of the Polish Academy of Sciences. Dzień dobry, Natalio. Zapraszamy.
Słuchać mnie? Dzień dobry, witam serdecznie. Ja się nazywam Natalia Zalewska.
Good morning, welcome. My name is Natalia Zalewska and I represent the
Jestem
Center
geologiem z
of
wykształcenia,
Cosmic
a zajmuję się
Research from the
geologią Marsa.
Polish Academy of
I
Sciences.
tytuł mojej prelekcji to właśnie
the
jest okiem
title
geologa,
of
co
my
możemy odczytać z
presentation
marsjańskich
is
zdjęć.
from the perspective of geologists, what we can read
Chciałam
from
na
the
początku
Martian
powiedzieć, że
pictures
geolog
and
to
images.
takie
I
stworzenie
would like to start from a remark that geologist is
z
somebody
młotkiem zazwyczaj.
traveling a lot with a
Ogląda
hammer, taking a
pobiera
close-up
próbki.
look at rocks, taking samples.
Próbki często
And
zabiera
these
do
samples very
laboratorium.
often are taken to
stuka w nie
laboratory. They are hammered. They are
robi różne
they
analizy.
are examined under
co
the
ma zrobić
microscope
biedny
and
geolog,
analyzed. But
który bada
what
planety?
such a poor geologist can do
Oprócz
if he's
Księżyca nie
supposed
udało
or
się na
she's
razie
supposed
ludziom
to
wylądować na żadnej innej
discover
planecie.
new planets?
No,
Until
na Marsie
now,
może w niedługim
people
czasie się uda, ale są
did not
przygotowania.
land on any planet
jak na
yet.
razie
There are some preparations to
geolog
land on
może
Mars, but
tylko
not
liczyć na
yet. So
zdjęcia
for
i
now,
dane, które
geologist
są
has to
przesyłane
base
przez
their
sondy,
work
łaziki
on
i musi badać
photographs
taką
and
planetę na
images sent by
odległość.
probes
Ja trochę
and
powiem o tym,
rovers, and
jakie
which are sent
jakimi
remotely
sposobami się to
to
robi.
the planet Earth.
możemy
And I
właśnie
will
odczytać z
present
takich
some essays and
Zacznę
some
szybciutko
samples, how it
od
is done,
historii
and what we
badania
can
Marsa.
read from such
Oczywiście
images.
były
Let me
pierwsze
start
mapy
from
Marsa
the
jeszcze z
history of
XIX
Mars. There were
wieku.
some
Tutaj są
first
pokazane,
maps of Mars created in the 19th century.
Mamy
We
przykłady tutaj
have
map.
some examples
Mapy
of
są
such
zrobione na
historical
podstawie
maps
obserwacji z
made
teleskopu.
based
Więc
on
naukowcy,
telescope observations.
Schiaparelli
So
lub
scientists from such as Schiaparelli
Camille
or
Flammarion
Camille Flammarion,
Marsa
they
i
were
zaznaczali,
observing
to, co widzą.
Mars and they were
No, chyba
marking what they
Schiaparelliego
can
mapa
see.
jest najbardziej
The
przystępna i te
Schiaparelli's
nazwy, które
map
on
is the
nadał
most
terenom
accurate
marsjańskim, nawet
until
funkcjonują do
now, and he
No,
has
Flammarion
named
oglądał
all
na
objects
przykład,
visible on
czapy
the
polarne.
surface of
No, kto
Mars,
pomyśli, może
on
zgadnie,
the
o co
Mars.
tu chodzi. Ale
Flammarion
są obserwacje
was
tylko
observing
Niestety biedny
ice caps on
Lowell,
Mars.
zmarł
Unfortunately,
na serce z powodu
Lowell
tego, że nie chciano uwierzyć, że są kanały na Marsie.
died
A on był przekonany, że
from a
kanały są.
heart attack because
I
nobody wanted
tak,
to believe that there are some
frustracji
channels on Mars.
prześladowania,
Because of this
zamerował. Niestety.
frustration,
Wierzył, że
he
kanały na Marsie istnieją.
fell ill because nobody believed in his Mars channels.
Ale właśnie
But
co taki geolog,
what such
rzeczywiście
a
potrzebuje?
geologist
No ja
can
powiem
do
krótko
and
o
what can
sondach
use?
marsjańskich.
So let me start from saying about Martian probes. We have some first images made by mariners, the number 4 and the 9.
Już widać, coś było
We
na
can
tych
see
zdjęciach, już
some
podejrzewano, że
first
te kanały
images,
są.
so
Warto
people started to
zbadać
expect that
Marsa.
it is possible that channels are there and that it's worth exploring Mars further. Further research and Vikings in the years sent in the years 1975 to 1982 show some real channels, images of these channels. But there was a question.
Nie wiedziano wiele o Marsie.
What about water on Mars? Because nobody knew anything.
Były skierowane na tematykę
So
poszukiwania
there were
wody
some
na Marsie.
further
Nie wiedziano, czy
research
może
in order to explore whether there is water on Mars or any liquid form.
końcówka XX wieku.
So at the end of the 20th century, Mars Global Surveyor and Mars Express sent to Mars Express sending data until now, and we geologists can use this data.
Po prostu i jeszcze powiem, że Mars
Let
Express
me add that Mars Express is a probe, and we as CBK were involved in sending it. Some part of spectrometer was constructed in our center for space research. Orbiter sent in 2005 a probe equipped with many instruments. And what is there and what can be used by a geologist? We have a radar, Sharat.
radar penetruje
It's penetrating the surface of Mars up to a few kilometers. Thanks to that, we can see what is under the surface. We can explore its ice caps. Chrism, it's an infrared spectrometer, very useful as a tool in sense super short infrared signal. Thanks to that, we can carry out research of the geology of Mars. Camera CTX that has mapped the surface of Mars, and thanks to that it is clearly visible what are the geological formation on the surface of the planet. HiRISE camera, this is something that wasn't there before. A huge mirror telescope installed on the Mars orbiter with the aperture of 0.5 meter with resolution until by 25 centimeters. So we don't have such accurate pictures from Earth even. So here we have a great example of picture made by Viking and HiRISE. I don't know if you remember, especially the younger generations of our listeners, maybe older ones, remember that there used to be a story about a Martian face. A picture from Viking presented something that resembled a face. So there were some divagations about possible life on Mars, and this picture sent by HiRISE made it clear that it appeared to be a simple mount and that this face was just a play of light. Another picture made by a HiRISE camera, probably it's a volcanic tunnel or a water canal, as somebody might say. So it is difficult to get to the genesis of this, but quite probable it's a post-volcanic canal. So we can be sure that canals are there on the surface of Mars. So this is a kind of erosion made by water and Martian dunes. Apart from that, that's a quite accurate picture presenting dunes and some polygonal patterns, because these are the polar areas of Mars. So we can see some frost which is there due to low 6 HP Martian pressure. So it's not only ice which is there, or it's a kind of gas that became frost. And how do we know that these are dunes? Of course, geologists are looking for some Earth analogies. So if something is comparable to anything that we know from Earth, that's quite probable that they have the same history. And now, quite a popular picture made by some consecutive shots, the same place, Newton crater, where there were some seasonal patterns, and until now we don't know, we haven't discovered what is that exactly. So there was a hype about it and a rumor that maybe it's a sign of water being present on the planet of Mars, but we don't know yet. Then it has been analyzed whether what we can see this maybe it's just sand which is going down, not water. But until now, that we don't know yet, and we didn't manage to discover that. But it's quite probable that it's just sand leaving such a pattern. Okay, I'm within the time limit. So something more difficult that I'd like to present. For example, when it comes to these patterns, there were some special sulfates. Maybe these are some remainings of some other chemical substances. So thanks to spectrometer, infrared spectrometer, and the activity of Mars Express probe, such specters that we can see, this is a spectre of the great crater from Hellas Plancia, and it's comparable with a spectre from our library of well-known spectrums. And if we have some spectre from Mars and it is the same as one in our laboratory, we can predict that probably it's a sign that some specific mineral is present on the surface of Mars. It can be a hematite, it can be a goethite. So I compare it to sulfates. That's why I jumped to that conclusion. Another important thing is that CRISP spectrometer. It has different channels. Infrared is one of them. We divide them according to mathematical rules, and we arrive at some special indices. There are plenty of them. They're visible on the slide, and they serve to monitor the content of chlorophyll or water in plants, and based on that we can also detect and examine the level of different minerals in a rock. So it's not so simple to select and to mark each and every mineral. Sometimes we have to come up with another index. But thanks to that, we are still able to carry out geological research on Mars. It's very difficult. The scale shows from blue to red color what is the size, so the content of a given mineral on the surface of the planet. So if it's more red, it means that you have more of some mineral there. Here, as an example from Isis Planitia, on the northern part and hemisphere of Mars, we can see some patterns of we don't know what, some different shapes. There were some works devoted to interpretation of these forms. Maybe it's a remaining of a glacier, but these are probably volcanic formations. Until now, we don't know and we cannot be sure. I would say that it's more, these are volcanic formations similar to these visible on the surface of Iceland or Azores. Or the Canarian Islands. So, and such forms can be also found on our planet, but they are very popular on Mars. High-rise camera. Thanks to that, we can use stereo steams, so stereo couples, let's say, of pictures. So there are two similar pictures. Thanks to them, we can arrive at the 3D model of a geological form. And how do we know that it's a volcanic formation? We compare it to some analogical Earth formations. So, for example, to those in Iceland. We have some mysterious forms and formations. For many years, we were not able to answer the question, what is that? What are these dark shapes resembling some feathers or eyelashes even? Very often they are concentrated mostly on the northern polar area of Mars. So during some part of the year, CO2 is defrozen and it sublimates and it throws such dark stains. So we don't know it from Earth. Not everything is comparable. And now construction of geological maps. It's also based on pictures, because it's not possible to drill in to the Earth and take all samples in order to find out the geological age of Mars. So we do it based on the diversity of forms. So if we have a lot of craters, that means that the area is older. These maps are quite inaccurate, so if a man goes there and takes a sample, that will provide us with valuable information and that will increase the level of accuracy of my map. So I don't think I will be able to talk about rovers and pictures taken by them. Just to finish, there is some proof that some evidence that water is there on Mars. Curiosity presented oval-shaped rocks that may mean and might be a sign of water existing on Mars in a liquid form. Opportunity also that was active on Mars photographed such bubbles. Nobody knows what is that exactly, but we compare it to bubbles and to that are present in Utah on sandstones, and they are concretions that were formed by water penetrating sandstones, and these formations might be really large, and their dimension can be up to the diameter up to 1.5 meter. And just to end, Perseverance, Mars rover, a landscape of Mars, but probably, hopefully, Perseverance will manage to take some samples and they come back to Earth with another mission, allowing us to carry out research and have a hands-on experience. Thank you for your attention.
Thank you very much. Thank you very much. See you.
Ladies and gentlemen, this is the European Rover Challenge, so it's only proper that the last photo we saw was that of a rover. And what a nice introduction. After thousands of years of exploring our own planet, we still don't know so much. So just imagine how little we still know about Mars, given the fact that we haven't been there yet ourselves. We haven't drilled a major hole, but we are getting better and better photos from that planet. Ladies and gentlemen, next up, young constructors, designs of space devices. Sebastian Soberski and robotics team Grudziądz.
Dzień dobry Państwu. Witam serdecznie.
Hello, ladies and gentlemen. Welcome from this virtual studio of the Copernicus Planetarium in Grudziądz. Ladies and gentlemen, we meet because we're following the another edition of the European Rover Challenge, and during this competition, planetary competition, not international anymore. It's a planetary one. Teams compete, and it's worth knowing that not only students are interested, not only university students, but also high school students are interested in this topic, and they have their own machines built. In the observatory event organized almost for 50 years now, young constructors present their work. And some of these solutions, some of this work, some of their machines might one day go into the outer space. Interestingly, ladies and gentlemen, this planetarium is on the rooftop of the group of technical schools in Grudziądz, and the robotic team Grudziądz is a group active in that group of schools, and they are mentored by Marcin Jabłoński, who inspires these young people to prepare these machines, this spatial equipment. And today we'd like to focus on one of these projects, Flora Hub. But before we continue, Marcin Jabłoński will give us the gist of the project. Please tell us how the robotic team Grudziądz operates. Well, robotic team Grudziądz works within the group of technical schools, and Grudziądz has been active since September 2016. And as of today, we've been operating for 5 years under this name, and we've organized formalized robotics and mechatronics high school lessons, but not like they're organized in the technical high school of mechatronics, but going outside the standard curriculum. Well, we focus on such projects as building own PCB plates, designing and 3D printing, Arduino and Android design, autonomous mini sumo vehicles, construction, etc. That's how it all started. Our main project of the robotic team Grudziądz is the construction of autonomous rovers of the mini sumo class. Under this project, since 2015, our students have been heavily successful in Poland and internationally as well. In Poland, the closest competition from Grudziądz is the Bydgoszcz Polytechnic Technical University, the UTP competition, where every year we have been, one of the prize winners. Also, the Gdańsk Bitwy Robotów robot battles. Also, Krakow Łódź competitions are other ones that we compete in, but not only in Poland. We do not limit our activities to Poland, because since 2017 we've been active in the Czech Republic, capital city Prague, where a 2-day event is organized, and we've been really successful on that arena. And in the mini sumo category, every year we win at least a few awards. Also, in the freestyle robotic category, we won the jury's special award for the robotic arm. I think this is the most valuable prize we've won, because it was awarded by a college of professors of the Charles University in Prague and the Technical University of the German Heidelberg. I know that one of your flagship projects is Flora Hub. Please tell us a few sentences about this project by way of introduction before we hand over to the students who will present their work on their own. Well, Flora Hub is a project constituting a development of a project started in the Belgian Eurospace Center, where we were shown how to, in a simple way, to use Arduino and a few simple sensors, how it's possible to build a simple system for automated watering of plants. We went a step further, or even 10 steps further, and we constructed an absolutely autonomous habitat. In this habitat, plants are isolated from the external environment because they're closed in a black box. They are delivered water and all kinds of resources they require, air, as well as lighting. So it's a fully autonomous project in which plants grow absolutely independently of the parameters outside that black box. Another piece of innovation that we introduced was powering the system with PV panels and an accumulator. So the whole project can be fully isolated from external conditions, independently of what happens outside the plants grow. Really impressive. For those among you that have just joined us, let me tell you that this is not an academic school, it's a high school team of the group of technical high schools in Grudziądz. So now let us hand over to the high school students to talk to us about how they implemented Flora Hub. Hi, my name is Jakub Łukowski. I am a student of the technical school in Grudziądz, and I would like to talk to you about the Moon Habitat Flora Hub project created by Maciej Kowalski, Dawid Kwiatkowski, and Jakub Łąkowski, headed by Marcin Jabłoński. Slide 2. As you know, even the best designed space base cannot operate without people, which requires food. This is the solution being Flora Hub. So Flora Hub is an expansion of European Space Agency called Teach with Space Plants on Mars, build an automatic plant watering system. But our project is much more technically advanced. The project ESA only described an automatic system for watering soil-based plants. Slide 3 shows you a vision of the implementation of the project in Fusion 360, including a steering system, watering, temperature regulation, lighting regulation, and automated air circulation, and the whole system is based on hydroponic solutions. Slide 4. This is the Flora Hub in practice. Slide 5. We introduced hydroponic cultivation, soilless cultivation. So water and fertilizers are introduced into the water. Slide 6 shows you the lighting in the project, which includes artificial light, making it possible to for the plants to grow without natural light. Slide 7 shows you another element of the project, that is artificial air circulation. Slide 8 shows you the elements of power supply, which are a PV panel providing energy to an accumulator that provides energy for the Flora Hub. And the steering circuit is based on Arduino Mega, including sensors of humidity, lighting, temperature, and others, as well as switch off and switch on of individual elements. It is possible through a 3-channel system. Slide 10 is an additional element of Flora Hub, which is a mini lunar rover. Slide 11. The whole project was carried out with the support of 2 Grudziądz-based companies, which are the Grudziądz Industrial Park and Missile. This shows you face shields that were created under Robotic Team Grudziądz in combat against COVID-19. They were 3D printed mostly while the transparent elements were separately provided. Thank you very much for the Robotic Team Grudziądz and the Technical Schools Group. Welcome, ladies and gentlemen. My name is Maciej, and I would like to talk to you about Flora Hub. The habitat comprises the energy part, water part, the lighting part, heating part, and the air circulation part. Energy supply comprises an accumulator and a PV panel. Additionally, it's possible to connect an additional energy source to be used in places where external light is not sufficient. The steering circuit is based on Arduino Omega, which is the central element of the whole control system. There's autonomous control with all kinds of sensors. Based on information from the sensors, the central unit makes decisions about what to do. Also, it is possible to control the system manually using this panel, where values are introduced, and there's a monitor which shows what we are currently working on. The whole control system uses also transmitters and a central unit. Also, remote control is fully possible thanks to a Bluetooth system. The watering system, the watering part, is based on 2 containers of water. One contains water and the other water plus fertilizer. Pumps are turned on through transmitters at the right moment. They can be turned on and off and are controlled by a sensor. The lighting system in the habitat was created so that it's possible to make everything work in conditions without natural light. So it is so optimized that it creates the perfect conditions for the plants. There's also a heating mat, whose role is to control the temperature inside the black box, so that the conditions are optimal for the plants to grow. Additionally, there's an air circulation system, so that there's the right circulation in the whole black box. There's one system that pumps the air inside and the other evacuates the air. Thank you for your attention. Dawid Kwiatkowski is my name, and I am a student of the technical school in Grudziądz. I would like to talk to you about a complement of Flora Hub, and that is the Rover, lunar rover. It was designed based on Fusion 360, and it's been created using 3D print. It has a 6-wheel drive. The central plate was designed and built by us. The control system is based on Arduino Nano, plus there is a lithium-ion battery. There are sensors necessary for autonomous drive, but also it can be operated manually. Thank you for your attention.
Bardzo dziękuję za zaprezentowanie niezwykle interesującego.
Thank you very much for this fascinating presentation of such an interesting project. Ladies and gentlemen, it's worth adding on top on that the project was continued after the habitat was built. So that's not the end of the project. Apparently, one of the juries in AMSA was Agata Kołodziejczyk, PhD. Of the training center. So, as an award for the project, the students were invited to partake in a lunar space and an analog lunar station. So the students were closed in the station for 2 weeks, and since they have these technical abilities, they created a huge number of interesting projects, and some of them are of the devices created are still there in the lunar station. But that's a different story. Hopefully, one day we can talk to you about that. Maybe we can give you a brief of that stay in the lunar base. So thank you very much for your attention as of today, and I encourage you to look into the sky. But since the European Rover Challenge is taking place, now I encourage you not only to look at the sky, but also think about how to get there, how to get to the outer space. Thank you very much, and see you.
Quite a story from robotic team Grudziądz, you will agree. It's mind-boggling to see that every single thing that we take for granted here on Earth is such a challenge outside our planet, wherever we try to go. And hopefully one day we'll be able to, not so far from now, to host a guest who will bring an actual rock or a piece or a sample of the material from Mars. In the meantime, however, allow me to welcome our next guest in his presentation, The Geology of Mars, Michał Poros, Geonatura. Welcome, Michał.
Mam nadzieję, że mnie słychać głośno,
Hopefully you can
wyraźnie.
hear me loud and clear. Today I have this pleasure to present you Mars geology from the perspective not only of an expert, but somebody who's very passionate about geology and Mars. Of course, I specialize in geology locally in Kielce, in the Świętokrzyskie region. And my interest in the geology of outer space stems from one event. A few years ago, I had an opportunity to take part in a knowledge contest about the geology of the solar system, including Mars itself. And I can remember that while preparing for this contest, I had to read two great books. The first by Carl Sagan, A Blue Dot, which I strongly recommend to all of you. And the second one was the dissertation, a book by Jerry McSween. And it was a book From the Stardust to Planets. I remember that these two books, I was impressed by both of them, and I got interested in the topic from the position of a hobbyist. And today, during my presentation, I'd like to share my passion and to share some information that I managed to combine for the purpose of this presentation. Hopefully, my presentation will run smoothly. Okay, so first and foremost, what we can see on the night sky, the red planet. This red color was the reason why Mars was called red planet, and a name taken from the Greek mythology, and it was called Mars because it's a god of war. We have such, due to the refraction of light in the atmosphere, which is full of dust, we are under impression that Mars is red in color. This is something that we can see with an eye of a telescope, and this is something visible on a night sky. Here we can see conjunction of a few planets, including Mars. Of course, why with the development of telescopes and equipment, the image of Mars became more precise. The astronomers started to see more details on the surface of the planet. Usually the planet is hidden under a thick layer of dust, but there were some structures that started to be visible by means of a telescope. Of course, the initial observations that I'm going to present in a minute, they gave rise to some questions and theories that with time got verified. Today, after sending all missions and manned probes, orbiters circling around Mars, and rovers that were sent to the surface of the planet, now we know much more about the red planet. But it doesn't mean that we know everything. There is still a lot of questions that remain unanswered. So this slide summarizes some basic information about our planetary neighbor, from the fact that it's the fourth planet from the Sun. It has two moons, Phobos and Deimos. We have a longer year because of a longer orbit around Mars, and the structure, and similar day as well, and the structure. Of course, we're not able to explore explore the surface because we cannot carry out seismic or geological research on Mars, but we can make some assumption when it comes to the structure of the red planet. So, thanks to the recent observations, we already jumped to some conclusions about the structure. Of course, there are some analogies to Earth. The red planet has its nucleus. We have sulfur there. It has its mantle made of silicas. It has its crust. The crust is full of iron, which was subject to many different phenomena. That's why we have this red dust around the planet. Of course, there are some differences as well when it comes to the planet Earth. The hard nucleus of Earth is surrounded by liquid nucleus, and in case of Mars, quite probable that it's only hard nucleus there. A different diameter, a different volume. This is something that should be stressed in terms of the structure. But going back to the first observations of Mars and the first conclusions about the planet, it's worth reminding the personality of Giovanni Schiaparelli, an Italian researcher who at the end of the 19th century, with a telescope, by means of a telescope, he carried out some observations of Mars and created the first map. This map presented different rock formations and different land structures that he called canali from Italian. And based on that, further theories were created. And that all led to a conclusion that on Mars we have different structures and canals, which, according to some researchers, were artificial, made by some intelligent civilization. It's worth referring to Percival Lowell at the end of 19th century, American astronomer and passionate about astronomy. He referred to Schiaparelli observations, but he did them also on his own. And he jumped to a conclusion that we have to do, and we're dealing with some artificial structures made on Mars. Of course, it was under heated debate, and it stirred a lot of discussion among researchers. Now we know that there are no Martians on Mars, despite great Herbert George Wells' book, The War of Worlds, the civilization was presented in detail. So further astronomical observations and missions of probes being sent to Mars, they gave us some real picture of the planet. When it comes to data based on which we have some knowledge about geological structure of the red planet, of course, it should be stressed the role of the probe of unmanned probes should be stressed. They are sent from the end of the 60s, the beginning of 70s. They were successfully sent to the Mars orbit, and some rovers being sent as well. Viking probes and further missions related to rovers, such as Opportunity. They shed some new light on the topic of the structure of Mars. Another important source of information are meteorites, Martian meteorites that until now were found on Earth. Here another slide referring to Mars rovers and missions that were completed. And meteorites, Here I refer to Visitors film. So these are visitors from heaven, from the outer space that got to Earth, and they take different forms. Very often we refer to abbreviation SNC, to an acronym SNC. This acronym stands for the first letters of the names of meteorites. So we have shergotites, naklites, and chasinites. These are three names of meteorites that were defined as Martian meteorites. In the petrographic perspective, these are igneous rocks. In terms of their mineral content, they are quite similar to basalt. So it was an igneous rock of volcanic origin. Of course, we have similar rocks in Poland and in many other places all around the world, and there is some problem related to that. And when it comes to distinguishing Martian meteorites from other rocks, and here I wanted to quote a popular phone call that we got that, good morning, I've just found a piece of Mars. We get many such messages, but as soon as we get information where it was found or somebody brings a rock to us, very often it appears that we're dealing with basalt or with diabase or with other similar rocks, for example, some remainings from steel mills as well, which are quite popular here in Świętokrzyskie. So we want to cool down our researchers and tell them, explain that it's not what they think it was. But very often we send rocks to real experts. So very often that requires some further research to be able to tell. Majority of Martian meteorites, these are anachondrites, so they are very similar to basalt. So opinion whether a given piece of rock comes from Mars or not, that requires gases which is encapsulated inside to be examined. If the content of this gas is similar to a Martian atmosphere, we may be 100% sure that we found a rock from Mars, but very often such findings appear to be of Earthian or the origin, or they are some byproducts of steel works, as you can see in the picture below. So it is quite difficult to distinguish these Martian visitors from rocks which are popular on Earth. So this is one meteorite that was found on the North Pole, so a lot of them are found there because of the ice desert there, so it's easier to find something dark there, and it's easier than in parts of the planet with rich biodiversity and vegetation, or on the territories where basalts are popular. So then it becomes really difficult to distinguish. So this meteorite ALH840001 is one of the most popular findings when it comes to Martian meteorites, also because of the fact that there were some structures found there which were supposed to be of organic origin. So until now there is a heated debate whether these are organic structures or not. The majority of researchers are against this theory theory, but it doesn't mean that someday we would find some structures of organic origins, because we know now, after all research made and our analysis, that on Mars there is some water in form of ice, of course. Nevertheless, the water is there, and it's highly probable that in the past we had liquid water on Mars. So an evidence of that are different canals or sedimentary rocks which are taken or visible from the Mars rovers. So these are some pictures from the surface of Mars, and the view of rocks being present on the surface very often when watching these pictures, we are under impression that it resembles our desert, some erosion, which is also popular in some hostile desert environments. Of course, a lot of dust, which covers the majority of the Mars surface, and dunes, which are a mainstay on the surface of the planet. When it comes to Martian rocks, there are a lot of analogies to Earth. Here on this picture. One picture was taken on the surface of Mars, another one on Earth. This is a typical sedimentary rock, very popular on Earth. This is a conglomerate. And this is an evidence that there might be some processes that led to erosion of some parts, transport of them, and creation of this conglomerate. So there are some analogies related to rocks and processes that led to their formation. And we can make such assumptions based on this comparison of Martian rocks and Earth rocks. Of course, we are dealing with other structures which are visible on images. Here, for example, a highly interesting picture visible on the left, showing the structures resembling basalt pillars which are popular on Earth. Not to look too far, because we do not need any exotic areas. For example, near Złotoryja, Kaczawskie Mountains, you can observe very similar formations. Comparing to the pictures on the left, we can see that these structures are quite similar, and that's a clear evidence of volcanic processes taking place on Mars.
Jeżeli chodzi o takie formy
When it comes of the landscape
wynikające oczywiście w dużej mierze
they result from geology and from the climate.
zdjęcie Marsa,
If we take a look at the picture of Mars visible on the left, we can see some high-scale features, for example, Mariner's Valley.
Można powiedzieć takie tektoniczno-erozyjne, tektoniczne w tym
It's
sensie,
supposed to have some tectonic origin. So quite probable that tectonic plates, that the Mars crust has cracked just there, and there was some erosion present in the valley that made it even deeper. This is a system of canyons over 200 kilometers wide and over 8 kilometers deep. A large structure visible from our planet.
W górkę od niej wyżyna wulkaniczna, czy płaskowyż wulkaniczny Tarzis, z charakterystycznymi występami wulkanów, między innymi Pavonis Mons, który tam właśnie wśród tej trójcy występuje.
Which is one of the three structures,
widzimy na tej mapce załączonej
and further northwest,
z prawej strony.
you can see on the right map the highest volcano, Olympus Mons,
25 km, wulkan parczowy,
25 kilometers high. a shield volcano which has a fault on one side. Of course, these structures, these features are illustrated in form of maps, Olympus Mons, on both black and white pictures, and 3 volcanoes on Tarsis. Here, the essence of shield volcanoes, so magma being let out through a vent, and a drastic difference between shield volcanoes on Earth and, for example, on Mars, like Olympus Mons. The difference stems from the fact that we have intense tectonic movements on Earth, and the tectonic plate moves where magma should go out. And on Mars, there is no limit, and the magma is released without any obstruction. Of course, it is also due to lower gravity on Mars. But this moment of tectonic plates and these differences between atmosphere of Mars and Earth were decisive. Here are some forms related to landscape features, a lot of magma going out, volcanic planicies and plains, different erosion forms related to magma and creation of canals. Some impact craters, another important and popular feature of Mars. Very often they take different shapes, as if we had some mud being dispersed around. That's because the meteorite were hitting the surface, it melted water under the surface. That's why this water was spilled out around. That's why we have a difference between Mars and Moon. So my time is over, so I will just present you a few pictures. Martian dunes, different forms related to the activity of rivers. Thank you very much for your attention, and sorry for taking too much of your time.
Thank you very much, sir, for a very interesting presentation. As you can see, it's an endless story. Even if there are any of you in this room who didn't know anything about Mars before coming here, I'm sure by now you know a lot more. It's a big story. Next up in our agenda, where should the first base on Mars be built? It will be a presentation prepared by Alexandra, Gerald and Paweł, high school students, the winners of the Spaceship Cosmos Challenge. Competition will meet them shortly. See you soon.
Witam wszystkich serdecznie I dziękuję za przybycie.
Welcome, a warm welcome to everybody. My name is Gerard, and with my colleagues we will talk to you about what international space agencies have been wondering about, and the private sector as well. That is where the first fixed base on Mars should be built. But first of all, why do we want such a base to be built? Do we not have enough Earth-based issues? Well, such an endeavor would definitely bring a lot of benefits, impact impacting many other areas. Has there ever been life on Mars? Was there ever life on Mars? If so, that would contribute to our understanding life on Earth. Also, man can answer such questions much faster than rovers and other equipment, which is also expensive. The very different conditions on Mars, and meeting them would definitely speed up the development of technology that will be very useful on the Earth, like also inflammable material from like the ones that were created for space missions and are now used by firefighters on Earth. Also, functioning in such a different ambience generates the need for completely new services, creates new markets for a society on the large. Well, wonderful. So why not raise the funds as soon as possible and go to Mars as soon as possible? Well, there is a series of answers to this question. Above all, Mars's atmosphere has very low density compared to Earth's and has only 0.13% of oxygen. The pressure is around 170 times lower than Earth's, and the colonizers would find it difficult to breathe after landing, and the first seconds will be the last seconds of their life. This particular atmosphere and a lack of magnetosphere create another issue, that is, high-energy particles emitted by the sun reach the surface directly, and this means very high radiation, 4 times as high as safe doses for nuclear plant employees, which significantly raises the risk of cancers, for example. Also, the distance from the sun is significant issue. It's 230 million kilometers, and that's much further than the Earth, which means that only 60% of the sunlight compared to the Earth reaches the Mars, so temperatures are significantly lower. Instead of the average 15 Celsius on Earth, the average is negative 60 Celsius on Mars. But the things tend to be even worse due to, for example, sandstorms, which you can see on the photo, which tend to cover the whole globe for long months, covering the source of light and spreading dust, electric dust on the equipment and the colonizers. We all know that man cannot live without water. Unfortunately, there is no water on Mars. Unlike on the Earth, there are no big basins of water. So we'll have to use minerals that water can be generated from, and ice forms. And then making these resources available for man will be definitely a challenge for colonizers, for colonists. The map that you can see is land formation. Blue means lower areas, and red areas mean higher up. Significant stretches of land are much higher than the point of reference, the level of reference, and there is all kinds of craters and other. So what now? Well, definitely the issue of light on Mars would definitely be the main issue, if not for the other issues that I just raised. So the location of the base will be very important. What you can see is an algorithm where every arrow means an impact of the early element on the next one. There are 4 main issues that fundamentally impact the goals of the mission. Why these? Well, this is something that Ola will talk to you about in more detail. Yes, like Gerard just told you, there are four main issues that impact the choice of the location of the first Mars base. So, above all, it's water resources, for land formation, latitude, and scientific interest. Starting with the location on the globe, the latitude. Well, the temperature impacts how important or difficult it is to start and land. This also means that there will be more or less sunlight that can be used by PV panels. And the higher we go, the less sun there is. Additional issues mean differences of temperature. So the lower the temperature is, the more energy we need to use to heat up the base. So we are looking for a relatively warm place. This map shows you the average temperatures along the year and daytime. So it's between -125 and +20. The yellow and red areas are the warmest. So you can see that generally the middle areas in the North Hemisphere are the warmest. Then talking about water resources is very important. Moving to point 2, it's necessary for electrolysis and for daily functioning, because electrolysis is an element for fuel generation and for breathing. Now, free minerals can be used for that. Free minerals are those that can be used for water generation, and the map on the left shows you where these minerals are located on Mars. These are sulfur compounds, chloride compounds, and others. Most are on the eastern part around the around the equator, but they're not all available because some are covered with dust, which means that we cannot access information about them very easily. The other area is ice caps that are marked with black dots, and most are located around 30 degrees north and south. What are these caps? They are ice caps covered with minerals. This is what this looks like on the Earth on your right, and on the left, a bit less imaginative, on Mars. Another area is land formation. Importantly, the atmosphere of Mars is very thin, which means there is high radiation. So we want to avoid that, so we want to find a place where the atmosphere is as thick as possible. That will be rather low on the globe, because that's where we get the thickest atmosphere. So we're looking for a place that is rather low relatively in terms of land formation. This is also related to landing, because the thicker atmosphere, the easier it is to land. Additionally, this is related to the area. Landing area should be rather flat for the rovers to land rather easily. So we're also looking for caves, plateaus, plains, etc., and other land formations that can be used for the construction of a base, and that can also be protection against radiation. And then scientific interest. This is something we mentioned because this is the whole goal of the mission. We want to learn about Mars's astrobiology, about its geology, that is, what happened to Mars and what caused it to be as it is today, and what it looked like before. This will help us answer questions about the solar system. So, we talked about four main elements, and we go back to the algorithm that Gerard showed you. We talked about the first level of the algorithm. Now, what do we do to choose the best place on Mars? Paweł. Right, let's move to the core of this project. The four factors mentioned by Ola were what impacted our decision about the base's location. We picked 10 locations that were best suited. That's how we created based on those areas, we created a long list of 23 spots. They had to meet basic conditions. First, it needs to be possible to land there. The latitude has to be no more than 50 degrees, and other benefits, advantages of that place should be present. And we marked them between 0 to 5. We looked at water separately, looking at the free minerals and mineral caps, water caps, ice caps. 0 means a lack of resources, 3 means significant amounts, and 4 or 5 means significant wealth of such resources. 0 meant conditions that were close to making it impossible to carry out a mission. 3 means advantageous conditions, and 4 or 5 is reserved for really well-formed locations that include McLaughlin crater that you can see in the photos. We also marked a latitude, and we also talked about 4 to 5 points for those that were at the most at 20 degrees, and the highest rank went to around 10 degrees. McLaughlin is close to the highest mark, so we marked it at 3.5. And the last element is scientific interest, and here the key was different. Well, we used a procedure used by scientists for the location of Perseverance rover. Also, it included 0 to 5 marks, so we struck an average and assigned the marks to different locations. For example, in the case of McLaughlin, we can look into the crater as such, as well as the Morphalis Valley. You might have seen that McLaughlin crater is not an average place on the list, because the points it got was exceptionally high. But there's also another place that was the ranking very high. So these two went to the final. Why are these two places so attractive? Well, let's start with water availability. What you can see on this map is the location of free minerals. The wealth of these is significant in both locations. Here you can see a cross-cut of a cross-section of these places. In the case of Acidis Planitia, it is around 3.1 negative, and for McLaughlin it's almost 5 kilometers negative. The land formation is visible on the right, but remember that the proportions are not kept, because in the flat part the differences are only 80 meters on several kilometers, so they are very flat, and it's easy to operate using rovers. These are temperature maps. It shows that both locations are rather warm for Mars. Summing up, both places are very well suited, and picking any of these would be a very good decision. We are sure that they will be considered by space agencies and private companies. But there are particular areas where one is better than the other. So in the case of Acidis, we see that there are as many as 3 interesting facilities, objects, and in the case of McLaughlin, these are 2. On the other hand, McLaughlin wins in terms of access to water, because freed minerals are on the spot, unlike in the case of ICD's Planitia, where a transport system spanning several dozen kilometers has to be created. The height is better in the case of McLaughlin because there is a kilometer longer landing trajectory, while ICD's Planitia is better in terms of latitude. Remember that the height, might be good for landing, but bad for starting, for takeoff. So we decided not to choose any of these. They are both recommended by us, but maybe you saw one of these as more attractive. So we encourage you to partake in our questionnaire that's available under the QR code that you can now see on the screen. Now we are happy to answer your questions.
Prosimy.
Jaka jest jedna najważniejsza rzecz, którą chcielibyście przebadać naukowo w obu tych miejscach i co jest fajniejsze i ważniejsze?
Czyli pytanie, aby nasi odbiorcy usłyszeli.
The question is
W tych miejscach.
Zacznijmy może od krateru McLaughlin.
Let's start with McLaughlin crater. Interesting in terms of scientific interest is More Fallis. Even more interesting than McLaughlin as such. It's an old canal that was created by floods in the past. It is very rich in minerals that are created in the presence of water, and a potential wealth of astrobiological remains. Also covered with volcanic dust, they might have survived space radiation. So scientifically it's very interesting, and it has never been looked into by any rover. Well, in the case of McLaughlin as such, I would like to add that its big part is probably covered in volcanic ash. And, learning about the volcanic past of Mars would be very valuable geologically. Also, it's rich in lignites and other compounds that could carry signs of past life.
Bardzo.
Ja chciałem zapytać o temperaturę w obu tych
I'd
miejscach.
like to ask about temperature. As quoted in the presentation of both places, are these temperatures that are stable, fixed all year round? Or does it oscillate? Well, yes, the map generally related to daytime temperature, so it's daytime temperature, it's much lower at night. Also, it's an average struck, along the year, so depending on the season, it might vary significantly. We have 1 more minute. Any more questions? Well, collecting samples is already possible. The only issue is transporting them to the Earth. Anyone else in the last 30 seconds to ask a question? If not, thank you very much then. There is a question you can see. What is the distance between these two places? Is it possible to go to one and from there move to the other one? It's not rather possible. The distance is significant. It would be thousands of kilometers. So, taking into account our capabilities at this time, in the nearest future, I don't think it's possible unless we use the Mars Direct program, for example, and so that we first use, fuel-producing equipment in one location, then move to the other one, do the same thing. Then we could start creating a network of Mars bases, but it is impossible directly. to move from one to the other. It's very probable to visit both, but moving between them is very difficult because there's an area full of craters which is very difficult to operate in using a rover or any other vehicle, and the distances are very, very significant. But I'm quite convinced that we will visit both, especially since ICDs is already being looked into by Perseverance rover.
And that is very much deserved applause. Thank you very much, Gerald, Alexandra, Paweł. Fascinating, inspiring, and wonderfully optimistic. Thank you so much once again. Ladies and gentlemen, we've talked so much about the space, the surface of Mars, and the different opportunities and options as presented by our brave students. It's time that we actually visit the Mars yard built especially for this event outside the Kielce
with
University
competition judges and people
Technology.
behind the biggest space and robotics event in Europe. So I have with me right now Kasia Gajewska, one of the judges and one of the members of the science team who can answer a few questions about the scenes behind us. So first of all, Kasia, let me ask you, this Mars yard was very carefully designed specific for this event. Can you talk us through some of the key features that we see behind us?
Oh yeah, of course. We've been designing that for a few months when we were discussing that online with another jury team's members, and we actually focused on Elysium Planitia this year. So we have the big volcano. Of course, everything is scaled properly because we couldn't have done the same sizes and the same distances between the features, because otherwise it would be just empty plain place. So we have focused mostly on tectonic events here. So we have volcanoes. We also have impact events. So we have craters, and as you can see, the lava flows from the volcanoes. I hope you can see. So yeah, in general, I think that this year this place is much better designed than the last year one.
Okay. There's a lot of talk in planetary science about lava tubes that might be good places for human missions in the future. Are they featured here at all?
Oh yeah, of course, we've done that, and it's been pretty tough to do, but we've managed to somehow, I don't know, build it. I don't know how to say that in general, but yeah, we have lava tubes as well.
Okay, brilliant. So how closely does this really resemble the real features of the real planet Mars?
Oh yes, as I said, the scale is much smaller because the distances between the features in Elysium Planitia are much bigger. So here we're trying to collect everything and close it in a small space. For example, like Olympus Mons, it's much smaller here, but we are doing our best. So you could have seen that from the drone pictures. I mean, the team members obviously have noticed that. So yeah, we were trying to do our best to show all the features, different features, so we could have shown different geological processes in here. But I'm pretty proud of it, and I would say that it's pretty well built, and it reminds of Elysium Planitia if you see the pictures of Mars.
Okay, how about the soil? Because it is red behind us, and the red planet is red. Is this special soil that was selected for the Mars yard?
Oh yeah, of course. We've done the proper selection for that, and we are doing that every year. So we have one source where we get our red soil, I mean dolomites in general. And yeah, we are trying to show the redness of a red planet here as well.
Brilliant, brilliant. Now we see lots of features that you just explained. How did you build in challenges for the teams? How did you make it difficult for the teams to put the rover on the ground and do all the tasks? How difficult is it for them? How challenging is this Mars yard?
I mean, I'm just after finishing checking the reports from the pre-competition reports where they should have state their hypothesis, where they should interpret the Mars yard. So I've seen that there are a lot of challenges for them, which we didn't expect, to be honest. But for example, I don't know, the lava flows were pretty often described as glacier forms. So that was pretty surprising. There's one crater that was slided with a crosscut, and I don't think that any of the teams have described it properly, so I've seen that there are some difficulties. But in general, I was pretty surprised because almost all teams recognized the rootless cons, which was pretty amazing, and bravo for them. And yeah, I mean, I think that these are the most challenging features for them. From what I've seen from the pre-competition report, I hope that in after competition report, they will show us much better reports.
Okay, very well, thank you. Now, there are two competitions going on, not one. There's the on-site competition and there is the remote competition. Last year, everything was remote. Now we have the two challenges. Are the challenges the same for the teams? What are the differences and which challenges are the same for the two formats, if you like? And by the way, we see the remote Rover remotely driven from, I don't know exactly where at this moment, but that is remotely operated from somewhere around the world, right behind us here. So can you tell us a little bit about the differences between the two formats?
Yeah, so in general, they are pretty much the same. We're trying to do that, to be fair, to both challenges, let's say. But the remote, of course, is using only one rover. Every team is using the same rover, which is Leo rover, that you could have seen behind us. And they are using that from, yeah, as I said, all around the world. And the on-site teams are coming here with their rover, so this is the difference. And there were some other questions in in the science task. But in general, we were trying to do this as much similar as it was possible, but of course the maintenance task is kind of different because they are not using their arm, but the robotic arm that is prepared by I believe it's the university from Poznań, but I'm not really sure, so sorry if I'm mistaken now.
No, that's okay. We'll have a look at that later as well. We'll report from different locations around the Marjat, and hopefully we'll see the maintenance task at some point as well.
Yes, they are using just different stuff, but to do the same things, and the goal is the same, just to find something interesting here, to do the research, to analyze the place, and to confirm or just check their hypothesis, which they stated before the competition. So this is our thing.
Okay, thank you very much. Now, I do notice there's a big difference in size between the rovers. This one's very small. We also see ones that are, well, almost as big as Curiosity, big as a small car. So how is the terrain different from small rovers versus large rovers? Have you any idea?
How is it difficult for both of them, or how is? I mean, there are some spaces where Leo can cross with no problems, like the grabens, which were not recognized in our reports. So these are pretty tight. So the big rover will not pass by, and will need to check the other places, the spots to come to, I don't know, to down to the crater or something. But from what I've seen, Leo doesn't have a problem. We are kind of concerned if he can climb, like if it's pretty big angle for, I don't know, the volcano there. So yeah, I mean, I've seen that he doesn't have problems, and congrats. But I think that in general this place is designed for both, and they shouldn't have problems with access to any forms, because we were trying to do that, like keeping in mind that these are bigger rovers that weigh, I don't know, 50 kilograms, I believe. And there is a small rover which is like, I don't know, few kilograms. Yeah, it's there. So in general we were trying to do that so everyone could have access to each feature designed on the Marjat.
Right. Okay. Thank you very much. Let me ask you the last question, because I forgot in the beginning. Can you tell me a little bit about your role in this competition?
Okay. So before I was a member of the team, one that is taking part in the competition, and now I'm a jury. I'm checking, as I mentioned, the reports, like the pre-competition reports, post-competition reports, and in general, it took us like a year to design the whole area. So we're just meeting, talking, checking the places on Mars, checking how could it work in here in the small area where we needed to combine all the features and to stay like with the geological sense in here, because it still needs to make sense, and it needs to be like, they need to be able to explain what happens there. So it couldn't be like just random things. So we were designing that, we were checking the reports. We were checking the reports mostly, yeah, and trying to design something that they can map and they can explain, basically.
Okay, and it has to be realistic. And the reports you talk about are the reports of the 6 previous editions, because this is the 7th edition of the European Rover Challenge at the moment. So, and what is your role today? I mean, your badge says jury. What exactly does that mean?
Okay. So the teams are, they have to send us the reports, post competition reports, after up to 2 hours after finishing their riding here. So we were waiting for them. They are trying. We are trying to make them keep on time and everything. And basically, we also have workshops for children in there, so we are taking care of that as well. We are changing during the competition. We are changing the spots of this unplanned science mission that we've decided to make here. So they need to find something interesting, some interesting objects, like for example, meteorite or something. So we need to change places so the teams doesn't know how to reach to them, and they need to find them themselves.
Right. So how many judges or jury members are there today?
I believe it's Ania Łysiak as our team leader. There's me, there's Magda Baranowska, there's Piotr Król and Gabrysia Ligenza, so it's 5 of us today.
Okay, very good. I think we're reaching the end of the live broadcast from here, and we're switching over to back to the studio for the next talks. I would like to invite everyone to stay tuned in today, tomorrow and Sunday. Today is all about Mars. Well, every day will be about Mars, but in the conference, today is about Mars, tomorrow about the Moon, and the last day, also important, is about Earth. Keep following us on social media. We're on Twitter, Instagram, LinkedIn, Facebook, and of course the website roverchallenge.eu, where you can also find the live stream. Keep tagging us with hashtag ERC2021, and we'll be back with you at 2 o'clock Polish time. Thank you very much.
Quite a hectic space out there, you would have seen. Luckily, we are also enjoying some splendid weather here in Kielce today, which brings more and more people watching what's happening in our Mars yard, dedicated Mars yard. Next up, ladies and gentlemen, the first active seismic experiment on Mars to investigate mechanical properties of the shallow subsurface. Here to talk to you about Nienke Brinkman, ETH Zurich.
Do you hear me? Do you all hear me? Hello, thank you very much for the introduction. Today I will present an experiment that has been conducted on Mars outside the primary mission goals of the InSight mission. So most of you are probably aware or very familiar with this InSight mission, but for those of you that are not, I will provide all information you need to know to understand the InSight mission. The main focus of today is going to be the first active seismic experiment on Mars to investigate mechanical properties of the shallow subsurface. Throughout this presentation, I will explain how such an active seismic experiment works and how to obtain properties from the subsurface out of the acquired data. On the top, you see the names of the people that I worked closely with to obtain these results. During the Apollo missions on the Moon, 4 seismometers were placed on the lunar surface to record potential moonquakes and meteorite impacts. Moonquakes and meteorite impacts are so-called passive seismic sources. But since moonquakes and meteorite impacts cannot really be planned, astronauts also place dynamite on the surface of the moon to generate seismic signals. These type of self-made sources are called active seismic sources. And the main goal of the seismics during the Apollo missions was to investigate these passive sources and image the lunar interior using the active sources. But due to large noise level, it was difficult to produce models of the interior of the moon as we have of the Earth. So 40 years after the Apollo missions, still new insights on the interior of the moon are being found outside the Apollo mission scope. New results are still being generated. And these unplanned experiments can thus be very helpful to exploit the recorded data to its fullest extent. And as you already saw in the title of this talk, we will discuss results obtained from an unplanned experiment on Mars. So I will just give you a small outline of my talk, where I will first give a short update on the seismicity of Mars prior to the InSight mission. Then I will describe the main mission goals of the InSight mission. And after that, I describe the setup of this unplanned or opportunistic experiment to finally present some of the results that we obtained for this experiment. Before the InSight mission, multiple attempts were made to acquire more information about the seismicity of Mars. It actually already started before any space missions were launched to Mars. Theoretical models predicted that the seismicity level of Mars is in between that of the Earth and of the Moon. Then in 1976, the Viking missions landed on Mars, with the main goal to investigate life on Mars. Both landers had the seismometer on board. However, the seismometer from the Viking Lander 1 did not work properly, and the seismometer from Viking Lander 2 recorded mostly noise. Therefore, the seismicity of Mars was still quite a mystery. But after the Viking missions, the Mars Orbital Laser Altimeter, or in short, the MOLA, operated in Mars's orbit. And from radar data of the MOLA, a shaded relief map of Mars was available. And based on this map, researchers could identify faults on Mars. And from that, a rough estimate of the seismicity of Mars was done. Then on May 5th, 2018, the launch of the InSight mission took place. This mission is completely devoted to geophysics, and since the seismometers from the Viking missions were not as successful as hoped, this mission could be revolutionary. So on November 26, 2018, the InSight lander touched down successfully. And here on the image, you see a picture from the lander taken from orbit. And if you look closely, you can even see in white the seismometer that will be placed on the surface. Yeah, so that's the landing of InSight. So the two main scientific goals of the InSight mission are to understand formation and evolution processes on Mars, and to determine the level of tectonic activity on Mars using passive seismology. To achieve those goals, the InSight lander carried two main instruments along that were placed on the surface of Mars. And these instruments are devoted to investigate the main goals of the mission. So the first instrument is a heat probe, which is called the HP cubed. And the HP cubed consists of a probe that will hammer itself into the Martian subsurface to measure the heat flow at various depths in order to understand the Martian planetary heat flow. This hammering probe is called the MOL. And then the second instrument is a seismometer, which is called SEIS. And SEIS will listen to Mars in order to determine the interior structure of Mars, and of course to determine Mars's seismicity. Here you see two of the instruments still on the lander, but on December 18th of 2018, SEIS was deployed onto the surface of Mars, and in the image you see that the seismometer is covered with a white windshield. And then later, the HP cubed was placed on the surface of Mars on February 12th, 2019. Both the instruments are placed on the surface with the robotic arm of the inside lander and thus are very close to the lander. And here I will give a little bit more information about the instruments themselves. So as we saw in the previous slide, SAIS is protected by a windshield, so the white cover. And this is basically to avoid only wind measurements as happened during the Viking missions. So SAIS consists of 2 seismometers placed on a leveling system. And one of the seismometers is a very broad band sensor and one is a short period sensor. And that just says something about how sensitive they are to different frequencies. The HB-cubed instrument on the right-hand side consists of the support structure that is placed on the surface and a self-penetrating mole. And the support system and the mole are connected to each other via the science tether. Temperature sensors are attached to this tether, and these temperature sensors, they measure the heat flow. So SAIS on the left records the seismic signals, which is basically a super sensitive microphone listening to the echoes and cracking of Mars, as well as things like meteorite impacts. And the HB-cubed experiment measures the temperature at various depths. By creating a temperature profile, we can figure out the flow of the heat in Mars. However, once both of these 2 instruments are executing their individual experiments, we can investigate certain properties of the subsurface when we combine the measurements from both the instruments. So when the mole is hammering itself into the Martian ground, it produces seismic signals, which are recorded by the seismometer. And the characteristics of these signals, such as, for example, their travel speed, can provide us information about the subsurface material. You can compare this a little bit with when you knock on a wooden or a metal plate. So both materials, they sound different. And this is exactly what we are doing when we analyze these seismic signals. Okay, so let's dive a little deeper into how these signals work. The seismometer is continuously listening to Mars. The unplanned experiments start only when the mole is starting to hammer. So when the mole hits its hammer on the ground, it will generate a seismic signal. And the time that the hammer hits the ground is called the origin time of the source. And that's what you see here in blue. The generated seismic signal is now traveling inside Mars. So that's the black wiggle that you see. But it has not yet been seen by the seismometer. So therefore, on the recordings that you see here on the left, that's this black line, you only see a constant noise measurement. Because when the seismometer is not recording active or passive sources, the background noise of Mars is prominent on these recordings. So that is, that's why it's wiggling a little bit, but not a lot. So then the seismic wave travels a bit further, but what you see now is that the seismic wave is still not detected by the seismometer. So still we only see the background of the Martian noise. And now it starts to become a bit more interesting. As you see, the seismic wave has finally reached the seismometer, and you can see the signal on the recordings. Now in red, you see that we have picked a time, which we call the arrival time of the seismic wave, and that represents the time arrival of the seismic wave and how long it took to travel its travel path. Since we know the distance between the source and the receiver, we can determine how long the seismic wave took to travel, and thus we can calculate, for example, the wave speed of the seismic wave. And these wave speeds then gives us information about the subsurface. However, if we know just one wave speed from one source, we cannot determine the various layers in the ground. And if you look at the model on the right-hand side, so the colored model, you see that the Martian ground is not a homogeneous model. So it would be very helpful if we have more data points from various depths, for example, to obtain more detailed model of the Martian subsurface. So that's what you see, for example, when here we have the mole moving downwards, and we observe that the signal recorded by SEIS comes in later, which is due to, one, the fact that the travel path is longer, but also because the seismic wave is traveling through different material. So in the end, the data that we get on Earth is the data that is recorded by SEIS. And here you see a computer-generated example of data where the mole digged to more than 1 meter depth. And the model on the right represents, in this case, the Martian ground. And our goal is to retrieve as much as we can from this, from the original model. But how do we do that? Well, first, as I mentioned, we find the moment the wave arrives, the first wave arrives. So we end up with a travel time for each travel path. Now, if we do this for all the travel paths, we have a bunch of data points. And from these data points, we could reconstruct a model that represents the Martian subsurface. So we apply some so-called inversion techniques to find a model that fits our data. Using, for example, this fake data that I made on the left, I was able to reconstruct the subsurface in low resolution, as you see at the top. If you compare that model to the initial model, you see that we definitely miss some details, but the general structure is resolved. And how can we increase the resolution of the solutions? Yeah, we should add more data points, which is unfortunately going to be very difficult as we would need an extra lander. That is the main idea of our active seismic experiment. But now let's just go to the real Martian data that we have. So during the first hammer session that took place on Mars, the mole unfortunately got stuck. So instead of hammering to a target depth of 5 meters, it only digged until a depth of 30 centimeters. The reason for this was unknown for a while, but the main cause for this is believed to come from the insufficient friction. So the mole needs a certain amount of friction on the sides to dig itself into the ground. And also, as you see here on the left, the mole tilted also with around 20 degrees. To further investigate what had happened with the mole, the robotic arm of the lander carried the support structure away, as you can see here. And if you look closely, you can see that the mole is visible from the images. So it was clear that the mole did not dig very deep into the subsurface. And then a final attempt to help the mole to dig deeper was to push with the robotic arm on the top of the mole. Unfortunately, it still did not help, and we remained stuck at around 30 centimeters depth. So in the end, the position of the mole has stayed the same at the depth of around 30 centimeters and tilted with around 20 degrees towards the seismometer. So that you can see here in the image. The gray shape basically represents the mole. And this indeed does not provide us a detailed model of the shallow subsurface, but it can give us some information about one value that we have, because we only have one travel path, but we can determine some velocities from there. Not only did the mole get stuck at a very shallow depth, there were also some additional issues that made the data analysis extremely challenging here. So I quickly discussed them here. So first of all, the clocks of the HB cubed and the SEIS, they were not synchronized with each other. And this means that the origin time of each hammer hit was not directly projected onto the seismic data. So we needed to use the lander clock to synchronize the clocks with each other. Then secondly, the data received on Earth has a very low sampling rate, which means that you have very low resolution data. And as we saw in the unplanned experiment setup, the two instruments are very close to each other, and therefore the travel time of the seismic wave is expected to be extremely short. So if we want to have an accurate travel time, we need to have higher resolution data. Yeah, and therefore we designed an algorithm to recover high frequencies above the Nyquist frequency in order to pick the travel times to a higher resolution. So it helped to get a more higher resolution in the data. But to do this, we needed to pass the data through a different filter. So every time the mole started hammering, we needed to switch the filters inside the lander. And then finally the mole got stuck, and it was actually the main issue of the entire unplanned experiment. Then we come to the results, and we resolved the issues that's mentioned in the previous slide. But in the end, we were able to determine a bulk velocity of the first arriving phase, so which is around 120 meters per second. And this is very similar to a typical unconsolidated sand. So on Earth, you would see these very low velocities on very beachy sands. Sorry, sandy beaches. And we did also recognize later arriving phases in the data. And we were able to determine the velocities of these later arriving phases, which will be published very soon. Then it was very unfortunate that the mole got stuck, and we could not obtain the results that we initially wanted. However, based on how many issues we had with the data set, and due to the fact that it was an opportunistic experiment, we still got out some useful results. And these results we wouldn't have had if we didn't try to perform this unplanned experiment. And as I mentioned in the beginning of this talk, it was very convenient that the data from space will be used for years and years. So we probably can expect to obtain more from the InSight data than we currently have. Thank you very much for listening.
Thank you very much, Nienke. It's been great to have you with us. Unfortunately, we don't have much time for questions left. But once again, thank you for presenting to us here at ERC 2021. Ladies and gentlemen, that was Nienke Brinkmann, ETH Zurich. And now, Mission Control Systems in the European Space Agency and Ladies and gentlemen, we have a last-minute change in the program. We're having problems establishing the connection with our next speaker. Hence, we'll shift it slightly, and we'll have the behind the scenes of the European Rover Challenge with Szymon Dzwończyk, Leo Rover, Deputy Head of ERC Jury, and Anna Wosiak, Institute of Geological Sciences, Polish Academy of Sciences, and ERC Science. Hello there. Could you please kindly use those microphones on the table? If you need water, it's also there. How are you?
Very good, very good. Very busy.
Very busy. I would imagine hugely busy. It looks like a really complicated event to organize and launch. Tell us all about it.
Oh my, where can we start?
If it's possible in the first place.
Well, it should be possible. One of the things that we should be able to do is communicate clearly what we are doing, but it will be a very long story because we start our tasks a year before. So like literally after every ERC, we take about a week of a break, and then
only a week.
Yep.
Not much of a holiday after.
Nope. Nope. Then we need to start planning for all other things that we will be coming into the reality next year. So
Anna, let's get all the statistics out of the way. How big is the team? How big is the challenge?
So
like in numbers.
So well, the numbers are about 6 to 10 people, depending on how you count, because some people are more involved than others. This is the size of our science team, I mean. So only people that are focused on making sure that entire design of the Mars yard is appropriate, both from geological, scientific point of view, but also from the point of view of having a competition.
What do you mean by appropriate? It's obviously not accidental. It's a replicated version of an image, isn't it?
Exactly. Well, not only image. It's a replicated version of a true geological setting, and a very specific one. Every year we are replicating a location on Mars, a different location on Mars. So for example, last year it was the Jezero crater where Perseverance landed. This year we are focusing on Elysium, which is a volcanic region within Mars, and we are not copying the Mars surface one-to-one, because either it would be, flat and quite boring and boring looking, or it would be very, very complicated for rovers to do anything on them. So one of the main challenges is not to is to design everything that it looks good, because it needs to look good.
It does, and we also happen to have brilliant weather today. Hopefully tomorrow and the after as well.
Yeah, let's hope so. Yes. But it has to look good on pictures. It has to be appropriate from the point of view of having a rover competition, so that everybody can participate. So we have people that are less advanced, we have people that are more advanced, and everyone needs to be able to find something challenging and something easy for them to do. And also it needs to be appropriate from the geological point of view, because this is a part of scientific challenge.
I'm sure everyone has already found something challenging for them.
I hope so.
In this edition already. Szymon, tell us, what's your perspective on the behind-the-scenes perspective on this event?
Yeah, so actually, in our case, like I'm the head of the remote version of the competition, so something new that is only the second edition of this version. And
little wonder, given that we are sending signals now to Mars, 17 minutes later, we can fly a helicopter there, right?
Yeah. Then you have like everything.
So it's a scaled down version of a remote event.
Exactly. Yeah, so these are built on our like commercial product, because we are a commercial partner as well of this ERC. But the thing is that like we have so there are two actually ways to views on the preparation here, because first thing is what we do as the judges and as the partners and as the whole team who build and then prepare the whole environment for the teams, and second is that the teams actually tested their, at least in remote, they already almost been here. Like 3 times already on this like last year.
Almost been here.
Oh yeah, I'm saying almost, but remotely. Yeah. So they have like during this whole year they had 3 test drives. They needed to prepare some videos. They needed to prepare some documentation for that. So this was actually this whole year of like preparing to this challenge. So it's not only the thing that you see now, but these teams are really well prepared.
Szymon, but it's not just driving the rover on our Mars yard. So how much mathematics and coding is involved in the complexity of it?
Right.
Because just to handle the whole thing remotely, everyone could do that, let's say. But
not everyone.
Apparently it's much more complex. So what's the job? I mean, they look at it through the camera lens, right? Don't they?
Exactly. So if you imagine like how does it look from the perspective of like really low hanged camera, that's like the perspective is really different. Like you can really get lost on this Mars yard. It's huge. It's actually huge for these rovers, and so that's the first thing. And the second thing is that the teams need to prepare. Like they should prepare. They don't have to, but it's always advantageous to prepare some software for localization, for example, where they can actually localize themselves on this Mars yard if they get lost, and then if they want to reach the waypoints, like get the score, the actual score.
Essentially mathematical mapping of the entire area.
It's based on mapping.
Based
from
on what? Drone footage?
Stereo vision camera.
Okay.
There is stereo vision camera on the rover that provides them the depth image. And second thing is that we have like 15 AR tags on the terrain. They are called landmarks. So they can actually like based on that they actually know the location of these landmarks. So then they can actually like triangulate their position on the terrain.
Finally, some useful application for beacons, isn't it?
Yes, finally someone uses that. Yeah.
Well, just to clarify, they do get information about the Mars yard surface and the holes and the mountains, and also a lot of other information that they can get from the image before the competition itself. And this is how they plan their both the navigational task that is the important thing, but also the science task.
I haven't seen the Marsyard myself yet because I'm in this conference room from the very beginning, but I'm planning to definitely very soon.
Yay.
But looking at the way you smile, Anna, when talking about it, I'm sure you set a trap or two in this Marsyard so that at least the smaller rovers can fall into it directly.
More than one or two, actually.
Than one or two, I see.
And the judges can fall into the...
And the judges can fall into the
Yes,
trap.
they can, but they shouldn't.
Ladies and gentlemen, all of the health and safety procedures are duly observed. No worries here.
Exactly, yes.
Anything else you would like to share with us about the behind the scenes of organizing this event?
We are always...
Because you look wonderfully relaxed, both of you. You probably didn't sleep much over the last week, but still, you somehow managed.
Week? More than a week, believe me. No. We are very excited to be here because it's an amazing event. And what we would like to say is that if anyone would like to join our team, for science, especially, people that are doing some sciencey things. We are always yes, we want nerdy people. We are always happy to have some additional team members, it's a lot of work and a lot of challenging work and a lot of stress, but it's all worth it because it's wonderful.
And you have probably just coined the most user-friendly adjective about science I have ever come across, and that is doing sciencey things. So all of you doing sciencey things, this is a place for you, not only about education and awareness raising, but really fascinating, something that can be addictive in a non-biological sense, hopefully.
Well, considering how much time, effort, and thinking and stress we are devoting to this project, I think it is some kind of addiction, a good addiction, because a lot of wonderful things came up of that. But we are all crazy, so be aware.
Let me ask the two of you a really tricky question now. It may sound simple, but think about it for a moment at least. If you were to think about this entire effort, the team of people working, the building of the Marsyard, connecting with dozens of speakers from all agencies around the world, interviews, chats, preparation, juries, procedures, drafting all the documents that need to be drafted, surveyed, checked, etc. It's a huge effort. So my question is, if you were to identify the top 3 value-added items from organizing such a huge enterprise from your perspective. I mean, look at value in a very broad sense. What's the actual value that drives you to commit to such an extent to work on an event like this in Poland, especially?
So in case of values, I would say fun. So that's something that really brings our
stand-up comedy would have been easier in that case.
So I don't have any experience in that, but I have some experience in rovers, so maybe not.
So it's fun. The fun factor is number 1 for you.
So
or
that's
number 3.
that's the I would say even team building experience for the whole team of friends and people who you want to work with. And you have the opportunity to build something there. It's the same thing from the perspective of the judges and the teams as well. So in case of on-site teams, for example, where they build the rovers, they want to have something in common, right? So they want to have this goal and build something together with the friends. And we are doing the same actually as judges. We are doing the same. We are building this competition, we're building maybe somewhere the rules, which are seem boring, but then we are building the Marsyard, we're building the rovers, the setups, the things for the teams, and that's fun. Yeah.
Correct me if I'm wrong, Szymon, but in the past there was an instance where one of the rovers didn't reach its destination, and the rest of the teams was it at ERC or was it at another international rover event? You know what happened? Essentially, one rover didn't reach the destination. It was a big media story. And the other teams helped whatever spare parts they had to rebuild the rover. You must have heard this story. So that's the kind of team spirit we're talking about here. Even though people compete, they're essentially ready to help exchange ideas help solve problems.
So I've seen that from the other perspective, because like in the first edition of ERC I was the team, so I was like not only me, but I was the head of the Scorpio team from Wrocław University of Technology, and there is no such thing as like unfair advantages, etc. Like this, like teams tend to work together because it's already hard, and you want to know people, to learn about different approaches, and like get know the like there are parties after the challenge, right?
Mm-hmm.
So that's the same teams who normally take part in the competition and try to like fight each other.
Mm-hmm.
They're then partying like in one card.
Thank you very much, Simon. So it's really fun and team spirit for you. How about you, Anna?
Also possibility to teach engineers about geology and make geologists learn about engineering.
Wonderful. It's absolutely wonderful to have you here. Thank you for finding the time, despite the busy schedule, to share some of those stories with us today. Ladies and gentlemen.
Yeah, thank you as well.
Ladies and gentlemen, we'll come back to you shortly, in a short while. Ladies and gentlemen, it appears we are now ready with our next speaker. The title of the next keynote is Mission Control Systems in the European Space Agency and Planetary Robotic Missions. Maciej Prokopczyk, GMV, Innovating Solutions. It looks like we are almost ready. Bear patiently with us.
Dzień dobry, nazywam się Maciej Prokopczyk.
Good
Jestem
morning,
inżynierem
my name is
oprogramowania w
Maciej
firmie GMV
Prokopczyk
Innovating
and I'm
Solutions.
a
Chciałem zaprosić Państwa
software
na krótką prelekcję
engineer
dotyczącą
at
systemów kontroli
GMV
emisji.
Innovating. Let me invite you to my presentation about the mission control system and European Cosmic Agency.
Spotkanie zacznę od krótkiego przedstawienia firmy GMV.
Let me start with a short introduction of GMV Innovating Solutions, then I will concentrate on the ground systems and mission control systems. And I will present our newest systems and concentrate on the features of the planetary missions. Then I will present and finish by presenting the results of our work. As I've said, I will start with a short presentation about GMV Innovating Solutions. So our company is a Polish company owned by Global GMV Group. It has its chief registered office in Warsaw. It employs about 86 employees and is active in the cosmic sector. As a group, GMV is one of the European leaders in the cosmic sector, employing about 1,300 experts. There are many telecom operators using our systems as they are very popular. We provide software to communication antennas and telescopes. GMV is a supplier to cosmic industry customers. Our important customers are operators or communication satellites. GMV specializes in mission analytics, both software and ground systems, including space control systems. After this introduction, I will concentrate on how the ground segment operates. So it looks as follows. The satellite, which is on the orbit, sends out some telemetrics to the system. The products, payload of the mission, these are telecommunication details. Telecommands are sent from the ground and they control the satellite and instruct it about the missions to be fulfilled. Ground stations are connected to the main control system. This is the management systems. We have simulators to predict the satellite condition, for example. We have mission planning systems in order to fulfill the mission goals and the control of the status of the mission. Ground operation systems serve to monitor the condition of the satellite by extracting relevant parameters, to send telecommands to instruct given subsystems what to do, and to image telemetrics on displays and present data in graphic form, archive data, and register incidents. The mission control systems, thanks to universal satellite model, they can operate smoothly. They are an important element of the ground systems because they are connected with ground stations and simulators and process telemetrics and send generated plans. I'd like to present two systems which are used now. So EGOS CC and its next version. EGOS 2000 was for the first time in MSG mission in 2010. They operate under Linux and the customer interface in Java. We had some graphics presenting the main subsystems and functions. The most important subsystems are responsible for data transmission, incident servicing, data archiving, and imaging. Some screenshot presenting the system EGOS. So the user interface is developed in Eclipse ICP. It's to launch different process systems. On the right, we have SPACON application for monitoring and addition of telecommands and telemetrics. Then we have telecommands which are sent which are visible in the last column. The last image shows the programmable checks and commands. Let's have another slide. COS 2000 is quite old, so that's why we have developed its successor, the European Ground System Special GCC. Based on it, we have developed mission control system. The system is almost ready now, and it is to serve JUICE mission, which is coming. It is developed in Java, it has modular architecture, and it has 3 layers. The basic functionality can be used by different layers, and this is in common for all missions. It offers an archive to store data and is cooperating and interfaced with applications. This layer, the last layer, these are test tools for validation and verification with the whole system and its components. EGOCC uses graphic interface developed in Eclipse RCP. The application should be similar to EGOS 2000. It is a static image of satellite. We have a list of parameters and some system incidents on the right. We have the story of commands being sent. We can see that the visual form has developed. The rest is like in EGOS 2000. In the next part of my presentation, I will focus on, from the perspective of the mission control system, the applications look like. It's different for satellite missions and robotic and planetary missions, so the environment in which the object control is placed is very important. So when it comes to planetary missions, everything depends on the surface, whether this is Mars, Moon, or other object. So during satellite missions, events are quite predictable. The evaluation of control of the object is another thing. For some missions, telemetrics is not enough, and we need some produce of the mission, like images and exact location. Planetary mission characteristic is long planning, and satellite mission is based on information which is collected every day. So, for example, for planetary mission, in case of a failure, if something goes wrong, you cannot fulfill its goals. For satellite missions, some part of the satellite are autonomous. For rovers, we need video streaming, especially during telemanipulation, in order to evaluate the progress. Satellite, they don't require any specific devices, while rovers are controlled by joysticks, iPads, and so on, for pads, and so on and so forth. In S, we use 2 applications to control robotic experiments. The first one is MOE. which is based, which has some basic part and some additional features. It is used to control and steer robots applied on the ISS. It allows for monitoring experiment by observations of the condition of robot and operations made by it. It has an access to historical data and it can process the values of and images. It defines given commands. You can operate Rover in real time, and you can get the information about the status of the activity. Telemanipulation is possible only if the lag time is up to 5 seconds in terms of Earth-Moon missions. Here you can see how the rover control system looks like. The second one is the model of controlled objects located on the map. Other system that I would like to present, this is Ground Control Station.
Okay. Niestety nie zdążyłem pokazać wszystkiego.
Unfortunately, we didn't have time to show you
Ladies and gentlemen, Maciej Prokopczyk, GMV Innovating Solutions. Next up in our agenda, the close-up imager on the ExoMars rover, searching for morphological biosignatures on Mars. Tommaso Bontonali, Space Exploration Institute, CLUPI ExoMars. We should be able to connect shortly.
Can you hear me now?
Yes, one moment, please.
We already have the connection with Tommaso, ladies and gentlemen, starting now.
Okay, welcome everybody. So today I'm going to talk about the ExoMars mission, which is a joint program of the European Space Agency, ESA, and Roscosmos, the Russian Space Agency. And this mission has the very ambitious goal of possibly finding the first evidence for the existence of extraterrestrial life. And what is new about the ExoMars rover, with compared to other rovers of NASA that are already driving at the moment at the surface of Mars, is that the ExoMars rover will be equipped with a drill device that you see on the right image that is capable of collecting sample from the subsurface down to a depth of about a meter. And how I will explain you in more detail later during the talk, this is very important and is expected to increase our chances to possibly finding signs of life. So since several years now, I'm working to prepare for the ExoMars mission. And more precisely, I'm part of the science team and science validation manager at the Space Exploration Institute of Neuchâtel of one of the 9 instruments that will be on board of the ExoMars rover, which you see it on the right picture. The instrument is called CLUPI, which stands for Close-Up Imager, and is a high magnification camera that we often compare to the hand lens of the geologists that you can use in the field to examine the surface of rock sample and see their texture and possibly the presence of sedimentary structure. And in the next about 10 minutes, I will show you what we hope to photograph on Mars with this CLUPI instrument, and more generally, what is the approach that we will use, that the science team will use during the mission. So the ExoMars rover will be launched next year, in September probably, from the Cosmodrome of Baikonur in Kazakhstan, using a Proton rocket. Then the spacecraft in the carrier will take about 9 months, like the pregnancy of a baby, to reach Mars. And when the spacecraft will get close to the Martian atmosphere, there will be this very thrilling entry, descent, and landing phase. And initially, the landing module will be slowed down with a parachute. And then during the final phase, the descent will be controlled with some thrusters. Then there will be this so-called egression phase, during which the rover will deploy its solar panel. And then the rover will be ready to go down from the platform and start the exploration of the landing site. And the rover will be equipped with various scientific instruments. And you see here located on this movable drill box, the instrument I was talking about before, that will be used to take close-up images of the ground. And then some sample will be collected and analyzed within the rover with other instruments that will provide information about the mineralogy and the chemistry of the collected sample. And then all the data will be sent back to the Earth. Now I will show you where we expect to land and which sample we plan to analyze. So as you probably know, today at the surface, Mars is quite inhospitable to life. There is many reasons for that, but the main one is that the average temperature is very cold. It's about minus 60 degrees. And this prevents the accumulation of liquid water, which is considered an essential requirement for life as we know it. However, thanks to our general understanding of the evolution of the solar system and also to many morphological studies and orbital spectral analysis of the surface of Mars, we are quite confident that early in the history of Mars, in this period that has been called Noachian, it's very likely that there were ocean, that there was a lot of liquid water on Mars. And of course, we don't know if this rendering is correct, the size of this basin. There is a lot of thing that remains unknown. But thanks to the work and the finding that have been done by other NASA rover, like for example, the NASA rover Curiosity, we are really confident that there was time where there was liquid water flowing at the surface of Mars. And here I show you again a picture that have been shown also earlier this morning in one of the talks that beautifully show how similar some rock that are present of Mars are to rock that we can find on Earth in alluvial fan so close to a river, or when a river arrives to a lake or to an ocean. And you see that if someone could, for example, propose that there was not liquid water and that this morphology that you see were caused by lava flow, it's very, very difficult to explain the formation of these small pebbles, navigated pebbles, that instead are fully compatible with an environment in which you had like flowing water. So the idea is that during the ExoMars mission, and this is the same also for the other mission of NASA, we are not looking for living life at the surface of Mars, but we are instead trying to find fossil evidence for life that is preserved in sedimentary rock that formed a lot of billions of years ago, when likely there was water on Mars, and so there was an environment that was compatible with the existence of life. And if we assume that life evolved with the same rate in all the solar system, which of course we are not sure about that, our expectation on the type of rock that we may find in this sedimentary rock is based on what we find on Earth in sedimentary rock that have the same age of the one that we are going to find on Mars. And unfortunately, in rock that are from the Archean age, that are older than 3 billion of years, we only find fossil of very small unicellular microorganisms. Instead, more sophisticated and morphologically complex fossil of animals and other organisms appear only much, much later, during the last 500 billion of years. And here I show you an example of a thin section of a small slice of rock that contains microfossil that I've studied years ago. And you see the fossil would be these two darker spheres in the center of the image. And I'm sure that you agree with me that the morphology of this microfossil is way too simple to support or sustain an important finding like the existence of extraterrestrial life. In fact, it's very difficult to be sure that these are really microfossils just based on the morphology and not simply some bubble or some other feature that form through completely abiotic processes. And on top of the simple morphology, there is also some technical problem, because to see microfossil, you need to polish very well the rock and make a thin section, which is not feasible on board of the ExoMars rover. And moreover, even CLUPI, which is the instrument that has the highest spatial resolution on board of the rover, has a maximal resolution of about 7 micron per pixel, which is not sufficient to detect microfossils that instead have a size of only few microns. However, this problem of the simple morphology and small size of early life is at least in part mitigated by the fact that on Earth, microbes tend to live not alone, but together in what we call microbial mud. And there are some places on Earth in which there are unusual conditions, and it's possible to see and study this microbial mud. And in the last year, I did a lot of research in the Sabkhas of Qatar that you see here in this background, that are very unusual evaporitic environment, that are fully colonized by microbial mud, and where we think that the environment is analog or similar to the landscape of the early Earth and possibly even to early Mars. And you see here that all the ground is covered by this very slimy microbial mud that is forming a centimeter thick layer. And you see here different color, green, the pink, and the black that correspond to the presence of millions of different microorganisms. And these microorganisms interact with the sedimentological processes, and sometimes they induce themselves the formation of some mineral. So you see here, this is like an image of a slice of this microbial mat tilted. And you see all these light gray layers. These are autogenic carbonates, mineral that are produced in response to the microbial activity that is present in this microbial mat. And so this interaction between microbes and mineral create or lead to the formation of some very unusual sedimentary rock that have this unusual laminated habit, or sometimes you have this unusual fenestre. And this type of sedimentary rock, they can be preserved, they can be fully lithified and transformed into a solid rock, like you see here, that is known as a stromatolite, or more generally, a microbial-induced sedimentary structure. And this is another example, so again, from a SAPCA of Qatar, where you see some microbial mat that have this very unusual polygonal, with a domed ring morphology. And so this, on the left, is the living microbial mat, and the right is like an outcrop in which we have found what we have interpreted as the fossil equivalent of this living microbial mat. And the beauty of these stromatolites and microbial-induced sedimentary structure is that on Earth, they are found in very ancient rocks, so in rock that have broadly the same age of the rock that we will find at Oxyaplanum, which is the landing site of the ExoMars rover. So the idea is that we are not hoping to find a fossil that is morphologically complex like the one of the dinosaur. We cannot exclude that there are fossils of microbes, but the rover is not equipped to find and see them. But it's possible, if they're there, that we will find some structures, some microbial-induced sedimentary structure that are similar to the one that we see on Earth in early Archean rocks. And here it's very, very important for me to clarify that if we should find something like that, it will not be proposed as a conclusive evidence for the existence of extraterrestrial life, because as it is the case with microfossil, the morphology of these stromatolites is too simple to be a strong conclusive evidence for life. Something like that could also form by coincidence through some completely abiotic processes. But finding something like that would be an excellent starting point to then perform additional mineralogical and geochemical analysis with all the other instruments of the rover, and in particular to detect biomarkers. And to do this type of analysis and to successfully detect a biomarker, it's very important to collect the sample from the subsurface, because at the surface, due to the intense UV radiation and also due to the chemistry of the Martian atmosphere, this biomarker with the time tend to be broken into pieces and they lose their complexity and their information. And a biomarker, in a way, can be seen as a fossil, so is a biomolecule that was produced through a biological process, and show a complexity that is not possible to achieve through an abiotic reaction. And then with the time, this biomolecule degrade, exactly like is the case with a fossil of a dinosaur, but they still preserve a complexity that allows us to confidently conclude that they were formed through a biological process, which is not the case. So you see, for example, these stromatolites as a complexity that is less compelling than the one of the structure of the biomarker. So the best possible scenario for us would be that of finding a rock that we can interpret as a putative morphological biosignature that we will see with the CLUPI instrument. And then we will do additional analysis. We will take a sample from the subsurface of the same formation, and we will hopefully find biomarker that will allow us to conclude that we are not alone in the universe. Thank you.
Ladies and gentlemen, that was Tommaso Bontonari, Space Exploration Institute. And now we proceed to behind the scenes of the ExoMars project, an interview with Thales Alenia space engineer Andrea Merlo, interviewed by Łukasz Wilczyński. Enjoy.
So, Andrea, what was the biggest challenge from an engineering point of view to be able to integrate and test Rover's core system and then assemble all the instruments and systems which will help scientists to collect samples and take pictures?
Well, making a satellite usually is already a very difficult task. If we target a new planet, as we are doing now with Mars, it's even more difficult because we are building something on Earth, testing it on Earth, but we have to prove that it works also on Mars. So it was quite a difficult challenge. So because of temperatures, because of different gravity, because of several reasons. But I think the biggest challenge we have to face is that with the Rosalind Franklin rover, we are gonna seek for life on Mars. So we have to ensure that we don't bring life with us. So all the assembly process, especially in the internal part of the body of the rover, so the one that will be in contact with the sample and aiming to really understand if the life was or is on Mars, was very, 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 very difficult. So we had to follow a process, and everything was mounted and assembled in a glove box. So quite a difficult task.
Yeah, and I want to mention that on the beginning of the year, the clean rooms in Thales Alenia Space Italy in Torino simultaneously hosted 3 versions of ESA ExoMars rover: the flight rover, the Rosalind Franklin, the ground test model, the GTM, and the structural test model STM. So what's the procedure of testing these 3 models and what information you gain after testing each of them?
Well, achieving qualification and acceptance of a satellite is a very long process. So we usually need a set of models to prove that we build something that can work, in this case for Mars, and then prove that the flight model we did is ready to be launched and to work on Mars. So the process is made in several steps. The first model we built are usually model like numerical software verification facilities or avionic test benches, so what is called a flat sat configuration, so all the units that are on a bench. In parallel, we start with a structural thermal model, STM, that is quite pretty because it looks like the Flight 1, so it is representative of mass properties and thermal properties, and that one is subject to a test campaign for all the mechanical and thermal parts to prove that we are ready from the mechanical and thermal perspective. Then, usually, each of the units is subject to a long qualification through a qualification model. The assembly of all the qualification model is the ground test model. So the Earth twin of the flight model is the ground test model that is used actually to prove the operation and perform end-to-end testing. The flight model cannot be subject to the full qualification, otherwise we would send it in a end-of-life condition. So it is just subject to an acceptance testing in all the environment, thermal, EMC, electromagnetic compatibility, and functional, but it's not stressed much. So it's we try to preserve it as much as we could.
You mentioned that this GTM is Earth twin for the counterpart on Mars. Could you please explain how it will work when the flight model of Rosalind Franklin will be already on Mars and its Earth twin here on Earth, and will be observed by engineers in rover operations control in Torino? And what will happen when these two rovers will start, I don't know, working together? How it will work during the ExoMars mission exactly?
So, as of today, we are preparing all operation using this Earth twin in a representative facility. So we are already rehearsing operation today, so that we will be ready for the real ops. Then, during the real ops, we will be capable through the ground test model to perform all the difficult operation or the contingency operation. So we will, in case we will be in a difficult condition, if you think to the for example, to the American rovers when they get buried on the sand, we will be capable to reproduce the same exact condition on Earth and test it in a facility before endangering the flight model. So it's quite a big advancement with respect to every other satellite where everything is simulated on ground. In this case, we have a real Earth twin offloaded of 2/3 of the mass, so that we are sure to recreate exactly the same conditions.
I see. I have also a question regarding your piece of advice to young engineers, to young scientists that are already stepping in the space sector. What kind of advice can you give them for those who are inspired by the space sector and want to go into?
Yeah. Of course, it is one of the coolest sector you can work in, because every mission is a completely new challenge. So I'm not, I would say, experienced enough to speak about tens of projects, but at least I saw 3 projects on 3 different environments, and every time we started almost from scratch. So it was very, very, very interesting. And then we usually produce unique things. So it's an incredible job, this one. So I would advise everybody to join the space sector.
And I heard, as a ERC director, I heard that there is also a success story of one of our teams joining Thales Alenia Space here over there in Torino. Is that correct?
Which one? Sorry.
Yeah.
Team Diana, you are right. Yes, you are completely right. Yeah, we are currently having some iteration with them. We are providing them some the facility we have here and a bit of consultancy. So I'm sure it's a very interesting job for them. It's a big opportunity for them, and it is also a big opportunity for us, because dealing with young people is usually the way to move on, to go forward and not step backward.
Thank you very much, Andrea. Thank you very much for your precious time. I'm very happy that you find some time for us, because I know that it's a lot of happening in ExoMars right now, everywhere on the planet. So once again, thank you very much.
You're welcome.
2, 5, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0.
Thank you, Andrea. Thank you, Łukasz. Ladies and gentlemen, the next item on our agenda poses the question: what might our life on Mars look like? Cold, hungry, dark, extremely unfriendly, or are we thinking about something else entirely. Here to talk to you about it, Leszek Orzechowski, architect of Space is More. Hello, Leszek. Our stage is yours. Enjoy.
Oh, thank you. So, yeah, we can see my presentation. Great. My name is Leszek Orzechowski, that was already mentioned. I was a team leader for Team Twardowski. We won second prize during Mars Colony Prize in 2019, showing our idea how future Martian colony could look like. Well, I guess will not die, at least we hope we will not die, and I will show you that this life could be, in fact, quite bearable. But first, before we start living on Mars, we need to find the exact location where our colony could be located, and we had the whole planet to choose from, and there was a lot of people involved in that project. So I am a space architect, but there was the group of almost 20 individuals, engineers, physicists, chemists, and, well, sociologists and lawyers as well, because we wanted to show not only the technical aspects of living on Mars, but also those social aspects as well. And I hope I will manage to do that in this 18 minutes. If not, remember that you can meet us also if you are here on site of European Rover Challenge, somewhere in the exhibitor venue. We can answer your questions. But now let's find our future home on Mars. So location. Location is the most important thing when you are trying to locate your colony, your city. And as I mentioned, we had the whole Mars to choose from. There was no restrictions where we can locate our colony, so that had to be some kind of a quantifiable process. We decided not to locate our base anywhere near the polar regions due to, well, orbital mechanic restrictions. Being as close to the equator as possible makes us easier to take take off from Mars. So we already scaled down on our landing site at this point. Then we understood that we don't want to locate our base anywhere, like any high altitude. Because also it's extremely difficult to land on Mars, and we need as dense atmosphere as possible, and as low landing spot as possible to lose some velocity when we are landing. So no highlands. Then we're scouting for resources, and we are looking for hydrate minerals that we could get some maybe water from. What do we have there? Olivines. What we have here? Pyroxenes and ferric oxide. So obviously, the red planet is called a red planet because there's a lot of rust there. So there's a lot of ferric oxides there. But we wanted to choose a place where all of those minerals are abundant. So we narrowed down to this region that is not abundant, it has an abundance of those minerals, also because it has the greatest geological variety on Mars. So this is an intersection of many different geological formations from different forming events in Mars history. At least this is what I understand, and the Mars geologist is looking at me right now, so I hope I am not messing this up. So we were able to narrow down our location even more, and we choose the region called Isidis with 2 possible landing sites. And there was this Jezero crater. Maybe you already know what is inside the Jezero crater. Back then in 2018, when we were designing and choosing the location for our colony, well, nothing. There was no mission plan for the Jezero crater. And when we decided to put our colony in the Jezero crater, we looked closer to this site. We noticed this wonderful, unusual structure that geologists call it an ancient river delta. But we figured out that this crater is low enough for us to, and has a flat surface for us to find a right landing site. But also, this formation would allow us to go to the highlands and find some minerals and other resources that could be helpful. So this ancient river delta is where we decided to locate our colony. And only a few months later, NASA announced that it's also the landing location for Perseverance Mars rover. So we did the same homework using NASA data, and well, the rest is history. Like probably they already knew where they are landing, but we had great luck, or we did a very good job. So we were very interested in analyzing the topography, or how this terrain is formed, because when you want to build your house on Earth, you are looking on the where your sun sets, or how much hours of sunlight you can get throughout the day or throughout the year. On Mars, we wanted to do the same thing, but the opposite. We wanted to locate our colony in solar shade, so we are least exposed to direct solar radiation. So we did the exact opposite of what we would do on Earth. And we took the data from a HiRISE mission, analyzed it in 3D, and choosing the best location that is least exposed to direct sunlight throughout the year. And this is where we located our colony. Can we see it? I guess so. It's here. It's on the northern slope of this ancient river delta. In a close proximity, around like 5 kilometers away from the from our colony, we located a spaceport. Safety precaution, probably like now landing technologies and are getting better and better. And in fact, Perseverance rover landed exactly in the same spot as our spaceport, so that's also cool stuff. And now we can start talking about architecture and how it could look like. You can see that we were supposed to propose some kind of timeline how this colony could grow, but the most important part is how it looks like in the very end. So obviously Rome was not built within a day. The same goes with a Martian colony, and I will skip that since I really would like to show you how the colony works. So here you can see, okay, not this one. Here you can see the master plan of 6 modules that we called biomes, and this is the only place where your living quarters are. All the functions that are needed for the colony to, like for colonies to live, and this whole other part that is at the base of this hill is our factory that produces everything that colony needs. So you can see the ratio of the amount of buildings you need, or the number of buildings you need to support 1,000 people on Mars, and you can see also how much space they need to survive. So with this section, it's also important to notice that I already mentioned that we are shielded from the direct sunlight, but we still needed some sunlight for us to have some daylight inside our modules, and also for plants to grow. So we are locating array of mirrors on the other side of this delta to reflect the sunlight directly into the living units, but without radiation. So the cross section through the living module. In the module is designed for 200 colonists, and you can already see that it's really similar to some kind of a shopping mall, because we have this gallery where on very top there are your living quarters, and when you go down you can see other functions like gastronomy, like public spaces, like gym, but also you are able to see this Jezero crater by yourself. So you're both shielded from the sun, from direct sunlight, but here you can see a place where you live, so you can really feel like you are living on Mars and not underground. What is extremely important here that this is where we also located our fruit production. So we are taking advantage of this reflected sunlight that will help our plants to grow. And also, this is where we located our tanks with water, but in those tanks, marine life or river life will be grown and harvested. So this is exactly where we take our food from. But water is also very good shielding for the radiation. So this is yet another solution for us to shield our colonies from harmful radiation. So designing a habitat in a certain way can have multiple different advantages. When you look closely to those windows, let's say, they have shutters, so we can close them during any dust storms. But also you can see that there are some exits or like small holes. This is and our habitat is not entirely closed off from the environment. In fact, it exchanges gases between outside and inside. So this is an intake for MOXIE equipment that now is working on Mars on Perseverance rover. It's a science experiment to produce breathable atmosphere using only Martian atmosphere. And we could take this atmosphere from Mars directly through our facade and put it in our living modules, but also it can go the other way around. Okay, so this is like a simple setup how this place is organized. On the very top, your living quarters and functions at the very top with public spaces. And this is how this could look like. So more like some kind of a shopping mall, a big space where you don't feel that you are, well, contained in a small can, a place where maybe a colony could, well, thrive and develop. But then we have this all other part, how to get all the resources for them. And here you can see a small cross-section of our production system that I will go into better detail in a second. But first we need to discuss from where we are getting energy. And we are getting energy from liquid thorium reactors. So it's a nuclear reactor working with molten salts. That the technology that is now developed is under development on Earth, but also in the landing site. On the landing site, there is some thorium to be used. And using this technology, I guess, if you visit Sat Revolution booth somewhere in the exhibition venue, there's our friend Sławomir, and he designed all of that, so he can answer questions about nuclear reactors. Once again, I'm a simple architect. But I guess I can get you some basics. We are also using some kilopower energy grid, something that is also developed by NASA, so small nuclear reactors as well, but and some solar panels. But we need more than one energy source in order to feel safe and to produce enough energy for our colony. What is important about using the thorium reactor, there is always an abundance of heat that we can redirect to some production processes or into the colony itself. This is the visualization of this reactor, so it's a lot more. So it's a lot smaller than the things you can see now in use, and this is exactly how our future on Earth can look like. Those reactors are also extremely safe, or are said to be extremely safe. And having a nuclear reactor there, it has also very important use, because we can produce some radioactive materials that can go to our medical purposes, to our drugs, to our medicine. And this is exactly what the only working Polish nuclear reactor is doing, producing material for medical purposes. Yeah, I I have 5 more minutes, and there's still a lot to tell you, because we also need atmosphere and we need water. We are getting atmosphere from also 3 different sources. I need to turn to make it to see what we have here. So we can use subatomic reactors to use CO2 from Martian atmosphere to create our rocket fuel, so methane and oxygen. But also we can use this oxygen for use inside our colony. Life support system, so environmental control and life support system. So all our plants and our algae can produce oxygen and well, take care of CO2 as well. Yeah, there's a lot of atmosphere that we can get from manufacturing itself. Water. I was talking about producing water with my friend a minute ago, so I still need to remember what's there. But first of all, Martian regolith has some small amount of water, like very traces in every kilogram. So you can get some water from that. So during our manufacture processes, we can always get some water from each kilogram of regolith we are processing. But also we can use melt pools. So there are some underground reservoirs of ice on Mars. We can drill into those reservoirs, get some heat there, and pump water. That's some of the proposals how you can get water on Mars. And now we are getting to how we are building stuff. So open pit mines. We need to get a lot of regolith to our main chute or place where we can sort it and process it, because from regolith we can get a lot of different minerals and okay, how's that work? Oh yeah, so we can get aluminum, we can get iron, we can get ceramics, and many more products that we can create. So silicons, we can even create some plastics, and all of that after this segregation can go to our R&D processes, where we can create small prefabricates when we can prototype new technologies. But we need to create architecture for people. So it's all about creating this Martian concrete that can create big, sturdy elements for people to feel safe in. But also it's all about creating all your rovers or your robots, but also your clothes, your everyday items that you can use. So there's a lot of production that needs to be made in 3 distinct halls that are either for creating prefabricates, then putting them together. Then there's also R&D that can happen when you want to design something new. And in the end, it all goes to those warehouses and can be distributed in these living modules. This is how R&D production looks like. In fact, we were so happy with this visual that our friend Dominic, that is sitting there, is also here, and Sławomir, that was designing the nuclear reactor, is also here. So we're super happy to put ourselves in there. And there's still the whole life support system. So how we were producing our food. And this is the part that you already seen, but in the close-up. So this is near our windows in the living module, where we can produce plants using aeroponics or hydroponics. So we are not using soil, but rather water with nutrients that are dissolved there. And the whole thing about designing that such system is that it needs to be closed loop. So there is the whole. I already mentioned about how we are producing atmosphere, but also there's a lot of we can create from biomass, from not only our food but our clothes, and well, some drugs and alcohol as well, because why not? We need really to produce everything, including drugs. And I have 20 seconds. How I will do that? I know what I will do. I will show you the whole visual of that, and I will show you that, for example, here, this whole system was designed by Natalka and Joanna. Joanna is now working at the European Space Agency for Melissa project, and she is designing this whole biological circulation system exactly the same as we proposed in Twardowski, because this is how the colony is named. Healthcare. We need quickly to go to one last slide, and we will be extremely happy. And I can leave you with that. Because now I could discuss to you how our society is organized, and we thought, well, we should all be specialists, so we can be in guilds. So someone is responsible for life support system, someone is a scientist, someone is an engineer, someone is in logistics, someone is administrative. But we can, or these people can, if there is like only 1,000 of them, they can make decisions on their own. So they can directly decide how the colony should progress. So this is direct democracy with this guild system that, well, if some topic is more focused on life support system, maybe people that are skilled in that area should, in fact, have vote that is stronger. So maybe 2, 3, 4 votes. And this is what we thought is some kind of technocracy, but is it really? We are only engineers, and maybe we're too utopian for proposing the egalitarian society on Mars. Maybe it will be a lot more difficult. There's also yeah, I can leave you with those few shots how this life there could look like. And for all other things, I can invite you to our tent. I will tell you more about potential Martian society. And right now, there is an analog mission happening in our analog habitat, so our simulated Mars laboratory. 6 people are now isolated for 2 weeks in our laboratory, and they're doing a simulation of a moon mission. You can go there, you can see what they're doing right now, and you can answer your questions how our first Moon and Mars mission will look like. We are in the exhibition venue, somewhere there. You can see what our analog astronauts are doing right now, and we can even talk to them later today, maybe in several minutes. So thank you very much. And for the questions, you can find me there. Thank you very much.
To catch you somewhere near the exhibition area.
You know where to find me.
I still remember the way you started the presentation. You said, after all, life can be quite bearable on Mars. So I could imagine already the commercial going like this, come to Mars, life is quite bearable there.
The trip, it will be far worse. So get to Mars, it will be better.
So it's getting worse and worse, ladies and gentlemen. Thank you very much. And now we'll go straight to the next presentation in the Art and Tech section, The Road to the Largest Astrophotography of the Milky Way in the World. This is the lecture by Michał Ostaszewski. Michał is joining me on the stage now. Hello, Michał.
Hello, everybody.
We're starting in a few seconds.
Ladies and gentlemen, welcome on board the Galaxy project. Fasten your seatbelts, we're going to Namibia. We flew there with the vision of creating the largest photo of the Milky Way in the world. A photo that will change your perception of our galaxy. We experienced and documented an adventure full of challenges, wonderful landscapes and amazing night scenery. It is a view that most people will not have a chance to admire due to light pollution, weather and geographic location. From several thousand photos taken in a remote wilderness, with a total exposure time of over 200 hours, combined with weeks of calculations and months in complicated post-production, a work of art will be created that the world has not yet seen before. The result will not only be the largest commercial photo of the Milky Way, but will also become the basis for an ultra-accurate sky map and animation of star movement, based on the most accurate survey of the sky from the Gaia space mission.
Dzień dobry Państwu, nazywam się Michał
Welcome, ladies
Staszewski.
and gentlemen. My name is Michał Staszewski and I specialized in astrophotography. For a dozen of minutes I'm going to talk about this fascinating journey that I followed together with Marcin Kuciński, who has joined me today on the stage. So, creation of the largest commercial Milky Way image is a huge challenge. It's a project that I've been in for several months since the beginning of this year, and I think that it will take me another few months in order to get to the point to be able to show the picture and to be able to move forward with this project. But starting from the very start, what is the idea behind this project, and what does it come from, and why astrophotography became my work and my profession? I have to say that I got interested in the topic when I was a kid. So I was carried away by the pictures from the Hubble telescope. Then I was struck by such images like Aurora Borealis and total eclipse of the sun that I photographed in Andes. And I'm trying to present the Milky Way or a night sky juxtaposed against some objects on Earth, and I'm trying to present a cosmic perspective and to present to all people that we are part of the something bigger, and we are part of the space, and that we will have to explore outer space in order to survive as a civilization. Very often my astrophotography differs a bit from other pictures taken by the majority of photographers and about the most popular images of dark sky, and I'm trying very often to get to some remote places which are not easily accessible, in order to very often before I take the picture I'm waiting for months for a situation, for some special pattern positioning of the Milky Way, and I'm trying to present the space, to show the space to people. At the beginning of this year an idea came to me. I started to think what can be done new, something innovative in astrophotography in order to take people closer to the space and to take to space people who haven't seen Milky Way at all. As we are living in a society, we are city dwellers, we have the light pollutions and Milky Way is hardly visible. This is how I came up with the idea to create a big picture of our galaxy. Some part of it, of course. And thanks to accuracy of this photo, we will be able to present the scale of the universe. In order to do it, we have gone to Namibia for 3 weeks, and we worked days and nights to get one picture made of thousands of individuals, exposures, and you will see how it looked like. the farther the desert, the darker sky, the better. That was our principle to follow. So that was the backstage of our activity. Starting from the very start, what is the origin of this idea? Why I got to it and I got attracted to it. When we take a look at standard astro photos, and these are one-off exposures with long lightning time, so we can combine with the first
I te zdjęcia są ciekawe, ale jeżeli spojrzymy na przykład po internecie, to takich zdjęć jest miliony, tysiące. Jakby każdy, kto tylko zaczyna swoją przygodę z nocnym fotografowaniem, tworzy mniej więcej takie kadry. I okej, tam widać drogę mleczną, ale prawda jest taka, że to światło drogi mlecznej od bardzo delikatnych mgławic jest na tyle
this light is it's not very intense, and you need hours in order to provide enough light to your picture.
Naświetlimy
So
kilkanaście minut jakiś kawałek drogi mlecznej.
Exposure is for a dozen of minutes. Very often it appears that, of course, Milky Way is
technicznie na to spojrzymy, to gwiazdy często mają jakieś niewielkie mankamenty i tutaj jakby jak przyjrzymy się bliżej takiemu zdjęciu, to już zaczynamy walczyć z ograniczeniami sprzętowymi. Więc podstawowym aspektem, który musimy w realizacji
So there are some things that we have to manage before a picture pleasant to an eye will be created. So here you can see such pictures made by for example, 50 seconds or a dozen of minutes, it's the same. After lighting of some part of sky, it appears that you can see the whole myriad of little dusts surrounding the galaxy. These dusts and pollutions are shaped by the gravity forces, by radiation, and by many other effects on a cosmic scale. Very often they have tens of lightning years.
Nieba dłuższą ogniskową, jesteśmy w stanie zebrać więcej światła na jednostkę powierzchni, to one focal ponieważ po pierwsze zyskujemy większą rozdzielczość, jesteśmy w stanie rozdzielić tworzone siebie gwiazdy, ale jesteśmy też w stanie zobaczyć te
light nearer stars, but also to see distant nebulae. So
nocnego nieba absolutnie pięknym.
Purpose was to present the night sky in the most beautiful manner possible. So to catch every nebula with hours of lightning, to show the exposition to light, to show, and that is the main strength of this project, that we show it exactly as we could see it with our eyes if we were able to accumulate light in our eyes. Unfortunately, we don't have this ability as people, and for that reason we cannot see nebulas as accurately. But it doesn't mean they're not there. They are there, but the only thing to do is to register the light. So that was the first image, the first picture I made in February 2021. So I imagined what would be a perfect picture of the sky to present to people, even to people who are not interested in this project. So I assumed that I want to create a large picture, several giga of pixels, to be able to print it on meters wide material. So taking such an approach I would like to provide something that even after a close-up look, that would give an accurate image of some galaxies or distant ones. Of course, at the very beginning, it was not possible to start this project without asking myself a question whether somebody did something, had done something like that before. So, of course, I found some sky reviews that have been completed before, but the problem with them is that these are some scientific data focused on astrometrics and photometrics, and these data is black and white. Maybe I exaggerate a bit, but if we were to compare this picture with the picture I've presented you, so full of colors, of structures and shapes, the pictures, high-resolution pictures are quite boring, in fact, when it comes to their visual aspect. So this is the picture that was published at the beginning of the year by a Finnish astrophotography. It took 10 years to him to take such a pictures. In total, it was about 200 hours of exposure to light. So I made an assumption that with 200 hours of exposure, it's a good strategy to create something valuable. So I assumed a few things in order to follow and to complete this project. First and foremost, I want to make it the largest commercial Milky Way photo ever done. The scale has to allow to admire individual galaxies concentrated out of the Milky Way. So I expect the beautiful picture in its majesty presenting the greatness of our galaxy, but the whole project is not only about an image, and I'm not doing it for fun only. We want to present a fascinating story of which is behind that. These are hundreds of hours of preparations, our trip to Namibia, post-editing and everything, and thinking about what has to be done with the picture. So it will be a piece of art for sure, within the meaning of museum-like art, but we suppose it to be a piece of art that will bring the galaxy here on Earth. From the technical perspective, I had to collect and catch a lot of light, so hundreds of hours. Thanks to the amount of light caught, I will be able to get rid of the poorest objects and skip high resolution of the picture, respecting all details in light and in shadows as well, because the light is... So if you want to expose the smallest galaxies and the darkest galaxies with light, other ones are too exposed. So this project was subject to some technical aspects and limitations that I had to fight from the very beginning of its implementation. So the first one is I've prepared several solutions, in fact, and in practice it appeared that it didn't work. So the rotation of the field, I had to apply a special piece of equipment to follow the stars. Thanks to that, I can carry out this long-term exposure to light. Sometimes my frames got distorted from standard, and I had to spend many hours in order to make up for it, to compensate for unmatched pieces, and it was a burden. It was a mundane task to do so in order to have to create one picture. So noises, another thing, in order what to do to show the smallest objects in a galaxy which is so distant from the planet Earth. And here we have galaxies which are at the distance of 250 million light years. So I had to do tens of photos with different photo cameras. Every night for 3 weeks, every 15 minutes, I had to change and control the frame to see whether everything is fine. And thanks to that, we can see the difference between a single shot and stacked products, so combination of many shots. The major challenge to tackle that we are not aware of at all while implementing such projects, this is so-called leveling of the background. And there are many aspects included in it. These are some aspects taken from scientific work, because now I'm working on the techniques of background leveling. These are digital techniques. Photography in its standard version stopped. And it's only about mathematics now. So as you can see, we have some areas which are more red, some are more orange, and we had to arrive at a uniform, homogeneous background. That is a result of a difference in the atmosphere during different parts of the day. So I photographed at different levels over the horizon sometimes. Another topic that we have to tackle is the need of strong computing power. So we need a strong computer to combine all details, because we have about 100 gigabytes in raw pictures. And if one raw picture is quite a lot, here I have to work on a file which will have about 100 gigabytes. So now we're working on it, and we're working on our providing ourselves with an access to such a powerful computer, and that will be the more or less the final effect of our work that I predict, because I know that such a field of coverage will be possible for me to achieve. It will be about 1/3 of our galaxy, which is visible from the southern hemisphere of Earth. I will continue this project to recreate the whole galaxy, but what will be really interesting here, this is just a look-up version. You cannot see the little and saddle structures that I want to see, because here I just combine the pictures in order to see whether I did everything right, and whether it may, because it could happen that some part of the sky would be missing, but so that was just to check. But that will be the image that we will have. Will be about a dozen meters long, and it will be possible to look at under a magnifying glass. So it's less than 1% of the field. So this image that you can see now, this is a preview of the final version. So this is a part of the Magellan nebula. I know that it will not be there in this in my frame, but just to give you the picture, the final picture of my work. So as you can see now, you can visualize that this wall, which is in front of me, it will be the whole picture. And it will be, so it will be giant. It will be a great part of the space that we will bring here on Earth. And what is my business now? So there are still some things to be tackled, because combination that takes a lot of time. You cannot combine it with Photoshop to create a landscape. We're looking for some methods of dividing and boiling this picture down to individual pixels to be able to make me sure that the quality of this pixel, of every single pixel, is the highest possible. So my trip to Namibia, it was a trip to collect some data, to collect light, and behind that there is a series of processes that have to be completed in order to sieve the right data and show the final picture. So leveling of the background, as I've said, leveling and calibration of colors. You can use stars as color calibration and astrometrics. As another indication, we want to create an ultra-accurate map of the sky, and we want to do many other things, commercial things, that I will not tell about it now. They're our business secrets, so we're doing everything not to limit our work to just a beautiful picture. We want to push the scientific data collected by me and to show galaxy in movement, because we think that stars are there fixed on the sky, but the truth is that they're moving, and we're able, thanks to scientific observers, to follow that movement, and we want to combine both aspects. Of course, there are many other aspects related to post-editing, making this picture attractive to an eye on a big scale, and we're working on commercialization and marketing in order to attract as many people as possible to this project. Now I can say it boldly, that's all around the world, because we don't want to keep this project here in Poland. We want to go global, and this is a project consulted with a few experts and astronomers from around the world, allowing me and helping me to understand what is there on this picture and what can I do about it. So what can I say? Everybody interested in some follow-up information and my next steps, feel free to contact me. I can provide you with my newsletter. For sure, you will be informed about the announcement that the picture is ready. Okay, thank you very much. Should you have any questions, I have about 90 seconds to respond to them. Thank you.
Tak, na pewno będzie wystawa.
Yes, there will be some exhibition, hopefully not only in one place in Poland. Yes, this is a picture that we want to present in its physical form. The idea behind this is to stand in front of the galaxy to watch it in the most beautiful possible version.
Nie ma już chyba więcej pytań, więc...
So, no other questions?
Proszę, zaczynamy.
All right, test 1, 2, 3. We're good to go?
Proszę start.
Well, welcome back to the European Rover Challenge, live from the Mars Yard at the Kielce University of Technology. My name is Remco Timmermans, and I will take you live into the action at several moments during this 3-day event. I will talk with competition judges and the people behind the biggest space and robotics event in Europe. In this 10-minute episode, right now, I will talk with head of the jury, Marcin, about how the Rover competition actually works.
Hello.
Earlier we heard from Kasia about the layout of the Mars yard and the different elements. Now we will look at the different tasks the team have to face. So let me ask you, Martin, there are two competitions happening at the same time here. Can you talk about the key similarities and differences between the on-site and the remote competition that's happening here?
Okay, so I guess basically the main similarity is just the place in which they are happening. So it's in the Mars yard. So basically we have both navigation and science task, and we have maintenance task also in both formulas, but they are a bit different. So basically in the on-site formula, the teams are the teams build their own rovers. In the remote, they are using the Leo rover, which is a ready to drive platform. So that's completely different, because in case of the on-site you just need to design the whole rover, so it means mechanics, electronics, also program everything. But in case of the remote, you only focus on the software, or mainly focus on the software. However, I would like to add also that it didn't start here on the Mars yard, because there were many more tasks. So for example, in the remote edition they had the test drives, which were also the qualifications for the teams. They had to prepare quite a lot of documentation. For example, also in case of the on-site, they had also to provide documents like the proposal, preliminary report, final report, video. So that's only what is happening here. That's, I would say, 60% of what happened in the past.
Okay, so this is just the last part of the competition.
It's just the grand finale.
Okay, excellent. Well, and a grand finale it is, and we have nice weather, and the teams are busy doing their thing. So all the teams have to perform certain tasks. There's a task to navigate around the Mars yard here. They have to perform scientific experiments, to probe the maintenance tasks. They have to do remote maintenance on other equipment, as you said. Can you talk us through what some of these tasks really mean?
Yeah, so for example, a few minutes ago, 20-30 minutes ago, we have seen that one of the teams was doing the navigation task, and it means that they are just getting from us locations of 4 points to which they have to navigate, but they cannot see anything on the screens. They do not have any vision from the cameras. So basically they just need to base on the landmarks which are located around the Mars yard, and they just try to do it in the autonomous mode.
Okay.
After that, they are going to do the probing and science tasks. Probing means that they have like three probes which we are giving to them, and they need to place them in a certain spots. They choose 2 of them. The third one is proposed by jury. After placing the probes, after some time they need to collect them back. So they basically, this part of tasks checks the ability of robotic arm to take it out, place it, and take it in back. And so it's kind of, because in the previous years we were focused more on samples collection. Right now we are focused on both, so on living something and also on
very similar to what we see the Perseverance rover doing at the moment, where it's taking probes, putting it in test tubes with the goal of leaving it in a spot so it can be picked up later.
Yeah, exactly. Luckily here we can do it in Kielce with the air everywhere, not CO2. So at least we can watch from, we can have a closer look. Excellent.
Now, after the competition or during the competition, the teams are performing their task, you are judging them. How does the jury rank the scores of the teams? Kasia told us about the mission reports, you also mentioned them. How is it ultimately decided which team is going to be the winner on Sunday?
So basically we are summarizing all of the points for all tasks which were in the past. So starting with the documentation, video materials, all of the reports, and going through this part of the challenge. So all of the scores which were gained during those 3 days, we are summing this up, and the best wins.
Okay, well, can't wait to
all
see.
The rules are, I hope, clear as they were published in the rulebook.
Yes.
So right now we just need to follow it and to sum it.
Okay, excellent. Now, we see behind, well, not right now, it's quite empty here, but behind us, during the day, we see very different rovers in the competition. There's small ones, there's bigger ones, different sizes. Are there any restrictions for rovers that teams have to work with?
In case of remote formula, the rover is already defined, so
Of course.
no restrictions,
Yes.
of course. In case of the on-site, the limit is 50 kilograms. Additional limit is that teams cannot do any changes of the configuration during the tasks.
Okay.
So basically, if you would like to change the robotic arm or anything like that, it's possible, but it will cost you a lot of points.
Okay. Well, thank you very much for the interview, Marcin.
Thank you.
And please, everyone online, keep watching. Follow us on social media. We're on Twitter, Facebook, Instagram, and LinkedIn. Follow us under hashtag ERC2021 and keep following the live stream. And I'm looking forward to seeing you again with a live intermission from the Mars Yard tomorrow. Thank you very much.
Now, that was a quick recording from our Mars Yard. You could see what's happening there right now. Still excellent weather, hopefully also tomorrow and day after. And now we proceed to the next item in our agenda, technology and instruments employed in rovers for the exploration of space missions. Germán Sarmiento, the Mars Society, Colombia.
The history of evolution has taught us all those organisms that preceded us were the fundamental basis for the coexistence of the humans. In this case, the microalgae Astrophyra platensis, better known as spirulina, is a microalgae that from its essential characteristics has been evolving throughout the history of making, and today becomes a benchmark from the history of the people that is now in war and Latin American culture. The Aztecas already knew and cultivated in the Lago Texcoco what we know today as Mexico. These societies knew of the benefit that spirulina had. It is for reason that different archaeological engravings and manuscripts have been found that had allowed been identifying how these people use it. These novice tribes in Africa, there are also references to its use. As well, some space missions already have carried out tests, including NASA, where they have seen the different benefits that spirulina might have for the colonization on the other planet, not only in terms of food, but also on oxygen and other benefits that this microalgae can deliver.
My name is Germán Sarmiento. I'm the director of the Mars Society Colombia in the Mars Habitat European School today. This is a project is developed for travelers in the space. This is a project is in collaboration in the different persons, the different specialties. This is engineer, biological, chemistry.
This project is based on the characteristics that spirulina has, where we begin to study from its minimal expression, analyzing its internal structure under the microscope, and they begin to develop the different crops that we need to be able to make into more complex systems where it allows us to generate the sufficient amount of biomass that we need. This biomass can make it edible, but we could a little further and mix this spirulina with flour to make our bakery system based on spirulina. Laboratory work is one the main requirement with how we producing spirulina synthesis, where we select the best ones to be able to produce an excellent quality biomass, and we can grow on a large scale. The first step of our process is to identify the appropriate microalgae to produce the guaranteed amount of spirulina. From there, we move on the new step, which is generate the culture in the laboratory. From there, next step is into a small deposit where we make and grow to then make it's possible to pass to the tanks that we had designed to be able to work in volume and to be able to have the amount of biomass necessary for our final product. After this phase, where we have already working in the laboratory, what we do is have the crops to be able to start working of them. This process taking about a week where we begin to have the first biomass and we can begin to have the specific crop for later pass is the work thanks this spirulina. We have those different elements which we can work with to different types of microalgae. Our process continues in a small tank is we are going to make this microalgae can grow and go to a slightly larger element. This process takes about 15 days, where will be already have enough cultivation to be able to migrate at the higher elements. After having passed through the small tank, we are ready to make the two main tanks, where we have for large tank where we do the direct cultivation of the microalgae that we have grown from the laboratory in order to extract more biomass.
You can see tank of cultured microalgae, 113 cubic meters. The culture. Here you can see the green color water, like this shows us the microalgae concentration, high concentration, 5 million or to 8 million cells per milliliter the culture. It's very important for build all the food necessary to food for travels, space travels.
In this time, what we are looking for is to be able to generate the large amount of biomass biomass that will allow to obtain spirulina derivatives for food projects. Urging the automation of this tank is powered by the solar panel that heat the energy to control pumps and sensors used to improve and condition water for biomass production. This development is to promote work in STEM with college and university students so that they see this type of solution in alternative to help the Earth and the future space travel, and new colonization to have an element that helps them to sustain life from this type of microalgae that had proven to be an alternative to the problem of food and oxygen, fundamental factor in the process of terraformation. This research is being carried out in conjunction with the European Space Foundation to incorporate new technologies to support space mission. In addition to this, we are developing a rover that helps the astronaut on physical level. Our rover is designed to supplement food, oxygen, and medicine to the astronaut in his exploration. In this project, we had a number of disciplines or novels that are fundamental part of the success of this project. We had engineers, psychologists, 3D designers, nutrition, chemistry, baker, agronomists, with the free object of promoting space research in Latin America and giving a contribution to the development of world space research. The process that we develop for the use of energy in all our research process we do it using renewable energies that help to optimize the process that is with this solar field that provides us with all the necessary energy to be able to maintain the tanks and the greenhouse with hot. After cultivating spirulina in the tank, the next step is to have the biomass ready to mix in with the flour as to be able to produce bread and food based on this microalgae with hot curry augmented with different types of flour and flavors to optimize the bread process. After having carried out the whole process of building a bread, we then do the oven with the whole process with a traditional bread, and in this case we can already have sample of what spirulina based bread is. In the bread-making process, we have carried of a number of steps that allow the flour in consistency of bread to be of the best quality. We use portion of 17 grams as the basis of the portion of the food and the any human need to be able to survive and they with his single food. This portion of bread is enriched with spirulina that complement the nutrients and vitamins that are needed for optimal function of the human body, plus the characteristics of the flours and mixtures that will make with use to free of gluten with aromas with natural flours that allow the sun-cast acid flour that spirulina has of the palate of the contrary, so that is very rich of the taste. The spirulina has different process where it's mixed its power to high rate of illicit production of vitamin and protein and our bread.
Spirulina is a cyanobacterium, and this group is considered macroalgae. This microalgae we use in the production of piece of bread. You can see the green part in the piece of bread show the spirulina, and you can eat this piece of bread, and this is the food for the space travelers, and is a part important, very important in the space colonization of other planets, and that humanity can be a large travel in the space.
This research investigation in the Mars Society of Colombia and the European Space Foundation and Project Habitat Sustainable Mars. This vaccine is fundamental for food survival in the astronaut and mission space.
Hello everyone, my name is Sebastián Moreno. I am an engineering student and I know of Mars Society Colombia about 1 year ago. What is my society? For me, my society Colombia is more than volunteer. We are a special team, a great team. You find a lot of people in different areas of knowledge. You find mechanical engineer, electronic engineer, developer. You can find also teachers about physics, about biotechnology.
Thank you. En the European Rover Challenge 2021, un hub in the Colombia. Bye bye.
Thanks to the work of many people in the development of this process, we have been able to obtain very good results that have been tested and analyzed in detail for human consumption. The advantage and benefit that spirulina has, not only for the production of bread, but also for the other derivatives that we are working on, allow us to continue with this work and build solutions not only on here, but these other systems solved and speed with food production and the sustainability of the human race use priority. Very soon you will see more progress of the user research. And remember, never stop looking at the sky.
Ladies and gentlemen, that was the Mars Society, Columbia. And now we go to Miss Tanya Harrison. Hopefully we have some time left for the Q&A from our audience after the presentation. The title of the presentation is What's Up on Mars? Tanya, are you with us already? Do we have a connection? Let's see. Sometimes, ladies and gentlemen, it seems that it's more challenging to connect here on Earth than from Mars to Earth, apparently, for whatever reasons, ironic as it sounds. Last year, there were lots and lots of online conferences, as you all know, and the irony was that the connection was more stable when the country hosting the conference was South America, for example.
Right. Hi, everyone. Thanks for joining today. I'm Dr. Tanya Harrison, and today we're going to be talking about exploring Mars by looking at all of the active missions that we have there right now and what they're doing. We have a veritable fleet at Mars today. We have a ton of orbiters from NASA, the European Space Agency, the Indian Space Agency, the UAE, and China. We have landers and rovers from NASA and China. We have a helicopter from NASA. So this is the most active that we've been on Mars ever, and it's really amazing to see. So the oldest mission that we have that's currently operating at Mars is called Mars Odyssey, and it's a NASA mission that got there in 2001, and it's the oldest mission that is still operational. And we use this mission to help do things like pick where we were going to land the future rovers. So one of the discoveries that Odyssey made that was a really big player in deciding where we were going to land the Opportunity rover, which got to Mars in 2004, was that it mapped the whole planet in the thermal part of the spectrum. And if you don't know what these labels mean on this map, you don't really need to know. It's basically volcanic, 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 some ice, some dust, and then there's this red spot right in the middle that says hematite rich. And if we zoom in, which is the view on the right here, we'll see that there's one spot on the entire planet that had this bright signature of hematite. On Earth, hematite forms where iron-rich rocks interact with water. And so this was a prime candidate for Opportunity, whose mission goal was to follow the water. And when we got on the ground, we discovered that there were blueberries there, quote unquote, little hematite nodules that were actually the source of this hematite signature. So there was enough of them there that we could see it from space. We also found water on Mars with Mars Odyssey through something called the neutron spectrometer. And it made this map of Mars where the blue areas are places where we knew that there was ice underground, and then the red and yellow areas are places that were either no ice or much drier. And so we'll see in a few slides how we were able to confirm this with other measurements, but these neutrons basically told us there was hydrogen in the soil here. Generally speaking, hydrogen doesn't just hang out by itself in rocks. It usually is bound to something, and that something is often water, either as H2O, which we normally think of as water, or geologists also think of OH, which is hydroxyl, as water too, when we're talking about rocks. So both of those cases are highlighted in this map here. Then we have Mars Express, which is a European Space Agency mission that got to Mars in 2003. And it's in this strange elliptical orbit where it gets really close to Mars at some points and really far away from Mars at others. And it does this to collect three-dimensional stereo views of the planet, but it also captures really amazing what we call limb views. So when it's far away, it can turn around and tilt and look back at the planet where we actually can see the atmosphere. So this thin, wispy blue layer that you see over the planet is the Martian atmosphere. And there's no way for us to see this without turning at a really extreme, what we call slew angle, and looking through the atmosphere from orbit to be able to see that atmospheric height. If you look straight down, you don't see it unless you're peering through clouds, for example. So here we can see some ice on the surface in the bluish white areas on the right. And then as you move toward the left, you're starting to see dust and water ice clouds that are hanging out over the surface. This is another view from Mars Express. This is the south polar cap of Mars, and the northern polar cap is made up of water ice. The southern polar cap is made up of carbon dioxide ice, and it's much, much smaller than the northern polar cap. And we can even zoom in with another Mars Express view. It's absolutely beautiful. It's been returning these stunning color images now for almost 20 years. So if you go to the Mars Express website, you can see tons of gorgeous pictures that this mission has been returning of Mars. It's also returned images of Mars's moons. So this is Phobos, which is the larger of Mars's two moons. The moons are Phobos and Deimos, whose names mean fear and panic, since Mars is the god of war in Roman mythology. We've never actually visited Phobos, but there's a Japanese mission called the Martian Moon Explorer, or MMX, that will be going to both Phobos and Deimos in 2024 to help us learn a little bit more about the moons and where they might have came from, because we're not sure if they are captured asteroids from the asteroid belt that happened to get flung into the inner part of the solar system thanks to gravitational interactions between Mars and Jupiter, or if these are actually pieces of Mars that were shot out from the planet when some kind of impactor smashed into it, formed an impact crater, and some of those pieces were traveling fast enough to escape the gravity well of Mars and go into space. Some of them probably fell back down to Mars, and a couple of these pieces, like Phobos and Deimos, might just be the only two that are still present in orbit. So we'll find out with that mission, hopefully. Then we have the Mars Reconnaissance Orbiter, which is a NASA mission that got there in 2006. And this was actually the first mission that I ever worked in operations for, so it holds a special place in my heart. And this mission has a ton of different instruments on board to basically follow up on investigations from Odyssey and Mars Global Surveyor, which operated from 1996 through 2006. Mars Global Surveyor and MRO overlapped in operations for a few months before we ended up losing contact with MGS. And Mars Reconnaissance Orbiter revealed that Mars is an extremely dynamic place compared to what we thought before from these older missions, because we were able to collect so much data and get repeat coverage over areas. So these are images from the HiRISE camera, which takes really, really high resolution, like 50 centimeter, 25 centimeter images of the planet. And we were able to capture things like polar avalanches of dust falling off the edges of the northern ice cap as they were happening. So these are clouds of dust where we caught these avalanches in motion. That's hard enough to do imaging Earth, much less on another planet. And we were able to not only capture them, but we were able to determine when during the year they happen. And so we can proactively look for them to keep track of how often they're occurring year after year. We also found these features called recurring slope lineae. And this is something that is so small that we weren't able to resolve it with previous missions. So the HiRISE camera really made this massive contribution here. And the RSLs are these dark features that we see that form in the warmest parts of the year on really warm slopes, and they grow incrementally over the course of many weeks, and then they stop and they slowly fade away. So that's not a characteristic that we tend to see with an avalanche or a landslide. So what we think this is, at least if they're dry, so what we think this is are brine flows where really salty water is seeping out onto the surface and flowing very, very slowly over the course of many weeks when it's warm, and then the water is eventually sublimating away. It goes straight to gas into the atmosphere. It needs to be a brine because Mars is too cold and the atmospheric pressure is too low to be able to have liquid water sustained on the surface unless it is extremely salty. We've seen a lot of new impact craters too. We have coverage of the planet from MRO, from Odyssey, Mars Express, Mars Global Surveyor, and then going back even farther, we've got Viking and all the Mariner missions. And so we would see images where a new impact crater, which looks very distinctive, it has this blast zone around it, all of this dark area. This is actually where the shock wave from the impact has blasted the dust off the surface to reveal that darker Martian surface underneath. So once you get underneath all the dust on Mars, the surface is actually more black or gray. So it looks a little bit more like the moon or Mercury. So we would have places where we'd see these blast zones, and we could go back and look at older imagery to figure out when did this impact form. But the coolest thing is we found some of these new impacts that actually excavated ice from the subsurface. And these impacts formed in the places where on that neutron map we saw earlier, we predicted that there was ice beneath the surface. So this was a beautiful example of predicting something from one indirect measurement and now directly being able to see it. And this is not something we ever expected we would find. This is a brand new discovery from MRO, and we wouldn't have been able to see this if we didn't have this repeat coverage with these high resolution cameras. This has huge astrobiological implications, obviously, because wherever there's water on Earth, we find life. So maybe there's life hiding in the ice on Mars. Or we can utilize this ice for astronauts in the future. We can melt it to create drinking water. We can use it to create rocket fuel. So this was a massive, massive discovery. Then we have MAVEN, which is the Mars Atmosphere and Volatile Evolution mission. And this got to Mars in 2014. And this is a mission specifically designed to look at the atmosphere. So you don't tend to see a lot of images coming out of this mission because it's looking at things like different types of clouds. This is a view of Mars in ultraviolet where you can actually see some of the clouds. So the bright areas on the left, you've got sort of 3 dots of bright. Those are clouds hanging out over the summits of the large volcanoes, the Tharsis Montes, as we call them. And then you've got a lot of bright yellow areas on the right side of the frame. And these are clouds that are sort of hanging out over Valles Marineris and then moving over to an area called Arabia Terra. And MAVEN threw us a curveball because we thought that the magnetic field on Mars was dead. We thought the core had solidified and there was no magnetic field left. But then MAVEN discovered an aurora at Mars, which requires a magnetic field. So this was a bit of a mystery. And this led to some of the investigations that were performed later by the InSight lander, which we'll talk about a little bit later. Then we have India's first mission to Mars, which is the Mars Orbiter Mission, or MOM for short. And this mission was designed to look for signs of methane in the Martian atmosphere because a few missions before this, including Mars Express, had hinted that there might be methane that was being emitted seasonally in specific areas of Mars. And on Earth, methane is emitted by either life as a waste product or volcanic activity where you have warm water interacting with certain types of rocks in a process called serpentinization. So either way, it's a big deal. Either Mars was geologically active in certain spots, or there was some kind of maybe bacterial life producing methane as a waste product. Unfortunately, the methane detector on MOM didn't work properly, so we didn't get good measurements from that. But it has been collecting really beautiful color images. So we get these nice global views of Mars where you can keep track of some of the weather, and then some nice close-up views of things like volcanoes and craters. It also captured some views of Deimos, the other moon of Mars. So this is Deimos moving across the frame in multiple images. We've never gotten very close to Deimos, so we don't have great pictures other than things like this. Then we have another European Space Agency mission called the Mars Trace Gas Orbiter. This was another mission designed to look for methane, and it's been taking measurements since 2016. It also has some really amazing color cameras on board. So ESA's been doing a fantastic job with these color cameras. This is called Cassis, and it takes color and stereo, so three-dimensional images of huge swaths of the planet. This is another color view from Cassis of some layered sedimentary rocks on Mars. You'll see a lot of images from Cassis and from HiRISE where some of the stuff on Mars looks blue. This is just areas that are less dusty, where we've brought in the near-infrared band. So in that particular band, the dust-free areas on Mars tend to look blue, but it wouldn't look blue if you were standing there. Then we have Curiosity, which got to Mars in 2012. And Curiosity has been driving around in an ancient crater lake called Gale, where we've been looking at the different layers that are left behind from when the lake evaporated to see if there was signs of habitability. So when the water was around in the lake, could life as we know it have survived? So it landed here next to this 5.5 kilometer tall mountain called Mount Sharp. And this mountain has a bunch of layers that, like I said, were left behind when the lake evaporated away. Curiosity's been on Mars for almost a decade now, and it has determined that the lake here was habitable. It had all the right chemical conditions for life to survive, so that's been really fantastic. And Curiosity is able to take selfies on Mars, so it has a 7-foot-long robotic arm with camera at the end, where it holds it out, turns the camera back around, and then takes a series of images to be able to mosaic them together, and then we can see the rover on the surface. We don't just do this because it's cool to see the rover, we do it because it can tell us a lot about the environment around the rover and the current state of the rover physically. So we can see things like how dusty the deck is, we can look at the wheel tracks, which will tell us if the rover has had any trouble driving in certain terrain. Sometimes it's really hard to drive on sand because it's extremely loose, you don't get a lot of traction. And unfortunately, we're able to see things like holes in the wheels. So luckily the wheels on Curiosity are working just fine, but they do have some holes in them. And sometimes we drive over things with the wheels, either on purpose or by accident, and we can break the rocks to see what Mars actually looks like underneath all the dust. And I mentioned before, Mars is kind of grayish black under the dust. This is what that looks like. So this is a rock that we drove over with Curiosity, and you can see the dusty outer part that's been exposed to the atmosphere, and then the gray interior that we've just exposed to the atmosphere by breaking it. So this is actually what Mars looks like. It's the gray planet underneath all of the red. And then this is a view from some of the hazard avoidance cameras where we can actually watch the rover operating. So we can see if it's executing the commands properly that we've sent to it. So this is the turret at the end of the arm. This has that camera that takes the selfies, but also a lot of other instruments. There's a spectrometer, there's a drill, there's a brush. So this is an incredibly powerful tool mounted at the end of this arm. The white hill in the back, it doesn't look like much from this angle because it's a really wide angle camera, but that is actually Mount Sharp, those layers of sediments that we're driving up right now. Curiosity has also viewed eclipses from Mars, so they don't look nearly as impressive as the ones on Earth. So obviously the top view is an Earth eclipse. The bottom view is a Mars eclipse from Phobos. But they do happen quite often, and it's kind of cool that we can see something on Mars with the rovers that's very easy for us to relate to as humans here on Earth. And this is an animation of what that actually looks like. This is not real time, obviously. It takes about 6 hours for Phobos to go around Mars. Then we have NASA's InSight lander, which got to Mars near the end of 2018. And this is a stationary lander designed to investigate the interior of Mars. So what is going on inside? What kind of geologic activity, if any, is still happening? And it did this through two main instruments, a seismometer. This is actually a view from the lander of deploying its own instruments. So there it is, putting the seismometer on the surface. It's attached to the lander with a cable. And then we cover it with this little dome to protect it from being blown around by the wind, because we don't want to confuse wind with a Marsquake. Then there's also a heat flow probe, which was designed to measure the interior heat coming out of Mars. Unfortunately, we had some problems with the heat flow probe actually hammering itself into the ground, so we didn't get a lot of data from it, but we did manage to get measurements from the seismometer. And we discovered for the first time on Mars, Marsquakes. And they're magnitude 3 to 4. So this tells us that there is some kind of geologic activity inside of Mars today. And if you were standing on the surface next to InSight, you would feel it. It would feel about the equivalent of a giant truck driving by outside your house. And then just this year, back in February, we had a whole fleet of missions arrive at Mars. One was the UAE's HOPE mission, which is an orbiter that's designed to work in tandem with NASA's MAVEN mission. So MAVEN is studying the upper layers of the Martian atmosphere, and HOPE is studying the lower layers of the Martian atmosphere. So together, they'll paint a complete picture of what's going on. And the teams for these two missions have actually been working very closely together. So it's a really beautiful story of international collaboration. And it takes some really gorgeous global views of Mars. This is the first view that HOPE got of Mars earlier this year. Then we have China with their Tianwen-1 mission, which was a combo orbiter, lander, and rover. So they tried everything all at once, and they were all successful. This is an actual view of Tianwen-1 in space from a little camera that it deployed on the way there. And then here's a view from the rover sitting on the lander platform, one of the first views it took from Mars, and then a view from the lander of the rover sitting on the surface. And they've been having a lot of success driving this mission around as well, which has been really exciting to see that they were successful with their first ever mission, because it's not easy to land on Mars. Then we have Perseverance, which is probably the one that's been stealing the show lately, or more accurately, its little helicopter friend Ingenuity has been stealing the show. So Perseverance is in another ancient crater lake similar to Curiosity. This is called Jezero Crater. But it brought this little helicopter along with it. So this is where it's landed, and it's investigating this delta feature here, which is what forms when you have a river that empties into a standing body of water like a lake or a bay. And so we're hoping that if we go and sample the layers of this delta, we can find evidence of ancient life on Mars. So Ingenuity hitched a ride to Mars on the belly of Perseverance, and this was a mission, a tech demo with the mission to see if we could actually fly on Mars. And we were able to. We've now performed 13 successful flights with the helicopter, which is pretty incredible when we weren't even sure if we would be able to fly on Mars because of the low atmospheric pressure, the atmospheric density. But the helicopter has been performing extremely well. The goal here is that we could send helicopters like this with rovers to fly ahead of them and collect data to help with autonomous navigation so that the rover can see in its immediate path, if you're going from point A to point B, what is the safest way for it to get there? And then just a few days ago, we collected the first successful samples from this mission that will be returned to Earth to be analyzed in labs to figure out if there was ancient life on Mars, so we can do things like DNA sequencing. This is a view of the rock that we drilled. I believe this was September 6th or 7th, so literally just a few days ago. And then here's a view of that sample successfully drilled. It's going to be put in a vacuum sealed container, and then that will be plopped down on the surface. And in the next decade or so, a European fetch rover is going to go and collect all of those samples and bring them back to Earth. We'll collect about, I think, 40 of them in total. So the goal of all of these missions has been to figure out, was there ever life on Mars? We know from the progression of missions that Mars was habitable. It had water, it had all the chemical conditions you need for life to thrive. It had all the right ingredients like organic materials, so carbon, and oxygen, nitrogen, everything you need for life to survive. We know that Mars was habitable, but just because it was habitable doesn't mean it was ever inhabited. And so the question is, was there life on Mars that died out at some point? Was there life on Mars that is only microbial and it's just hiding in areas that we haven't been able to access it yet? Or did life never arise on Mars? And to me, that's almost the more interesting answer to the question, because we know that Mars and Earth were very Earth-like. They were both habitable at the same point in the history of the solar system, but we got life on Earth everywhere you look, and there is no life on Mars, at least today. If there was never life on Mars, but it was Earth-like, that tells us that Earth is really special, and that something here happened to spark life that didn't happen on Mars. And so I'm really excited for us to get those samples back from Perseverance and hopefully really answer this question once and for all. Thank you.
Thank you very much, Tanya. I hope you can hear me now. Can you?
Yes.
Well, I can see your Twitter address now. It's Tanya of Mars. So it sounds like your life is pretty much about milestone after milestone of space exploration. If you were to give us your top 3 memories of those milestones, what would they be?
Oh gosh, that's hard. Like in exploration in general, or for like my career specifically?
And in your professional experience specifically?
I'd say the top one was getting the first image back from Mars that I ever got to take from the Context camera on Mars Reconnaissance Orbiter. That was surreal. It was my dream to do something like that. So to actually get to see that and get the image back was really amazing. I think getting to work on Opportunity, this is a little depressing, but I was working on Opportunity the week that we lost contact with the rover. And so that's a sad moment, but it was really impactful to be part of the mission at that point. And then similarly, I would say being at JPL when we decommissioned the rover, when we made our final attempt to contact OPI and then called the mission over, that was extremely emotional. I cried a lot over a robot, which I think would surprise a lot of people. That room was full of tears, but being there with all those people who had spent so many years of their life working on this mission was a really incredible feeling. And I feel so lucky and so honored to have been there to say goodbye to the rover.
And let us wish you more such emotional moments linked to space exploration in the future. And thank you for finding the time to join us here at ERC in Poland.
Thank you so
Thank
much.
you so much once again. All the best.
All right. Bye, everyone.
Ladies and gentlemen, that was Tanya Harrison, and now we'll go to the interview with the real legend of Mars exploration. If you remember, his first book about Mars is 1996, entitled The Case for Mars. 2 years later, he set up the Mars Society, and in 2019, his most recent book was published, The Case for Space, very recently released in Poland, in Polish by PWN. I couldn't talk to Robert in person. We had a very short slot to talk to Robert, only 20 minutes. I was on the way somewhere. I had to stop the car in the middle of the road and do this interview. 20 minutes with Robert Zubrin. Let's listen to it together.
Robert, it's absolutely fantastic to have you with us at ERC. Thank you for joining.
Thanks for inviting me.
This conversation is essentially a follow-up to questions from readers following the Polish premiere of your book, The Case for Space, first published in Polish by PWN on the 31st of July 2021. And we already have a list of questions for you, 11 so far.
Okay, well, fire away.
I understand we don't have much time, more or less 20 minutes in the program, and 11 questions, that gives us less than 2 minutes per question. So I will fire away indeed. First question. We know that on the one hand, competition drives the market and in many ways defines progress, but also reduces costs. On the other hand, we need cooperation and unity towards a common goal. Do you think such a unification of countries, because at the level of international companies it is already happening, to act together from the position of Earthlings, not nations, realizing the common mission of colonizing Mars, developing a Type 2 civilization is possible? In other words, what must change for such a noble experiment, as you explained it in your book, to happen?
Well, I think the space enterprise needs to be underscored by a spirit of brotherhood in a great cause. But nevertheless, I think that it needs to be done on a competitive basis. I think that the space program, the official space programs, ground to a halt when there ceased to be, for instance, international competition regarding, well, first the moon race and then the space station. I think that we can compete in an Olympic spirit and compete for honors as to who can do the most to advance the cause of human expansion into space and the discovery, in the way that science as an enterprise is pursued. Scientists compete with each other. They want to win that Nobel Prize for themselves, but it is a grand joint international enterprise. And I think that the human expansion into space can be pursued the same way.
On the other hand, we all know that if you study the story of globalization, international trade, all kinds of conflicts and attempted cooperation, it hasn't exactly been easy. So why should space exploration be any easier? Are the motivators more powerful, or any other factors are involved?
Well, look, once again, there will be competition in space. There should be competition in space. But the overall enterprise, as in competition in technological progress and in science, underlines a fundamental brotherhood of man. That is, look, the thing that sets humans against each other is this idea that resources are limited, that there's only so much to go around. And in fact, this conceit was ultimately, I believe, the cause of the great disasters of the 20th century. World War I, World War II, the Holocaust, the Holodomor, were all ultimately caused by pathologies induced by belief in this idea of limited resources. But if we understand that humans are not competing for limited resources, that we are, in fact, are creators of resources, and therefore the more creators, the more resources, then there can be a brotherhood. Only in a universe of unlimited resources can all men be brothers.
Next question. Is the Falcon rocket, BFR generation, already the one whose power will allow us to carry the necessary loads, cargo, fuel, etc. into the trans-Martian orbit? How do you think?
Well, certainly the SpaceX company is acting as the cutting edge, the vanguard, if you will, of the entrepreneurial space revolution by introducing entrepreneurial ways of doing business and mostly reusable spacecraft, space launch vehicles. They've cut the cost of launch by a factor of 5 in the past decade after it was stagnant at the same level for 40 years. And if the Starship is successful, a fully reusable heavy lift vehicle, they'll cut it by another factor of 5 within the next 5 years. And this is going to make all sorts of things possible in space. But SpaceX is not going to be the limit of this. But SpaceX is just the beginning of this. I'm aware already of 5 companies in China that have gotten investor backing that are attempting to create launch vehicles comparable to the Falcons. And that is why I think Musk is moving ahead to make his own Falcons obsolete. I think that Poland is a country that might be a place where entrepreneurial space can take off. You have a highly skilled workforce, and while I'm sure Poles don't appreciate the fact that their pay scale is lower than Americans, it certainly would benefit any launch company developing a new launch system not to have to pay California wages. And so who knows? There could be a Polish SpaceX.
Some bold predictions there. What kind of technology would we need to be able to create a space station next to Saturn, which we could live in and exploit the nearby moons or perhaps asteroids?
Well, developing the launch systems, one huge need that there is right now for space development is space nuclear power. On Earth, energy is the key to everything, but on Earth, you can have fossil fuels, you can have waterfalls. Yes, you can have nuclear power, but you can also have solar power and wind power and all these other things. If we move out to Mars, there's no fossil fuels other than those that you make with another power source. There's no waterfalls. The wind is too thin to matter. Solar energy is only 40% as strong as Earth. We need nuclear power. And if we go out to Saturn, where sunlight is only 1% as strong as it is on Earth, and of course, if you go into interstellar space, sunlight is negligible. Now, the vast majority of the universe needs nuclear power for its development. And while we can have a space station orbit around the Earth powered by solar energy, you cannot have one orbiting Saturn doing that. So I think that a key technological development needed to develop the universe beyond Mars is space nuclear power.
Next up, Robert, can comparative paleontology research on Mars samples that are being currently collected by Perseverance help us understand how to prevent global warming and climate change, as well as how to survive on Earth?
Well, actually, we might learn some things about climate change by studying other planets. We actually got our warning about global warming by studying Venus. But the main thing we're going to learn, I think, by the exploration of Mars vis-a-vis biology is what is life, because I think there almost certainly was once life on Mars, and there probably still is underground. And while I don't think the sample return mission can return samples of underground Mars water, human explorers can. And then we get to see what the code of life elsewhere is like. In other words, all Earth life uses the same alphabet. Okay, it's like I'm an American, we use the Latin alphabet. You're a Pole, you use the Latin alphabet. But they have an origin in Rome, the Roman Empire, the Roman Church spread that alphabet. Now, if you go further away, though, you find different alphabets. The Russian alphabet is slightly different, and the Chinese alphabet is radically different. It works on totally different sets of principles, and but it does the same thing. It records information, you can write books in it, just as you can with the Latin alphabet. And so, the great science of the 21st century will probably be biotechnology. We're learning to read the genetic code. We're learning to program the genetic code. And what are microorganisms but self-replicating machines programmed through the genetic code? Okay, and now, but we only know one alphabet here. It's like people whose knowledge of computers are Babbage machines that work with gears and levers to do computations. You could go beyond that to vacuum tubes and then silicon, and you have all sorts of much greater capabilities become possible. I think that learning about Martian life, learning about what the possibilities of life's information systems are, will enable us to create the far more robust sets of technologies, including possibly programmable microorganisms that can control climate change, and both on Earth and to enforce radical climate change in the interests of life on Mars.
Robert, after the great success of MOXIE, what is the next step for ISRU demonstration on Mars and the Moon?
Well, there's difference. Moxie, the next step for Mars really is to create systems that make methane and oxygen bipropellant on Mars, making use of Martian CO2 and water. And I think we can do this on a significantly larger scale, much larger scale than Moxie. We could start doing it with making propellant for ascent vehicles for sample return. But of course, the real need here is for much larger ascent vehicles. The Starship Mars architecture requires making like 1,000 tons of methane oxygen propellant on the surface of Mars. It is not a practical architecture without in situ propellant, and the raw materials are there. The moon is tougher because the moon does not have carbon dioxide, and the water, far from being widely prevalent in the way that it is on Mars, where you have glaciers as far south as 38 north, which is the latitude of Athens on Earth. The moon only has a little bit of water and some permanently shadowed craters near the poles. The most widespread source of oxygen on the moon is in the form of iron oxide rocks. I think we need a demonstration mission. I think Artemis, the NASA program, should fly a demonstration mission to demonstrate a lunar oxygen in situ experiment, LOXI. And in fact, my company, Pioneer Astronautics, is working on a prototype for such a thing.
It appears that some of the readers of your book like a somewhat sentimental perspective as well. Next question is, if you were to go to Mars, what is the one thing you would take from Earth as a souvenir?
Well, that's an interesting question. What's the one thing that I would take from Earth? If I could, I'd take my dog Strelka. Because she's my best friend. Now, if I couldn't manage that, I'd probably take this chess set that I've had since I was a kid.
Wonderful answer, thank you. Another one is a bit longer. When standing on the brink of a climate catastrophe on Earth, is it realistic to plan the construction of Earth settlements on Mars, or maybe building Marshall settlements on Earth in the first place would be a better solution? For many of the hundreds of millions of people who may or will be forced by climate change to live in Martian colonies on Earth, colonizing Mars will be like moving from Florida to Alaska. A bit far away, dry and cold, but nothing out of the ordinary. There will be slightly different external conditions, but the lifestyle and functioning of somewhat isolated communities based on community principles and self-limitation of their needs, mainly to those that they can satisfy themselves using local resources, will not change much, especially if they have the constant support of these Martian colonies on Earth. Is such a scenario as one of the alternative methods of Mars colonization likely?
Well, I have to take issue with the question. I believe that climate change is real, and dealing with it will require certain technical solutions that need to be implemented in the 21st century, including the widespread use of nuclear power. Unfortunately, the so-called environmental movement has made it a prime objective to stop the use of nuclear power, and thus, in fact, they are the main cause of carbon dioxide-driven climate change. But the real issue here is this, that even if climate change is not stopped, the climate's warmed 1 degree centigrade in the past 150 years. If it warms another degree centigrade in the next 100 years, or 2 degrees centigrade, that's not an existential threat to humanity. That is going to be some problems. Venice will have to deal with flooding and things, but that's not an existential problem. The existential problem that humanity faces today is the possibility of global war, caused by the belief that resources are limited. We are not threatened by there being too many people. We are threatened by people who think there are too many people, okay? And people who wish to have that mindset to support their ambitions. You look at the 20th century, Hitler, he said, the laws of existence require unlimited killing so that the better may live. He wanted to do some killing, and so he said that resources were limited. In fact, he said that this idea that we can expand resources infinitely through scientific progress is some kind of a Jewish plot to undermine the people's belief in the necessity for war. Well, I don't know if it's a Jewish plot. It isn't, although, of course, people of every nation, including Jews, certainly participated in science. In it, but the issue is yes, the belief in scientific progress does undermine the people's belief in the necessity for war, and that is precisely what we need to do. Okay, we need to do precisely what people like Hitler feared, which is to undermine the belief that resources are limited. And that is the case for going into space.
That's a very interesting perspective right there. Thank you, Robert. 4 more questions left. The next one is somewhat related to the previous one. What are the benefits of analog missions and analog habitats?
Well, there we can practice how to live, work, explore on Mars. We should, to the extent we can, attempt to practice this in advance. You know, I mean, in any theater company, they do dress rehearsals. Any competent military does field exercises in which they try to figure out how to use all their equipment and so forth. And that's what we should do with respect to Mars. And now, these things are not perfect, just as a military field exercise is not perfect. A military field exercise may involve moving tanks and helicopters around, but it's very different from real war because there's nobody trying to kill you. Okay, doing Mars field exercises on Earth is very different from doing it on Mars because the environment is not lethal and it's much more forgiving. But nevertheless, no competent military would think of not doing field exercises to prepare itself for the real thing. And just in the same way, no competent space program should consider not doing analog exploration on Earth to prepare itself for Mars.
Thank you. Another interesting one. Currently known bacteria, plants, and animals are not adapted to terraforming virgin planets. Their adaptation is adjusted to life on Earth. Could the microorganisms preserved in the glaciers, which are now melting and releasing them, as pioneers of terraforming the Earth, be used to transform the environment on Mars, the environment of Mars and other planets? How do you think?
Well, yes, I do believe that microbes could help terraform other planets. Microbes are actually the creatures that terraform the Earth. There'd be no oxygen in Earth's atmosphere until photosynthetic microbes put it there. There'd be no soil on the continents. Now, in terms of terraforming Mars, there may be certain things we need to do through physical chemical technology, like greenhouse the planet with fluorocarbon gases to warm things up, to create a thicker atmosphere, and which will make it possible to have liquid water, which microbes need to prosper. But then microbes can certainly do certain things. They can produce methane, which is a greenhouse gas, which is, on Mars, we want to do global warming. And so we're learning a lot about the mechanisms for doing that right now on Earth. But we may want to do things with microbes that do not currently exist. And I think that this new science of biotechnology, of learning how to program organisms, the people have written science fiction about nanotechnology, miniature machines you can program and to do things, and they're also self-reproducing. Well, microbes are nanotechnology. They are the real thing. It's just that up till now, they've done their own thing. And if we can learn to program them, then we can use the tremendous powers they have as self-reproducing micro machines to alter planets and make them better homes for life.
Robert, 2 more questions left, and we've already run out of time. So can we try a quick answer to 2 complex questions? The first one is easy. Which not as complex. Which of the visions presented by the most famous science fiction films comes closest to being fulfilled in the next 100 years? What would you choose? Which one?
The only science fiction film that that I'm acquainted with that's actually been done in a spirit of realism would be The Martian. Although I think we need a better film, one that does not just somewhat realistically depict Mars and show the can-do spirit of the astronaut, but also makes clear why we need to go to Mars. That conveys not just the peril of Mars and the challenge of Mars, but the wonder of Mars. That one has yet to be made.
And the final question, you assume that in the next 10 years we will send the first people to Mars. This means that relatively little time is left for the teams participating in the ERC, young engineers and enthusiasts, as well as the next generation of children who follow them. It is them who will create this new world, and it's time to start preparing for this challenge. What is your message to them? What directions should they be educated in? What skills and character traits should they develop?
Well, okay, first of all, as far as the university students participating in the ERC today, they're right on time. This is the decade in which humans are going to reach out to Mars, and their careers will begin shortly. They are here now. They are present at the creation. They are incredibly privileged. And as for those that are in high school or elementary school today, I would say learn all the science you can, because we're not living at the end of history. We're living at the beginning of history. Okay, history begins at the point when humanity leaves its cradle and goes out into space, and that's what's about to happen now.
And we truly couldn't hope for a more inspirational closing of our conversation. Robert, it's been an absolute pleasure and an honor to have you with us here at ERC. Thank you for finding the time to join us.
Okay, it's been my pleasure. I wish I could be there in person, but it was impossible this year. Good luck to everyone at the ERC.
Ladies and gentlemen, we very much recommend Robert Zubrin's most recent book, especially now that it has been already translated into Polish and released by PWN. And now we are joined by Ms. Amy Montserrat, U.S. Consulate General, Kraków. Madam, would you kindly join me on the stage, please? Yes. Much welcome.
Thank you very much. Ladies and gentlemen, Szanowni Państwo, it is a great joy to be a part of this incredible event today. The U.S. Consulate General has been involved in the European Rover Challenge for many years, and we appreciate being a partner of such a truly unique event. This year, the American presence is expanded with the exhibition From the Moon to Mars, which just opened, and I encourage everybody to take the opportunity to tour the display later today outside this room. I am particularly pleased to be here because my previous career, before becoming a diplomat, was connected to the space sector. I'm an astrophysicist, and many years ago, I worked at NASA Goddard Space Flight Center on X-ray detector development. And I launched scientific sounding rockets with partners from all over the world, including Japan and many countries in Europe. I know personally how impactful science collaboration can be, both for scientific discovery and for global cooperation. As a result, I am incredibly privileged today to introduce to you the Associate Administrator of NASA, Mr. Robert Cabana. Prior to this position, Mr. Cabana was director of NASA's Kennedy Space Center in Florida, and was a NASA astronaut. Born in Minneapolis, Minnesota, Mr. Cabana graduated from the U.S. Naval Academy with a degree in mathematics and served in the United States Marine Corps. In 1981, he graduated with distinction from the U.S. Naval Test Pilot School. During his career, Mr. Cabana logged over 7,000 hours in 50 different kinds of aircraft. Mr. Cabana was selected as an astronaut candidate in 1985 and is a veteran of 4 space flights, during 2 of which he was mission commander. Mr. Cabana's many achievements have been recognized with induction into the Astronaut Hall of Fame and numerous awards and distinctions. And now, let's welcome astronaut and NASA Associate Administrator, Mr. Robert Cabana.
Well, thank you so much for that warm introduction. It is such a pleasure for me to be here to speak to all of you at the European Rover Challenge. I wish so much that I was there in person instead of talking to a computer screen. But I think I got a pretty good presentation for you guys today. And just remember, rovers are the precursors to sending humans out when we go explore. And we're going to talk more about that. I think you heard a little bit about my career, but man, I have been blessed. I have gotten to do so many amazing things. But for all you students out there, it all comes down to hard work and doing your very best at whatever you do. And remember, if you don't get something on the first try, don't give up. I didn't get into pilot training, test pilot school, or the astronaut program on the first try, but they were things that I was passionate about, and I kept on working toward it. It also helps if you really like what you're doing. And I know all you folks working on teams for the robotics challenge, you love what you do, and that really helps. I love math and engineering. I love flying. I was passionate about it. And when you're really passionate about something and you like it, then studying's not hard and you do well at it because you enjoy it, and work's not work. And I've hardly worked a day in my life because I've had this amazing career in the United States Marine Corps. And since 1985, for the last 36 years now, working at NASA. And NASA is just an awesome place to be. So let's talk a little bit about where we're going and what we're doing. So I want to tell you about the Artemis program. Now, Artemis is the twin sister of Apollo, and this is the program that is taking NASA back to the moon. But we're doing this different than we did during Apollo. We're not going for a 2 or 3 day camping trip. We're going to go in a sustainable way. We're also going with our international partners and in partnership with commercial companies. And that's the difference this time. And it is absolutely amazing. So let's talk a little bit more about the parts of Artemis. So Orion is the capsule. This is built by Lockheed Martin. And this is the Orion capsule for the Artemis 1 test flight. It's in the launch abort system facility right now, having the abort motor put on it. and then it's going to be shipped over to the vehicle assembly building to be stacked on top of the Space Launch System rocket. And it's going to fly its first test flight, hopefully by the end of this year, but early next year, to the moon without a crew. And we'll talk more about that. And then this is the vehicle that's going to allow us to go into deep space to explore, not only to the moon, but one day going on to Mars. So the Space Launch System, this is the most powerful rocket ever built. And if you look at the solid rocket motors on there, these are essentially the same solid rocket motors that we use for the shuttle program, except one thing I want to point out is if you look at those casings that are on there, where those black lines are, these are 5-segment solid rocket motors as opposed to 4 that were used for the shuttle. And the engines on this are the same engines we used during the shuttle program, but instead of 3, there are 4 of the RS-25 engines. These are the most fuel-efficient liquid rocket engines in existence. The tank holds hydrogen and oxygen. That hydrogen is the fuel, oxygen is the oxidizer, and then the interim cryopropulsion upper stage, in the picture on the left, in kind of dark right there on the crane, that's the upper stage that's being stacked on top of the rocket. You can see the rocket on the mobile launcher in the vehicle assembly building, and then the command and service module that you saw in the previous picture will get stacked on top of that. Going to be absolutely amazing. So if you look at, again, another shot here, you notice that that silver module on top, that's actually a mass simulator for the Orion capsule and the launch abort system. And right now, the Space Launch System is going through modal testing in the vehicle assembly building, and that's a mass simulator until we get the actual capsule on top. They're doing a test of all the swing arms and umbilicals. You can see the platforms all around the rocket, but eventually those platforms will be rolled back, and in November of this year, it will roll out to launch pad 39B, and you can see the mobile launcher when it was out on the pad for testing, only this time it's going to roll out with the rocket on it, and we're going to do a full wet dress rehearsal. We'll learn from that wet dress rehearsal, and hopefully a month later, we will be launching Orion and SLS on a test flight to the moon without a crew in preparation for a crewed flight in 2023 to the moon, and Artemis 3, hopefully in 2024, 2025 timeframe, where we actually land on the moon again with the first woman in the Artemis program and first person of color. Artemis is going to take a diverse crew back to the moon when we go. All right, next slide. So when we get to the moon, we got to be able to get down onto the surface of the moon, and we need a human landing system. And so we are in the process right now. You can see Apollo on the left side of the screen, and a representation of what the human lander with the will look like when we go land on the Artemis program. But we're in the process of working with our commercial partners to develop this lander now to have it ready when we go to the moon. Gateway. So I said when we go to the moon, we're going with our international partners. Now, we've already let contracts for the power propulsion element, and what you see on the left side of the screen there is the solar electric propulsion test at the Glenn Research Center up in Ohio. This is the propulsion element for the PPE, and the HALO, the Habitation and Logistics Outpost. But also on the Gateway, I said we're doing this with our international partners, it's also in partnership with Canada, Japan, and the European Space Agency. And the Gateway will be in this near rectilinear orbit, this extreme orbit around the moon that allows access anywhere on the lunar surface. So we're well on our way, and the HALO and PPE are scheduled to launch in 2024. Now, the Artemis Accords, these are a set of principles that so far we've had all the countries that you see down below, all the space agents below, have signed up to the Artemis Accords. And these commit to common principles for working on the lunar surface in a peaceful, successful cooperation. And we're hopeful that the Polish Space Agency will also be signing these accords as we move forward. I also want to mention the International Space Exploration Coordination Group, the ISEG, and also the Global Exploration Roadmap. Now, together, 23 space agencies are participating and have signed up to this. And this is a non-binding forum where the space agencies share what they are going to do as we move forward in space. And we learn from one another. And then in 2018, the group published the third iteration of the exploration roadmap to foster cooperation and partnership opportunities as we move forward and explore. And we are very pleased that the Polish Space Agency is one of the partners in the ISIG. So when we get to the moon, we're going in a sustainable way. We want to use the resources on the moon, but we have to explore, and we want to get all over the moon. So on the left, you see a picture of the lunar rover that was used on the Apollo 15, 16, and 17 missions. But on the right, we're going to build a new lunar terrain vehicle. And this rover is going to be able to carry astronauts a distance of 20 kilometers per charge, and it's going to last for 10 years. But we want to go even further than that. So we are also building a pressurized rover. And you can see a mock-up out in the desert of what one concept is that we've been testing with astronauts. But on the right, you see what we want to build. And this will carry 2 astronauts in a pressurized compartment where they can actually live on the moon for 30 days. It's designed to last 15 years, and it will be able to travel 40 to 60 kilometers on a charge. So commercial lunar payloads. This is a partnership with American companies to deliver payloads to the lunar surface for science, exploration, and commercial development of the moon. And what you see on the left, that is the drill for the Viper spacecraft that's going to go to the south pole of the moon. And on the right, you see the Viper rover. This is looking for water on the moon. And we know at the south pole of the moon, there's tons of water ice. And water is hydrogen for fuel. It's oxygen to breathe, oxidizer to burn the fuel. So again, if we're going to go to the moon, we don't want to have to carry all our fuel and everything there. We want to utilize the resources on the moon, in situ resource utilization, for these extended stays as we move forward. So Viper's going to evaluate and find water on the moon. And these other CLIPS missions, they're going to start in 2022, and then 3 and 4. And these are all commercial companies that are going to different areas on the moon with different payloads to learn and explore as part of our Artemis program. And here you can see just pictures of what these different payloads are that these companies are putting together for the science. Rovers. You know, you guys are learning about rovers. I think it's outstanding. I love the competition. It's something that's really neat. I love going to FIRST robotics competitions here in the United States and seeing all the different concepts that you guys come up with to meet the challenges that are assigned to you. This to me was amazing. This was pictures from the Perseverance rover, Mars 2020. This was launched from the Kennedy Space Center in July of 2020. And February of this year, it landed on Mars successfully, and it's been absolutely amazing. And rovers, again, they're the precursor to sending humans, these robotics. So the ultimate goal is to go from the moon to Mars, getting a human presence beyond our home planet in our solar system. And we're going to the moon to learn all that we need to know in order to be successful when we go to Mars, as well as, you know, just the exploration of the moon that's going to help us learn more about our home planet and how to better protect it also. But the goal is Mars. You can see Perseverance, Mars 2020 on Mars, and to the left in the picture, you can see the Ingenuity helicopter, and that is so cool. This is the first time that we've flown a vehicle on another planet, and it has gone out and searched out things for the rover to go see. The other thing that Perseverance has done, it recently took its first successful sample. So it's going to various sites on Mars, collecting different samples. And we're looking to see if there was life one time on Mars and learn more about Mars. So these samples are being collected, and then eventually again, in partnership with our European partners, we are going to be returning these samples on the Mars Science Return Mission to Earth. So this is kind of a cool picture, and it just shows the evolution of the rovers on Mars from the beginning, from very small to the Mars sample return. You can see it having collected the samples, launching to rendezvous with a spacecraft to bring them back to Earth. And all of this is in preparation for bringing humans to Mars one day. All right, with that, I'd like to pull this to a close, because what I really want to do is be able to take your questions. Human on Mars, that's the goal. And if you want to learn more about any of this, nasa.gov/Artemis for more information. And there's a wealth of information out there. But if we could stop the presentation, I'd like to pull up pictures of my audience and be able to take your questions now. Let's see, I'm not hearing anything. Can you guys, do we have a moderator? Let's see, testing. Can anybody hear me? Gosh, I sure hope that worked. Anyone there? Okay, I'm told I just got a text that I can be heard. Is there any way to get me questions for the group? I can see the studio, but I cannot hear the moderator. All right, I understand that y'all can still hear me.
Hopefully we can establish a sound bridge with the United States. Can you hear us now, Robert? No.
Okay, now I can hear.
Now you can hear us. Bravo.
Excellent.
Wonderful. Maybe a round of applause for Robert, ladies and gentlemen.
Okay, I know I went through that really fast.
You should have heard this one.
I wanted to leave time for questions.
It's a lifetime of wonderful achievement, Robert. Congratulations and thank you for joining us today. And we decided to surprise you with the very first question coming from the youngest member of the team, an 11-year-old boy who has already built his first rover in his life. That's quite an achievement, you will agree, I'm sure.
Excellent.
All right, where do we have the gentleman who would like to ask the question? To pan chciał zadać pytanie, tak?
Hello, Mr. Cabana. I'm Simon, and I'm a student of Children's University of Technology in Kielce. Because of Starship will be used in the Artemis program, what do you think about the lack of the escape system in Starship?
I'm sorry, the lack of what?
Of the escape system in Starship.
Well, I'm sorry, I'm having a little bit, I probably should have had...
The question is, what do you think about there being no escape system or escape provisions in the Starship solution?
So first off, the Starship that's being built, you know, right now, SpaceX is using that to be the lander, the human landing system. That is, they've won a contract to build that to demonstrate a landing on the moon with that. But it will not have humans on it when it launches for the NASA mission. It will be in orbit around the moon, and then the Orion capsule will fly to the moon and dock with the lander and land on the moon and come back to Orion to fly back to Earth. So obviously before SpaceX can fly humans from Earth on the Starship, they're going to have to demonstrate reliability to prove that they have a safe vehicle to fly on. So that's a ways down the road right now. But from a NASA point of view, we are going to ensure that when it is certified to fly as a lander on the moon, and we rendezvous with it, that it's as safe as we can make it. It will have already demonstrated that it can accomplish its mission without a crew, an uncrewed demonstration of landing on the moon, and then a crewed landing. So a lot of work yet to do on that, a long ways to go.
And let's all hope that the mission abort, in any sense of the word, will not be needed. We've got a lot more questions coming from the room, Robert, so let me give it a try.
Thank you for this opportunity. I have a question. Well, you mentioned that there is a lot of international collaboration regarding Artemis program. So the question is there any plan for Europeans to visit the moon as well, together with American astronauts?
Absolutely. So as we go in this cooperative effort, this International Space Station has been a tremendous model for how we operate together in space. You know, we have the United States, Canada, Japan, the European Space Agency, and all its partners in Russia working together as one up there on the International Space Station. We've had our international astronauts be commanders of the International Space Station. So as they contribute to the International Space Station, they will also contribute to the Gateway, and they will also have their astronauts flying on the Orion spacecraft to the moon and going down to the lunar surface and being part of the exploration of the moon. So absolutely, our European partners, our partners Canada and Japan, are a part of what we are doing. And I think the International Space Station is a tremendous model for how we explore beyond our home planet. You know, in spite of all our political differences here on Earth, we're working together as one up there on the International Space Station. So absolutely.
Well, any idea if it will be like a first surface mission or some mission along the way?
It's too early for me to say. We're still working on all that. That's some years down the road, so I wouldn't be able to say exactly who and when.
You could see the video of the room we're sitting in and the number of people in this room. I should perhaps inform you that these are only the people who actually want to ask you questions today, because there is a large crowd in the Mars yard and in the Rover playground, so to say, right outside, because it's a beautiful weather also. So these are only the people who want to ask you questions. Make yourself comfortable.
So, Robert, my question involves ISRU. We know that in the short term, the lunar ISRU mostly revolves around getting water from the lunar ice and not even extracting oxygen or hydrogen from the regolith. But in the longer run, it actually revolves around the similar idea of OSAM, the on-orbit servicing, assembly and manufacturing. So those space mining, as we call them, technologies would actually, I don't know, how do you think? Would they tie in with the principle of the Artemis Accords, not the space resources principle, but the principle of remediating and mitigating the threat of space debris? For example, would it be easier to use the similar smelting techniques to break up space debris, space junk and wreckage that we would use on rocks, and not, for example, trying to burn upon re-entry some lunar space junk, as we know that the moon doesn't have such an atmosphere to burn up on re-entry, and sending it back to Earth to burn up on re-entry would be something that even Robert Heinlein wouldn't pull out. What do you think?
So that's an absolutely excellent question, and I will be honest, I would need to consult with some of my experts in that field and get their thoughts on it. I wouldn't want to comment and say something that wouldn't be technically 100% accurate. I can tell you in situ resource utilization as we go back to the moon, I mean, taking care of trash is a huge problem. But we are doing more than just gathering water for hydrogen and oxygen. We're looking at additive manufacturing on the moon, actually using lunar regolith to build shelters on the moon. So we have so much more that we need to learn. And that's part of the reason for the CLIPS program. As we go to the moon and we work with our commercial partners to gather this knowledge, we will be able to lay out a better plan as we move forward, doing this in a sustainable way.
Thank you.
So we pass the microphone for the next question. I've got a really easy one for you, Robert. When are we going to have the "It's a one small step for man" moment on Mars? Give us the year and the month. You don't have to give us the day.
Oh, I think, hopefully by the late 2030s, early 2040s, we will be on the Martian surface. Nothing ever seems to happen as quick as we would like. It's a huge challenge. A Martian mission right now, with our current propulsion technology, you're talking 6 to 9 months to get to Mars, another 6 to 9 months on Mars for the planets to align, for another 6 to 9 month trip home. And studies I've seen say that before we can send humans, we have to actually pre-stage like 18 metric tons of supplies and equipment in order to keep them alive for that period of time and be successful. Look at when we landed the Curiosity and Perseverance rovers, that was like 1 metric ton. And that was a huge challenge to do that. So we still have an awful lot to learn and systems to develop if we are going to be successful when we go on to Mars. And I think there's 2 really big drawbacks. Of course, one is the time it takes to get there. New propulsion technology would be absolutely outstanding. And we're looking at nuclear thermal as well as nuclear electric in order to provide new propulsion other than just pure chemical propulsion. And protecting astronauts for these long trips to Mars, the radiation environment that they have to be in is also another factor that we have to consider. So a lot left to learn before we can actually get on to Mars. And hopefully we'll learn a lot of that, developing the systems, the reliable systems that we need as we go to the moon, and how we operate away from our home planet for an extended period of time. And it's a lot better when you have problems to be 2 or 3 days from home on the moon than when we go to Mars. So we still have a lot of work to do. But I would, if I had to give my best guess, I'd say in the early 2040s, we will have humans on Mars. But it could happen sooner.
Thank you very much. We've got another question. Yes, madam.
Yes, thank you for this opportunity. I'm Paula from Lunaris Research Station. And how do you find balance between the innovation of new space companies like SpaceX and Blue Origin while maintaining the safety standards NASA is known for?
Whoa, thank you, Paula. So first off, people talk about space. They talk about new space, commercial space, government space. And the truth of the matter is there's only one space above us, all right? And if we are going to be successful, we need commercial and government integrated together. And we need all our partners working toward solving our problems. Innovation, competition drives innovation, and we constantly see these new startup companies being more and more innovative, doing things in a more cost-effective and efficient manner. So, we balance as best we can in how we award our contracts, making sure that they meet our needs in order to be successful as we move forward. So it's a constant, iteration as we move forward, trying to select the best that we can for what we need to do at the most cost-effective and efficient way. But I fully support this government commercial cooperative effort that we have as we move forward.
Robert, a few more questions. Łukasz is next. Hello.
Hello, Mr. Cabana. My name is Lukasz. I'm the European Rover Challenge founder and organizer. And I have very easy and hard question for you at the same time, because I'm being asked for the last couple of days why we need to go to Mars, because we have a lot of problems on Earth, a lot of things that we have to solve here first. And what are we escaping the planet, having plan B? So actually, this is a very important question, why we need a space sector at all. Thank you.
Absolutely. Well, first off, you know, every dollar that has been spent on the space program has not been spent in space. It's been spent right here on Earth, making life on Earth better. The technology that comes from our exploration constantly improves our life on Earth and helps us solve problems here on Earth. So this technology is critical to our future. When I got selected to be an astronaut, I worked for Captain John Young. He was chief of the astronaut office, and John was one of my heroes. He flew the first Gemini mission with Gus Grissom, twice on Gemini, twice on Apollo, walked on the moon, flew the first shuttle mission, and then flew the first Space Lab mission with the shuttle. And John used to say, single planet species will not survive. At some point in our future, there's going to be an event like the one that took out the dinosaurs. And if we are not prepared to live off our planet and be ready for that, you know, we as a species will not survive. Well, that sounds kind of grim, but I do believe that we need to establish a presence in our solar system beyond our home planet. It's our destiny to explore, to continue to learn. And as good as robots and rovers are for exploration, they still can't match what we can learn when we send humans. So I truly believe we need to learn to live off the planet Earth. I don't know how many of you guys have watched, I'm kind of a science fiction fan also, and there's a series called The Expanse, and it shows, it's off in the future, and it shows people living on Earth, living on the moon, living on Mars, living in the asteroid belt and mining it. And to me, that's the future. And we're going to continue to learn, to expand, and make that happen.
Thank you, Robert, for turning this question into a positive, optimistic direction eventually. Any more questions, ladies and gentlemen, I'm sure? Yeah.
Okay, can you hear me, Robert? No, you probably can't hear me. Okay.
Well, I can always borrow my microphone.
Hello, Robert. It's me again, Kamil, the guy from the ISRU question. I would first like to add to the thing you said about the whataboutism when we post, for example, environmentalism against space. Every time somebody tells me that we should focus on the climate and not on the space ventures, I say, okay, fine, but please don't use satellite data when you're discussing or bashing climate denialists. But my question about the rovers is one thing. You said that we would need to put several metric tons of supplies to have people on Mars. Similarly, we will have to build shelters for them, and this is near impossible with today's signal lag between Earth and Mars. So what would you say, for example, for putting a computer core with, not say an AI, but several programs that would actually operate a handful of rovers as a swarm intelligence on site without the computer lag, similarly that we have IoT and cobots?
Wow, that's a very interesting concept. I would be interested in learning more about that. And again, I would get my my really good scientists and engineers together and evaluate it and come forward with a plan to see if that's feasible. You know, anything, that's the amazing thing. Look at how technology has changed. Unfortunately, as we plan these missions, you know, we're planning a mission right now for the Mars sample return, right? In 2021. And it's probably not going to bring that sample back until 2031, 2033, you know, 10 years from now. But think about how technology is going to change in the next 10 years and what's going to be available. So I think we got to continue to grow the technologies and to learn, and then figure out how we can apply them as we get on some of these challenging conditions. I would also say, you know, going back to what you said about climate change, you know, I think what we do, obviously, taking care of planet Earth is, you know, a #1 priority for all of us. I've had the privilege of looking down on the Earth from a couple hundred nautical miles high, and it's amazing. I mean, you see the curvature of the Earth about like that, with this thin little hazy line over it. That's our atmosphere. That's all that's protecting us from that harsh void of space with its ultraviolet radiation and extreme temperatures. And space is the darkest black that you can possibly imagine. But our home planet, Earth, it's just this beautiful blue jewel of a planet. And there's no place close by that matches it, that's as nice that we can live on. So we definitely have to take care of it. And the NASA science missions, that the satellites that are monitoring our Earth, that are measuring the climate changes, that are measuring, you know, the atmosphere, that are looking at the oceans, you know, they are critical to our understanding of what's going on and how our planet is changing. And so it's very important that we focus on our home planet as well, and space helps us do that.
Robert, you've been on 4 space shuttle missions, if I'm not mistaken. You've also held some of the most important management roles in the space exploration industry over the years. My quick question to you is, can you think of one moment where you found human creativity absolutely mesmerizing in finding a solution to a challenging problem? When I think about it, and when we think about the rover landing on Mars and turning it into a bouncing ball until it eventually lands. So I'm thinking about something like that. In your career, in your experience, do you remember facing a problem that looked completely insoluble at first, but then someone found an out-of-the-box solution which was mesmerizing?
Wow, that you're making me think hard. First off, I believe in the human spirit and our ability to conquer and solve any problem, and we are amazing. What we can do if we focus and work together as a team it's awesome. And that's why diversity and inclusion are so important. You know, it's that diversity of thought. It's bringing a team together from different backgrounds, diverse backgrounds, that can, you know, everybody brings something different to the table. And to get the best solution to a problem, when you have all these different minds and different backgrounds working together, you are going to get the best solution. I believe we can solve any problem if we work together in an inclusive environment to make that happen. You know, there are so many technical advances, and it boggles the mind, and it's changing so quickly. It's hard to keep up with it. And I think it's incumbent upon all of us to continue to learn and grow. Even when we get old like me, you know, you got to continue to keep learning and moving forward and staying up with technology. I think what impressed me more, if I look back on my career, it's not the technical things that have impressed me or the solutions to the problems. It's what I've been able to see from different perspectives, you know, as an astronaut, as a pilot, and the beauty of space, the beauty of planet Earth. You know, when I look at, I guess if I could pick one scientific achievement so far that has been absolutely amazing, it's the Hubble Space Telescope. One of my favorite pictures, it's called the Hubble Deep Field. And everybody knows what the Big Dipper looks like, Ursa Major. And if you take the cup of the Big Dipper and you put your finger up in the night sky underneath the handle, between the cup and the handle, and look at your little fingernail, all right? And Hubble took a picture. There's nothing there. It's black. No stars, nothing. And Hubble took a picture of an area the size of your little fingernail, holding it up like that. And what it found were not only hundreds of stars, but hundreds of galaxies, all right? Think about how vast our universe is and what we have learned from the Hubble Space Telescope. And we're getting ready to launch another telescope now. It's the James Webb Space Telescope. It's going to be launched on an Ariane 5 rocket from French Guiana down in Kourou the middle of December 17th, 18th timeframe. And James Webb is this amazing observatory that's going to be out in L2. And it is going to see back 13.5 billion years in time, 350 million years from the Big Bang. That's how far it's going to be able to see back in time. And this is going to be absolutely amazing what we are going to learn. And I look at what has come from Kepler and our other planet observatories. We have found not one or two, but hundreds of planets that are in the Goldilocks zone, not too close or too far away from a star that could have an Earth-like environment. So I just think it's so important that we continue to learn and gather knowledge. And so I'll throw up Hubble as something that has truly advanced the knowledge of our universe.
Robert, if one of your goals was to redefine the words mind-boggling or unimaginable in a short statement like that, I believe you did it. We've got more questions from the audience. Sir.
Hello. Robert, what do you think about the idea of cooperation, United States and China, in case of exploration and exploitation move, and in case of exploration and exploitation to Mars? Do you think it will be mutual beneficial on, or only partly one-sidedly beneficial, only for China or only for United States? Thank you.
So right now, by law, we are prohibited from partnering with China in our space exploration efforts. But we still share knowledge about our home planet on various science missions and stuff. So I'm going to decline to offer a personal opinion on that, and I'll just stick with our current government position, which is we are not partnering right now with China. Could that change in the future? That's always possible.
Thank you very much, Robert. We've got more questions from the audience. I think Piotr is the nearest one, and then we've got another gentleman. Piotr.
Hello, Robert. I have a question about ISS. What about our space laboratory? Is it a finale, or should we look forward for some other cooperation between different nations? Are you going only for the moon and Gateway, or what are you up to?
Okay, so our goal is to commercialize low Earth orbit, to create a commercial economy in low Earth orbit, and where we can be one of many customers as opposed to owning and operating the entire laboratory that's up there. And then we can focus on that hard job of exploring beyond our home planet. So the International Space Station, it is going to come to the end of its life. And right now we're looking at the 2030 timeframe. So we are trying to establish a commercial destination. And we're working with a company, Axion, to have a commercial module on the space station. And eventually, they're going to have their own commercial space station. Sierra Nevada is another company that is looking to have a commercial destination in orbit. Right now, in establishing this commercial economy, we have SpaceX, Northrop Grumman, and Sierra Nevada that are on contract to fly cargo to the International Space Station. They provide that service. We have SpaceX and Boeing flying crews to the International Space Station. Boeing still has to fly a successful uncrewed and crewed test flight before they carry crew. But right now, the International Space Station is the only destination. So we also want to have a destination for these companies to continue to fly commercially to space. And that would be a commercial space station once the International Space Station reaches the end of its useful life.
Robert, I've got some great news for you. You only need to bear with us 4 more minutes, please. Next question, please.
Okay, thank you. Hi, Robert. My name is Remco Timmermans. This year we're celebrating 60 years of human spaceflight, and obviously you were a big part of that. But now we see lots of people here, especially young children, who are looking to the next 60 years of human spaceflight. What can you give them as a message of their opportunities in space in the next 60 years?
I believe the opportunities are unlimited. You know, I think it's really interesting. So if you look, anybody that is 21 years old or younger in the world has never known a time that there were not humans living and working in space. Since November of 2000, we have had a permanent crew on the International Space Station. And that's our future, all right? We are going to continue to live and explore and go beyond. Technology continues to change and get better and better. Costs, we always are coming up with ways to be more cost effective and efficient, more affordable. I believe that anybody that has an interest in being part of the space program, of exploring in space, that there is going to be opportunity for them if they apply themselves, work hard in school, have a technical degree, have the skills that are necessary to come forward. And again, I go back to having that passion. You know, I never dreamed I could be an astronaut when I was a young boy. I held those astronauts in such high esteem. They were so much, I thought they were so much better or smarter than I was. I just wanted to fly airplanes, and I was fortunate to get to go to the United States Naval Academy. I took a commission in the Marine Corps. I became a pilot in the Marine Corps, and then I wanted to be a test pilot and use all the math and engineering I had in school along with flying. I got to become a test pilot, and that's what qualified me to be an astronaut. It was always something that one thing kind of led to another. And so I encourage all students, all young people, to have a goal. And don't give up when they don't get it on the first try, but make sure that you're doing something that you're passionate about, that you really believe in, and it's going to make life so much better and so much easier, and it'll really be fun.
Thank you very much, Robert. Anyone else wishes to ask the last question, or the last but one?
Hey, Paul from Lunara's research station. So with the barrier of entry being so high with technology to get into orbit and interplanetary travel, how can we ensure equal international playing field as we move forward over the next couple of decades? Thank you.
So I think that, you know, we are doing very well in the United States, bringing our international partners in, and more nations have signed the Artemis Accords. I think we want to look towards international partnership as we explore. I believe, as I said, the space station's an excellent model. I think that when we leave planet Earth and go beyond and establish this present, we need to do it in an international and cooperative manner. A trick question for you is, who was the first person to enter the International Space Station? And the answer is there was no first person. When it came time to enter the hatch on that first space station assembly mission, I pulled my crewmate, Sergei Krikalev, a Russian cosmonaut, up alongside me. And if you look at the pictures, Sergei and I entered all the hatches side by side. I felt that as an international space station, we needed to enter as an international crew. So I had the honor of being the first American, and he was the first Russian to enter the space station, but there was no first person. And I think as we move forward, you know, that's what we need to do, continue to work in that cooperative manner. Hey, I just want to say how much I really enjoyed talking to you all. I sincerely wish I could have been there in person. I wish you all the very best in whatever you choose to pursue in your lives. I ask that you work hard and do well at whatever you do. And we are part of the Artemis generation, right? We are going back to the moon in a sustainable way, and we're going exploring beyond our home planet. And I think that's an absolutely exciting future for all of us.
Robert, I'm not sure if anyone has told you that, but we are actually planning to organize future editions of ERC. So if that's the wish you want to see fulfilled in the future, you're very much open to it. One last question, call it inspirational or call it out of curiosity. Long before you started watching The Expanse, do you remember your very first thoughts and emotions on your very first mission to space? And could you compare them to your very last mission to space, both looking at the planet and the thoughts you had?
Absolutely. So my first ride into space, I just wanted to make sure I didn't make any mistakes. I was really focused on my job, and I'll never forget that ride on that rocket ship going up. It is just a sense of speed and acceleration. you're being pushed back in your seat and it's hard to breathe and it just gets up and goes. And when the engine shut off at about 7.5 minutes, about a minute before the engine shut off, you're being pushed back in your seat at a 3G acceleration. It's hard to breathe. And when the engine's shut off, you come forward in your seat. It feels like you stopped, but you just stopped accelerating. You're going 17,005 miles an hour and 5.5 miles a second. And I looked out the window, and at that point, you're about 65 nautical miles above the Earth, and you continue to coast out to your apogee, the high point of your orbit. But you know, seeing the curvature of the Earth was just amazing. And on that first flight, anytime I had any spare time at all, I just stuck my nose up to the window and made a memory. And I just remember this beautiful Earth, how privileged we are, you know, to be able to live on it. My last flight, it was more of the same. And I didn't know for sure it was my last flight, but I kind of figured it was. But I think I never got tired of looking at the Earth anytime I had any spare time at all. It's absolutely beautiful. And that I spent a lot of time doing that. But what I will always remember is how well that mission went from start to finish, and to be able to lay the cornerstone for the International Space Station, this huge international cooperative effort that has been so phenomenally successful on orbit. I had great pride in my crew and what we had accomplished, and I will never forget that sense of accomplishment and that pride in my team, the entire team, and what we were able to do. So I'm still part of what I think is the most amazing team anywhere, NASA. I'm extremely proud and privileged to be a part of it, and I look forward to continued success of our space program. Thank you.
I never got tired of looking at the Earth. Ladies and gentlemen, please remember this sentence and do remember it forever. Robert, thank you for being so wonderfully generous with us. Let's give Robert a round of applause, please. Robert Cabana, Associate Director, NASA. Once again, thank you, Robert. All the best. Stay healthy. What a conversation, ladies and gentlemen. Ladies and gentlemen, it looks like we're back on. What a question and answer session with Robert Cabana, NASA Associate Administrator. Now time for a discussion. The discussion of the date, Humans to Mars by Explore Mars. Here to take part in the discussion, Chris Carberry and Janet Ivey, Explore Mars. Jim Garvin, NASA Goddard Chief Scientist. Joey Cassidy, Aerojet Rocketdyne. Over to you, ladies and gentlemen. Enjoy.
Well, thank you. Good afternoon. I'm Chris Carberry. I'm CEO of Explore Mars, and thank you for the European Rover Challenge for this opportunity. I think I can speak for everybody when I say we wish we could be there in person. So maybe in the future years we can come there. We would very much enjoy that. For those of you who aren't familiar with Explore Mars, we're a nonprofit organization based in the United States, but we do a lot of international activities as well. You were probably best known for the Humans to Mars Summit. And for those of you who don't know, our virtual Humans to Mars Summit will be taking place next week on September 13th through 15th. So if you're interested in registering this year, and this year it's free, which is a first and hopefully a last, you can go to exploremars.org to register. Explore Mars also runs the Mars Innovation Forum events, do a lot of policy work, and thanks to the efforts of our president, Janet Ivey, who I'll introduce in a moment, do an extraordinary amount of successful STEM education work as well. So really excited to be here today because we are living in exciting times. Some extraordinary things will be happening over the next couple of decades, just a few of them over the next, even just over the next few years. You know, we're going to start the process of returning to the moon. Artemis 1 will be launching to do an orbit around the moon, an uncrewed orbit, later this year. But then we'll be soon followed up by crew missions, and hopefully we'll be landing humans back on the surface of the moon by the mid-2020s. Later this year, the James Webb Space Telescope is launching, the biggest telescope ever sent into space. So we will be learning things about the universe we have never even conceived of before, probably. Robotic exploration continues as well. As you know, this has been a very busy year for Mars. NASA, the United Arab Emirates, and China have successful missions that arrived at Mars this year, which will not only possibly change our whole perception of the nature of life in the universe, but are also key stepping stones to getting humans to Mars. So we're very excited about that, as well as upcoming missions from Europe with the ExoMars mission. Japan and India are also sending them, and many other countries are interested in Mars exploration and exploring other parts of the solar system. So this is a very exciting time for worldwide space exploration. And of course, commercial space is making rapid progress. I'm sure you all saw that Virgin Galactic and Blue Origin successfully sent suborbital flights recently. SpaceX is continuing to make their progress, and we are particularly excited with a SpaceX launch that is taking place next week. The Inspiration 4 mission. One of our board members, Dr. Cyan Proctor, there's Janice Hammond holding up the entire cover. The Inspiration 4 mission, Cyan Proctor is one of those 4 astronauts. So they're tentatively launched to be the first all-private mission into space. They'll be orbiting for 3 days at a higher orbit to the International Space Station, roughly the same orbit as the Hubble Space Telescope. So this is a really momentous time when we're truly getting the private sector into space. So we're very excited about that. But one of the hallmarks of what Explore Mars has been advocating for years is the importance of international collaboration that will enable us to get to the surface of Mars. We don't believe it's going to be possible without events like this. This is very important to be able to educate the world about not only what's going on in space, but how the entire world can participate in this process. It's no longer just about superpowers. It's a total global effort that'll be able to get us humans on Mars, hopefully in the 2030s. And so I know we have a shortage of time today, so I want to introduce our panel who will discuss how and why we will send humans and continue to send robots to the surface of Mars and around Mars. So our first panelist will be Joe Cassidy. Joe is Executive Director of Space for Aerojet Rocketdyne. Joe is also a board member, an Executive Vice President of Explore Mars, and a longtime Mars advocate. I believe, Joe, what was in the 90s or even 80s, you started advocating for Mars. So a good long time for Joe. Kim Garvin, who's been a NASA scientist for 37 years, is currently chief scientist at NASA Goddard Space Flight Center. He's the former chief scientist at NASA and has been a passionate advocate for the cause of sending humans to Mars for many years, and is currently advocating various exploration of Venus, I believe, as well. So very exciting times. And Janet Ivey, last but not least, is president of Explore Mars. She's also the CEO and founder of Janet's Planet. She's on the board of governors of the National Space Society, and she's one of the most effective STEM evangelists around the world, winning 12 regional Emmys and 5 Gracie Awards for her efforts. So very impressive. Without further ado, I'd like to bring up Joe Cassidy. Joe's going to give us an overview of some of the thinking behind how we're going to get humans to Mars using international, commercial, industry collaborations that will finally be able to get us to the surface of Mars. Joe? Is Joe there? All right, why don't we start off with Jim Garvin if Joe shows up. So Jim will explain kind of some of the science we'll be doing on Mars, and we hope to do. Never mind. All right, there's Joe. So we'll go back to Joe. So Joe.
Could I have my presentation slide? I think that's what happened. I was looking at my slide.
Oop, that's mine there, guys.
Oops. It would be the other package.
I don't even see them. So
I just saw mine, Chris, but we want Joe's.
Yeah, the other presentation, please.
There we go. Okay. Yeah, that's what's going on. So I tell you what, could you just switch the slides for me? If I talk, you can hear me. Okay. All right. So I'm not going to touch anything on my end. So the first slide. I wanted to answer the question for you about why Mars, and my answer is because it stretches us just enough. It's not out of reach of our technology today, and this is the first slide, but it does push us to develop things that will push us in a direction that takes us from where we've been for 30 years in low Earth orbit out to the moon and then on beyond the moon to Mars. And so some of these capabilities that we're working on today, for instance, on the left-hand side of the slide, you see the Orion crew vehicle. And Orion is truly international, as Chris mentioned, with the propulsion on the service module coming from ESA. And of course, Lockheed Martin here in the United States developing the actual capsule crew vehicle. And then underneath that, we have the Space Launch System, which is the giant rocket that we've been developing now for a few years. I'm happy to say that it's coming together right now down in Florida. I was there a few weeks ago and got to see it in the VAB at Kennedy Space Center. Everything is now assembled into one piece, as you see it there, except for the Orion, which is going to be brought over and integrated in the next few weeks. There's some final tests going on now in the vehicle. Those two will be put together and rolled out to the pad here within a few weeks. So the exciting thing for us is this hardware is coming together now, and we're on our way. The other elements, if we move over to the middle of the slide, after we get out into deep space, which is going to be a first for us for nearly 50 years now since the Apollo missions. We're celebrating anniversaries every other month now of the different Apollo missions. I think we're coming up on Apollo 16 now, but we haven't been to deep space for all these years. So now we're going to look at two things, really. One is a transit habitat, and that's the thing that the astronauts will live in as they make these journeys of many, many months to get to someplace like Mars. And that's something else we can do at the moon with the Gateway. And I mentioned the Gateway briefly because that's another huge international activity where we're going to work with our partners in Europe, our partners in Japan, Canada, to assemble a miniature space station around the moon. But it's also something where it allows us to develop the techniques of operations in deep space, aggregating vehicles, putting things together that we can then essentially we assemble our spaceship in space to go to Mars. And something like this transit habitat will be a piece of that. And then underneath that is something near and dear to my heart, which is the propulsive element. And for many, many of the pieces that we need to send to Mars, we're looking at things like solar electric propulsion. And the reason for that is it's very efficient. It doesn't need much propellant. And because it costs as much for us to launch propellant into space as it does useful payload and people, we just as soon take things out in a very efficient manner. And so what we're doing right now is we're actually developing the solar electric propulsion that's going to be used to transfer the Gateway elements, the power and propulsion element and the Halo module, which is the first habitat module, to the moon in 2024. And that's underway also today. So part of my theme here is all these things are happening now. We're not talking about something in the far future or something that's just being planned. This is work that's going on immediately right now. And then finally, moving to the right-hand side of this chart, we have technology for getting to the surface of Mars. Right now, we can put down about 1 metric ton with something like the Perseverance rover. That's about as much as we know how to do today with the current entry, descent, and landing technology we have. We've got to scale that up to allow us to put down something on the order of 20 metric tons. And so that's a big challenge, but we're working on that too. We have an experiment plan that's going to be conducted next year. And in terms of larger inflatable devices that can be used as decelerators in the thin Martian atmosphere. And then finally, the last element is the Mars ascent vehicle itself, because obviously once we have the crew down on the surface of Mars and they've completed their exploration and found this wonderful science that Jim is going to tell you about, we want to get them home. So we have to have a very capable ascent vehicle. And one of the things we're looking at there is the potential to use in situ resources as part of that vehicle, because if we could just use the oxygen, for instance, that we can get out of the atmosphere of Mars, which we've demonstrated already on Perseverance. This is another exciting thing. We've already shown with MOXIE, an experiment on Perseverance, that we can produce oxygen out of the atmosphere of Mars. And that's not something that we have to be in any particular location to do, because the atmosphere is everywhere. So wherever we land on Mars, we know with the technology we've demonstrated with MOXIE, we can produce oxygen. If we can produce oxygen, we've got an oxidizer for our rocket. So now we don't have to carry all that with us out to Mars. We can actually make our oxidizer on Mars. And that saves us enough mass to make this MAV, Mars Ascent Vehicle, kind of come together. So let's flip to the next slide. And I hope you sense that what I'm saying is Mars is challenging us, but it's not too hard. It's not too hard. It's not too much of a reach for us. We can do this in the 2030s, as Chris said. And so what we're showing here is just some of the architectures that we're looking at, taking those elements that I showed on that previous chart and combining them in ways that allow us to efficiently transport all of the equipment we need out, probably in advance of the crew, and pre-position it, and then to have a very fast, efficient transfer of the crew out to Mars to allow them to get there without too much exposure to radiation and too long of duration of microgravity, so that when they get to Mars, they're fit and ready to explore. And then we're trading off various options for either electric propulsion, nuclear thermal propulsion. These are all still in the works in the trade space. And we're looking at what will minimize the number of launches required, because obviously still the most costly element that we have in any Mars exploration campaign is the amount of material we have to launch off of the surface of Earth. So we try to optimized for minimization of launch, and that brings the cost of the overall campaign down. But we're coming together with ideas that look very promising for doing this. And we have, the wonderful thing is we have some terrific opportunities in the 2030s, starting with 2033, but repeating again on about a 2-year cycle that would enable us to effectively do this mission and achieve the dream that we all have of getting humans to Mars. So finally, on the last slide, I'll switch to the last slide now. There we go. I just thought I'd give you a sense of the scale of these vehicles. And I mentioned earlier that one of the things we're looking at and what we're going to work on starting with the Gateway is the idea of aggregating things in space. And you can see why in this picture. I just used 2 of the examples here of a couple of the concepts that we're studying for getting to Mars. One is the nuclear thermal rocket shown in the upper left. And then down on the bottom is the nuclear electric propulsion, which is a hybrid nuclear electric and chemical propulsion concept. But you can see with the space station there for scale, the size of the vehicles that we're actually conceiving of to get to Mars. And that gives you an idea of why we need to assemble these vehicles out in space rather than launch them all together as we did on Apollo. So Mars is challenging. It's not going to be something that we can just go and do right now, but we're working on the technologies and the elements that we need to do it. We're going to be pioneering and pathfinding those out at the moon in the next 10 years. And I think by the early 2030s, all those pieces will be coming together and we'll be ready to make that great leap to go to Mars. Thank you.
Thank you, Joe. So once we're there, what sort of science are going to do, Jim? And what do we need to do in advance of getting to Mars as well as robotic missions continue?
Well, thanks, Chris and Joe and Janice. If I could have my slides, please, I would thank you. So I want to talk about the science push that is enabling this frontier that Joe was talking about. And in my first slide, I'll just remind you that we're already on Mars. We're profoundly exploring Mars as a digital exploration frontier. 2 rovers from the United States, 1 from China, soon 1 from Europe, others soon to be there from Japan, and continuing that. So the era of the 20s we're in is a digital exploration of a frontier at Mars. So I can go to the next slide. I guess you guys can change for me. In the next slide then, remind you that if we can go to the next one, I don't think I have control, do I? I can? Okay, here we go. Next slide. Okay, there we go. So remind you of what we have today. Today we explore Mars through this virtual digital presence at the speed of command cycles that are dictated by telecommunications. And so we're there, but the speed of discovery that we people, women and men, are accustomed to as we explore is different. When we are out in a field exploration venue here on Earth, as women or men anywhere, we explore by measuring and characterizing to understand, eventually and ultimately to predict and interpret, so we can learn about our environment, our questions of life or whatever they are, physics, chemistry. That's how we explore. And that is a very immersive kind of activity that we're good at as people. We've been doing it for millennia. And so right now we've learned to extend that capability with the cycles of telecommunications that we're doing today with Perseverance, with Curiosity, to Mars. But the future is going to be that digital exploration ourselves at the speed of discovery that we the people of planet Earth are used to. And whether we bring our dogs with us or not, or other partners, robotic or otherwise, I just picked a nice dog there in the spirit of a canine. I think it was National Dog Day last week. But in any event, we will be exploring there ourselves. And I would submit to all of you, with the science we've discovered and will be discovering as we return samples and bring instruments to look for biosignatures on the Rosalind Franklin rover and other experiments that will result when samples are back on Earth from Phobos, from Mars itself, that we will be able to make that leap to go to Mars ourselves as a cosmic imperative. And so in the next slide, I'll go there, I want to remind you of why that's important. A lot of the Mars we think we know is actually hidden from us. It's hidden beneath the veneer of an atmosphere that we can see through, except during global dust storms. But a lot of the Mars that we're interested in is actually the under Mars, the Mars under the veneer of surface, soils, regolith, sediments, really, a sedimentary place that we want to discover. And we're learning about it now through radar experiments on rovers, but that under Mars is going to show us what we believe to be the buried ice capes of a Martian past. And that past climate state, that past environmental state of Mars is a marvelous frontier for science. That's where we can start searching for the chemistry, potentially, of life, the chemistry of resources. So we can explore that remotely using reconnaissance remote sensing, and missions are being studied now internationally for an international Mars ice mapper approach. But more importantly, eventually we're going to need to go there. And the vertical mobility of going to the under Mars, which will first be demonstrated as will be happening on the Rosalind Franklin rover by ESA in a couple of years, will get us to a couple of meters. Eventually, those big Mars ice capes may require us to get to tens of meters, like we drill in the Antarctic and in the Arctic. And that domain will require the on-site presence of people, machines, reconnaissance, information technology, all coming together. That digital exploration with humanity present will access this under Mars that we all think will be so compelling. It'll give us the history of the old ice, the old climate records, perhaps even a first shot at understanding whether there's extant life on Mars. Science will open that frontier, but it's going to take humanity, I believe, and many people believe, to go there and immersively explore it. So today, we fly drones on Mars. Ingenuity's demonstrated that 13 times. We operate robotic vehicles as Perseverance, Curiosity, Zhurong from China, and others soon. These vehicles are great. We operate them through telecommunication links that often take days to respond to a discovery or an activity or an event. When we get there ourselves, as you can see in this artist view, with a woman standing on the cliff sides of Mars, hopefully not too close, by the way. Valles Marineris is a long way down, so safety first for those women and men that go. But when she gets there, and when we think she must be there, she will be able to operate, and with robotic assistance, that will change the way we see the planet, the way we now explore the deep ocean, the way we explore with drones here on Earth to understand crops, even the spread of disease. That in situ immersive reality of Mars, not the holodecks of Star Trek, but the actual being there is going to be important. That's the kind of exploration frontier that we want to enable in the 30s. And ultimately, when we're there, we might want to ask, what will we discover ourselves? Well, first, we'll discover ourselves as the experiments in living in deep space off planet. And yes, the Gateway in Artemis will give us a fantastic taste for that. But getting to another world, Mars, where we can actually go, as you heard from Joe, where there are science reasons to go, but also compelling reasons as people to get off this planet to see a neck of the solar system that we want to explore is going to be important. And whether we see interesting rocks that remind us of sharks, as you can see in this image from Curiosity, I call it the Shark Tank view, but whatever you think, it also looks a little bit like a small sandworm from the dune ecosphere, soon to be on movies. But other than that, what will we see when we're there reacting to the Mars up close as it happens will give us those opportunities for discovery that we haven't had yet. That will change everything. And so while people ask, why should we go to Mars ourselves as human beings, as women and men of planet Earth? I would say, why shouldn't we? Because the tools are there, from engineering masterpieces that are already happening. You saw them from Joe. They're happening on Mars today. And so going there ourselves will change the game. With Apollo, we changed the game perhaps 50 years ahead of its time by putting men on the moon to explore. And we see the outcomes. Other than hundreds of pounds of rocks, the great exploration experiences, the discovery, Harrison Schmitt seeing the special soils, the discoveries by the Apollo 15 crew. And these things are just, they're echoes in time. So when we get to Mars, ourselves as women and men of planet Earth, we will make those discoveries. And whether it's a Shark Tank of opportunities, competing for those discoveries, or whether it's just what we are able to do as we explore that Mars, that will change everything. Science is ready. Science will use the 20s to set up for the opportunities. But as we go forward, it's going to be up to all of us to go there together. And so I think Mars, why not? Let's go. And I'll turn it over to you, Chris.
Thank you, Jim. Very fascinating. So now we come to Janet Ivey. Now, Mars exploration, I think, has a powerful role in stimulating STEM education and bringing people together. What thoughts do you have on that, Janet?
Well, it's like I will bring up my first slide and just say Mars is a destination of aspiration, inspiration, and yes, destination. And much like we've heard our fantastic presenters before me in their eloquence talk about this place, what I hope you note that the same energy that Joe Cassidy is full on expressing as he's getting excited about the gateway and propulsion and that sort of thing is the same energy that I see in my students that are elementary, middle school, and high school students when we talk about this possibility and this very close reality of them being the actual generation that will step foot on Mars. And so when I also hear Jim Garvin and his same happiness, it's like he himself calls himself a Martian already. And so I just would ask all of you that are listening to think about not only these very, very interesting high concepts. We hear great words like, this digital frontier and nuclear electric propulsion. So kids are able to concept and conceptualize and take this in. I have got 8-year-olds in some of my classes that are really pondering the great questions. So my big push here is very much like this beautiful Gene Roddenberry quote. Of course, we've just celebrated, I think, Gene's what would have been the creator of Star Trek's 100th birthday, the 55th year of the Star Trek series. So yes, I'm a Trekkie. But he had a great quote that may be my favorite, and it's, "We are on a journey to keep an appointment with whatever we are." And many people ask me all the time, Janet, why not the other sciences? Why are you so interested in space exploration? And why are you pushing these students to dream about Mars when we have so many problems here on planet Earth? And I say, because everything that we innovate to get out there improves life here on Earth. Everything that we learn about out there makes us realize this precious blue ball that we call home, where 7 to 8 billion people live, we can make life better here by what we're innovating for tomorrow on Mars. So I am coming to all of you today that, again, so many people, it's like I'll talk with, well, we really don't be in these courses until kids are in high school or undergraduate. And I say we must turn that on its head. The curiosity of an elementary student or a middle schooler, that is where this love and exploration really is made incredibly clear and manifest. And we must encourage it at the youngest levels so that by the time they get to high school and onto university, they know exactly the path they're going to take. The other thing that I would say, and many of you already do this so beautifully, but I only encourage you to do it more, mentor. If you want the reality and the pipeline of talent for ESA, JAXA, NASA, the Canadian Space Agency, the Australian Space Agency, so many, Luxembourg, all of these places. If you want that pipeline of talent, here's what we have to do. We have to be willing to get industry meeting with these kids. When there is a class or a teacher that calls you and say, hey, can you speak to my kids? Try your best to clear your calendar and say yes, because you never know who you are inspiring, because once they get a picture of you, once they see that you are actually the scientist making these things happen, all of a sudden that is reality, and it has gone from a concept to something they can grasp a hold of and say, wow, I think I might like to be that. In closing, I'll just say this. We must give our students Mars. They will be the people that walk there. And many times when I poll kids about what they think and why we should go to Mars, here's what they say. They say, because we will be better. And I said, we will, as humanity, we will be better. And they said, yes. And I say, why? And the students of today who are dreaming about being those astronauts that set foot on Mars. They say, we'll have a shared experience. We'll all experience the same thing at the very same time. Our very survival will depend on if we get along well together. If we begin to fight and argue and have strife, the mission will fail and we will die. And so these are elementary and middle school children having these very esoteric philosophical discussions that the reason we go to Mars is that so we can show people that the better angels of our nature exist and that we can come together as humans for the good of all, for the benefit of humanity. And that, my friends, is why we must educate on every level, preschool, elementary, middle school, high school, undergraduate, because when we get those young, curious scientists who are digging around in the dirt, who are wanting to put everything in their mouth and they want to taste and learn and grow and understand, let's give them these high concepts. Okay, so they may not understand it the first time, but the second time they stumble on it, they'll go, oh, I think I've heard of that before. So my experience, and especially in the last 18 months of teaching solely online, is that kids are hungry. They are desirous of something more challenging than we have been giving them. And what better challenge to give them than to give them Mars? And that's how we'll honor the giant leap of Apollo and all the great lessons that we learned over 50 years ago as we take this bolder leap to Mars.
Thank you, Janet. Brilliant. Very inspiring. Now, I just want to do a quick round robin. All of you have answered this question to a degree, actually quite well, but I want to pose the question once again. I'll answer it myself first, but then, maybe in different words, why Mars? You've all explained that very well, but each of you, particularly within your frame of your knowledge, what you're working on, but, personally, why you think we should go to Mars. I'll answer that first. And well, of course, I agree with all the answers about discovery, everything that Janet said, everything that Joe said as well. But one of the things that's really inspired me over the last few years, and particularly as we're programming for Explore Mars programs, to be redundant, it's the benefits to Earth. I mean, look at everything when you're looking at Mars, looking at problems that we need to solve to go to Mars, like how are we going to eat? How are we going to breathe? How are we going to communicate? How are we going to advance medical science so we can keep our astronauts healthy and safe on Mars? These are tremendous challenges. And when you look at these challenges through the lens of Mars, we could make dramatic innovations that will benefit us here on Earth. As we're looking at food production and, for instance, agriculture on Mars, on this extremely arid, dry environment, how can we actually grow crops? And if we can perfect that on Mars, think of the applications here on Earth to feed people around the world. And in the same thing with, whether it be with like cellular grown meat, 3D printed food, or, even things like artificial intelligence in medical practice. Of course, when we're like the astronauts up on ISS, they're still separate from the rest of humanity, but they're still just a phone call away, a quick phone call away. So there's a way to get them back to Earth or have quick medical consultation. On Mars, you're not going to have that. There's such a delay. So it could take upwards of 40 minutes or more. So all of these innovations that we need to advance to go to Mars, I think are going to have a dramatic impact on Earth for the quality of life, but also for the economy here on Earth. So I think when people ask me, why are we going to Mars? To benefit Earth. So Joe, do you want to jump in yourself and give any additional thoughts?
Yeah, no, thanks, Chris. I think you covered it really well. I always start with inspiration. I think the thing that Janet covered there at the end, I grew up during Apollo. I saw those landings as a 10-year-old boy when Neil Armstrong stepped on the moon for the first time. And that's why I'm doing what I'm doing today. I don't think I had a choice after that. I was so pulled in and inspired by that even though I struggled at points in my academic career, I always came back and I persevered and found my way through engineering school to get a career in this industry. But it was that inspiration that was always there, in the back of my mind. And then the technology, as you said, I get excited about that and all the engineering we're doing now to make this work. But that technology always does translate back to benefit us here on Earth. And I think, the other side of it then is it's going to establish our ability to do other things in the solar system. I mean, we'll go and we'll explore Mars, and hopefully we'll find that there once was at least life on Mars. So we're not alone, or we weren't alone. We're not the only place that has life in the universe. But the other aspect, and that's going to be just totally mind blowing, I think, for humanity, if that's the case. But the technology that we develop to go there will enable us to go, to Venus and do things on Venus as we evolve ourselves into a species that can move about in the solar system. We can go to asteroids. We can go get resources from these other places. The power technology we're going to need to support this kind of outpost on Mars will enable us to make things from resources on the moon. And I said once in my talk, the biggest challenge we have right now is everything we take into space has to come off the surface of Earth. If we get to the point where we can start to make stuff in space from resources that are out in space, that's just going to really open up the whole frontier and it's, very similar to our history on Earth, right? It's our ability to go someplace and then take the resources that we find there and make those resources something that we can build upon. That's really what I see as what's going to happen when we go to Mars, and that'll open up the whole solar system to humanity.
Thank you, Joe. Jim, we have 3 minutes and 27 seconds.
So this is a big question because there's two parts. The first is, well, aren't we on Mars now? We are. And so we've answered that question. We have invested in Mars. The human condition on Mars is now embodied in those robots that are exploring and bringing those wonderments, those inspirations that Janet and Joe talked about. So the real question is, why do we need to go to Mars? We, the human beings of planet Earth. And that's a bigger question. And that's what I think the cosmic imperative comes in, because the one place we can go, building on what we've done on the space station and Artemis and a gateway, is Mars. And the science allure of that is tremendous. Mars is the one place close by where we can reasonably ask, are we alone? Through the record books of the story and the rocks and the chemistry in the ice. And we know that from what we've been doing. So I say, why not Mars? Why should not we go? And whether we can apply everything back to Earth, very valid question. Mars is a natural laboratory for climate change run one way, and perhaps Venus is the other. But if we get to know these places, the feedback loops to how we understand ourselves and our condition on this wonderful spaceship Earth, in this Earth system science domain, is going to be tremendous. And the final point I'll make is, we don't know what we don't know. And when we went to the moon 50 years ahead of our time with Apollo, look at what we discovered. The collisional universe, the nature of the records of the planets being so different than our Earth. Imagine being on a Mars ourselves with that discovery potential there, not waiting for multi-year cycles of returning samples or data, but being there in the immediacy of that. The digital frontier will become alive when we're there ourselves. And that's why we have to go. I think the people of Earth are ready. Back to you, Chris.
Thank you, Jim. Janet, 1 minute and 32 seconds.
I think I'll just be quick, and you guys have heard it. We go, and in the words of astronaut Nicole Stott, she's told this to my students, we can't ever be good crewmates out there if we're not good crewmates here. And so my why Mars is, I think it's a grand experiment, not only for science, but it's also a grand experiment for humans. We can be better. We can be kinder. We can be gentler, compassionate, collaborative. All of those, and I don't really like to call them soft skills. I think they are necessary human skills. And I think as we work together with partners across the globe to attain these amazing human feats of putting boots on Mars, we're going to find the better angels of our nature.
Thank you, Janet, and thank you, Joe, and thank you, Jim. Spectacular presentation. Thank you for the European Rover Challenge. We enjoyed this very much. As I said before, we hope we'll be able to come in person in future years. But I just want to finish off by saying, if you have not registered for the Humans to Mars Summit, which is taking place next Monday through Wednesday, September 13th through 15th. Please visit us at exploremars.org and register, and it'll be streamed out through multiple platforms. So we look forward to seeing you there. So I hope you have a great rest of your conference.
Thank you, everybody.
Bye, everyone.
Take care.
Szanowni Państwo, świetna rozmowa Jima, Joe, Janet i Chrisa. Teraz czas podsumować ten pierwszy dzień. Jest ze mną Łukasz Wilczyński i Piotr Kosek. Panowie.
Cześć, witajcie.
Witam. Intensywnie przepracowany dzień, prawda?
Łukasz Wilczyński and Piotr Kosek are with us on many occasions. It was
No tak,
niesamowity dzień.
To jest człowiek, szanowni
So
Państwo, który
it's
poświęcił nawet
exhausted,
kolana,
just
tyle
a
się nabiegał w tych
guy
ostatnich dniach, że już
consecrated
ledwie
his
chodzi.
knees. He has been running, talking,
Kolana
his
pierdolą.
knuckles, his elbows.
No dobrze,
And
to zadajmy
it's
mu
just
takie
the
pytanie,
first
które
day, so
wręcz
let's
zaprosił w
ask
tym
a
momencie. Łukaszu, bo zobacz, no,
question.
wciąż mamy jeszcze lato,
So
słońce,
it's still
piękna pogoda.
summer in
Niektórzy jeszcze myślą o
Poland,
wyjazdach,
great
bo
weather.
chcą
Some people are
odpoczywać, a ty
thinking
bierzesz
about
sobie na
going
głowę
somewhere,
tego
and
rodzaju
you taking
przedsięwzięcie, które nie
something
dość,
like that on your
że jest w ogóle
shoulders,
jakąś
such a
logistyczną
challenge.
stajnią
It is a
Augiasza rozwikłać to i
logistics
poukładać w taki
mess,
sposób,
and
żeby w
you have to
odpowiednim momencie wszystko się
arrange
zazębiło, to
everything
nie
to
lada
make
sztuka.
it
Dlaczego ty
work,
to w
and
ogóle
it's a
robisz?
real challenge. Why are you doing that? I'm not doing that alone, of course. I'm nobody here in terms of logistics and planning. We have plenty of people here supporting this event. Of course, this is an effort in terms of logistics, but also emotions, because we are with each other for many years. This project gives us a lot. Yesterday we had a little opening and we were talking when we're doing that, because for some months there were some moments when we said enough for a short moment, but now we started to think that it's all about these young people coming here, these people inspired, these emotions. One rover that slanted and almost collapsed for a second, and their faces. So young people can come here, they can find answers to their questions, and very often among these young people there will be one or two people who will become another Elon Musk. For example, two bald guys and one hairy one hairy with us. And what is the greatest challenge? Because very often people ask viewers ask me about ERC. The greatest challenge is, and the question is how many groups, how many teams will join us. Last year it was especially risky because of the pandemic. Today, you know that not all teams that qualified came to the competition. Some people suffered some technical problems. So always there is this challenge, how many teams will be here during the start. Second thing is how to lead this narrative. You know it perfectly now, and thank you very much for providing your narrative for this event. It wouldn't happen without you, so it is very difficult to overarch all that. This is a unique event with the double Rover challenge, digital, remote and stationary. The display station and this lecture hall. You can always come here, ask questions. I could see a series of questions to Deputy Chairman of NASA. So a lot of questions, a lot of issues to be combined. Of course, we could limit ourselves to Rover Challenge itself, but we want to give something more. That was a great and inspirational conversation with Deputy President of NASA. But the guy who participated in 4 shuttle missions and has a great perspective on it. And a question to you, Piotr, because you have developed a great platform to educate about the space. When you're taking a look at a project like the ERC, you're taking a walk through Mars Yard and you see these families with kids asking many questions about different types of different sizes of rovers and so on and so forth. What do you think is the greatest value in this project? Because we all understand that effort, but if you were to reflect on the most important added value, what is ER what? No, I'm just kidding. This is something incredible, and I've said that before. And before this meeting with the Deputy President of NASA, my first encounter with ERC was during the first year of operation of my channel. You were here. I came by train from Gdańsk to Kielce. I had a seated but I've never seen that. You know how Polish railway works. So the atmosphere was great. I spent great time with fantastic people, and I had an opportunity to meet with a guy who put his foot on the moon. How many people managed to do so? So the Harrison Schmitt meeting inspired me to invest that time and to invest even more in Astrophase, in my Astrophaza channel. So really chapeau bas for Łukasz and for his team and everything that they managed to do. And I'm not telling that because he invites me here. If somebody told me 10 years ago that I will talk with the Deputy Chairman of NASA, of course, technology made some progress, but it doesn't give me opportunity to do it every single day. I will not have another opportunity to talk with ESA people, with NASA people, with all people creating robots, creating shuttle spacecrafts. This is a wonderland, the cosmic Disneyland for all of us. So you might be surprised by this readiness and willingness to share responses to every, even the toughest question from the side of our guest from NASA. But he's passionate. He's so passionate about it. He likes to do it because he's a former astronaut. It's a living memory that he wants to share. Let's talk a bit about stereotypes. People are thinking about rovers. They imagine some guy sitting in a tent and maneuvering with some toy through some race trail. Let's talk about serious math, serious algorithms. How does it look like from this technical part? What makes it a serious contest, because people do not understand that. Let's start with the very word rover. In Polish, it's łazik, because people are smiling at it. And łazik in Polish, they don't know what is the association with it. It's so a funny word a bit. So I participated in a space talk, and I talked to Professor Bralczyk, the Polish language expert, and he said that łazik is something that walks, that crawls, in fact, in Polish. So, and these are serious engineering contests. They start on paper in January. In January, the year prior to the contest. So kids, they see our regulations, terms and conditions on taking part in this contest before our team starts to work in October or December. So this is the procedure. But tell me something totally different. And now if you go to this Mars yard, no, I will stop you. I will park you here because I will not let you speak freely because it's highly dangerous. So now, on the Mars yard, there is one round of competition that is always there every year. It's maintenance part of the competition. Okay, so servicing and maintenance works with Rover. So we have this Rover that approaches a score table and a dashboard, let's say, and they have to push precisely each and every button, and somewhere in a tent there are people. This is an autonomous task that depends on the team. That depends on the team. But generally, there are some tasks where somebody has to plan it, program it, and map. The best teams do it. So tell us about it, because we have different types of competitions within our general challenge. So we have some navigation tasks. This is a little bit task. What's going on there within other competitions? So we have a task where you have to switch off the camera. This is a blind navigation. You have to switch off cameras, and this is a forward-looking competition. But as we could hear today, in the 40s, we will have men on Mars, for example, after the first flights, and there will be some supply centers that will be created there. And if something will have to be serviced, repaired, the rover will be an extension of an arm of an astronaut. So it will be a teleoperations. This competition is about that. So that seems quite simple from aside, but our teams, they see only a part of the picture. They have to look for the panel. They have to program and their rover and to prevent the panel from falling off. And why engineers are so masochistic? Instead of giving them great camera, great lighting, and great conditions to approach, you will have a limited view and so on. But that is all about, it's worth stressing. It's not like that you want to torture them. Indeed, these teams of scientists, of engineers, they will have to tackle such facts that they will not have the state-of-the-art lighting and cameras, because it doesn't work like that. First and foremost, when a rover is sent to another planet, it is a sort of laboratory, and each team is responsible for each and every element component. There are a series of experiments carried out by a rover, so everything has to be stuffed there. You would have to send a bus there. To comment on Piotr's joke, so the 17 minutes in order to send a signal from Earth Earth to Mars, imagine that to send 4K image from Mars to Earth, how much would it take? Tomorrow we'll talk about the moon, and we will have a block before noon focused on the introduction, education to teachers, to students. Please invite people, because we have a lot of people present on the Mars yard in the display exhibition part. Could you see it? Maybe they are not aware that they can come and they can listen to a deputy administrator of NASA, because have you seen what's going on there? It's incredible. In 110 we have Lunar S. So we are taking a look at an analog mission taking place in Piła. So it's a lunar big brother. We have some cosmic and space industry companies. I didn't have an opportunity to be there. I've already got enrolled for some workshops, because tomorrow I will be there intense. The real leader setting himself aside, putting his hands off. But okay, tomorrow we start here. The moon will be the main topic, the moon and the orbit. I've told that today it was about tomorrow. Tomorrow we'll talk about the present times, and we will talk about history on Sunday. So today we'll talk about marketing, how these businesses can open, and about space mining. We will talk about helium-3. We'll have Astronica with us, so people who created the mole, experts in drilling. So we have a lot of specialists who will tell us everything. And I will be the moderator of one panel discussion about the manned missions. So we will try to dispel some myths and to describe some challenges in this limited time. Maybe we'll talk about space tourism, but it will be a surprise. Okay, so Łukasz goes to an orbit tomorrow. No, my wife told me no, but I will be here until Sunday, so I cannot go anywhere. But so many fantastic things. We can interact. I can see a lot of people after a debate or after a panel. They do some networking somewhere in the corridor, and this is why we created this event. Tomorrow we will have some people from Georgia, from other countries who already. So okay, but we will have a live broadcast starting at 10 a.m. So you can watch everything at Rover Challenge website at astrofaza.pl in Polish or in English. So we start tomorrow at 10 o'clock. Łukasz, we are after the first quite intense day, but already now we can congratulate you on another great edition of ERC. And Piotr, thank you very much for assisting us and supporting us with your great experience and your impact that you have on educational activity in the Polish internet. So thank you very much, and join us tomorrow in the main aula and ask questions, and come to us and take seats in the first rows. Okay, so see you.